Morning. Good to see you all here. We had a great day yesterday. Really learned a lot. I thought we had some really productive discussions, and I hope everyone had a good time last night at the icebreaker. The sliders were great. I don't really have any opening remarks except at the end of the day, I hope everyone sticks around for the breakout discussions. So I guess, Eric, you'll introduce our first speaker.
Okay, so our first speaker is Greg Thompson over here, and he's going to talk to us about mostly sunny mostly cloudy versus partly sunny, I believe. He's here at NCAR or UCAR and also JCSDA, which stands for something. And maybe if we're lucky, he'll tell us what it stands for.
Thanks, Eric. I'll give you a one. Okay, thanks. I'll probably put my phone out. Okay, yes, I'm now at the Joint Center for Satellite Data Assimilation. It's a mouthful to try to put those letters together since they don't go so smoothly as some others. I was here at NCAR for 27 years before I switched roles over to the Joint Center. So I'm doing some new stuff now, which is kind of fun, but it was a little scary to make that move after all the years I spent in the research applications lab. I will tell you, there's a huge amount of this talk that's going to be blending my experience of the last, jobs I did with cloud physics and so forth, since that's my specialty. So my new work, I have a lot less material for, but hopefully the next time we have one of these meetings, I'll have something more fun to show with the newer stuff rather than piecing together old information, but there's quite a few pieces of good information, I think, in here anyway. The title is probably not as appropriate as when I wrote the abstract. It's funny how that works. But in any case, let's just go through here. So here's some of the motivation for this talk. And I'm going to make it, semi-clear. On the left side here, as it goes, infrared brightness temperature from, long wave infrared. It says channel 4. Oh, that's because it's from 2013. Okay, so it did. It precedes GOES 16. So back then, channel 4 was the long wave infrared. And on the right-hand side, thanks to Jason Otkin and company, who's in the room, is the synthetic satellite image, taking all the cloud microphysics data and the rest of it from the model, in this case, WRF. So most of what I'm going to talk about is going to involve WRF, but not entirely. I'm going to be as model agnostic as I can be. It's not important. And I'm going to show what I've found over most of my career. This was published in 2016. A study that Jason and I and others did on how well does the model give a brightness temperature after, forward operator, of course, to the equivalent of a satellite. And this is rather typical. I want to show you those 5 areas that are highlighted there that are basically saying, well, look, well-forced clouds are well-forced in the model, so you get a pretty good overall picture of what the clouds are doing in the model. But what I also want to say is, if anything, if you spend enough time just using the eyeball test, you see that there's pretty much a consistent thing that there's an under prediction of clouds. In most models, we have had an under prediction of clouds. That's one. And so just look at the circled area number 1, for example. The low pressure system is kind of an old low pressure in the springtime on the mid-Atlantic of the US. And you can see far more cloudiness in the left image than the right image. That's one of the details. Another detail is, of course, that convection that's in northeast Oklahoma. It kicked off in the model at 18Z. Now remember, springtime, 18Z, noon, central daylight time, and it's already convecting as a strong storm in Oklahoma. Whereas what you see in the observation is a dying old MCS from the night before, or some convective complex from the night before is mostly what that thing is. So you can already see some discrepancies. But the second item I'm going to show, which is much easier to visualize in this histogram diagram, is that there tends to be this consistent behavior in models with this deficit of clouds in this, let's say, -10 or -5 to -20 region. And there's a bit of an overabundance in this 0 to +10 region. And so the left side of the figure is with, looking at cloudy pixels only, and on the right-hand side is all pixels from the entire scene. Anyway, so I published this in 2016, and it was probably progress that I did in 2015 when Eichenberg et al. In Germany pretty much publish the same thing. So this paper came out in this within months of my own. And this is, for my case, it's WRF. For the German paper, it's Cosmo, the best equivalent of WRF for the German DWD center. And this is them changing the microphysics. Even using 2-moment ice microphysics didn't really make a difference, as you can see in the color chart there, because the red is the MSG Severi, the Meteosat, and the black and the green lines are the model information. And you have the same exact behavior. You have a deficit in basically the same zone. Let's call it -5 down to -20, and you have an abundance in the really close to 0 to 10 Celsius. So I guess where I'm coming from here is I don't really believe this to be a model problem or a microphysics problem. Sorry. Yeah, I did say that right. It's a consistent behavior. I don't think there's a model that can do this well, and I don't think there's a microphysics scheme that can do that well. These are quite different microphysics schemes in this case. Mine in one case and Axel Seifert's in the other, et cetera. So I do think this is a common behavior in models, and there's plenty of other papers in the literature. What I do like to note in the difference between these two graphics is that look at the tail all the way down to 220 Kelvin. And there's very clearly a problem in Cosmo having an abundance of clouds at 220 Kelvin that the observations didn't show until they changed the Cosmo model to have 2-moment ice. 2-moment cloud ice did help the situation. So the green line drops down closer to the observed red line. And if you look at the WRF results, particularly, obviously with this case, this is my microphysics, it also has a very good tail into the cold temperatures. So in other words, the cloud anvils and the ice clouds are done pretty well. So I'm really happy for that. And yes, I invite to interrupt at any time. Josh.
I still feel like those pendulums might be switched because we see in the cloudy pixels only, it doesn't go up to, cloudy pixels shouldn't go up to 3040C, right? So I think your histograms are right, just maybe the titles are flip-flopped.
Oh yeah, that would be a good point. How to fix that? Hopefully it didn't get in the paper like that. Whoops. Good
I
catch.
just want to make sure that that was physically that. Okay, that sounds good.
Very good catch.
You do one bar.
Now, this is a fun case I was part of, and this is for the eye candy part of the presentation in a way. These two sets of movies are not, the set of 2 movies is not going to be timed correctly. On the left is 5-minute GOES data, on the right is 15-minute WRF output data run through a synthetic satellite forward operator. And I bring in this particular case up because it's a nice sized winter storm that I actually got on board the Convair aircraft from Canada for a field project on icing of aircraft. So this was in 2019, February of 2019. We were based in good old Rockford, Illinois, where we had temperatures that dropped to -32 Fahrenheit that winter, and I was there for that. That was a lot of fun. But already I want to show you the difference because you can already see in just this snapshot near 1100 UTC, the cold cloud there to the north where it's snowing through Wisconsin and Minnesota and over Lake Michigan is certainly colder in the synthetic image than it is in the observations. But overall, I mean, there's some real patterns here that are really pretty decently done, including some small scale features. I'm not going to excessively go over all those features right now, but essentially just set these 2 movies in motion. And again, they're not going to be synchronized properly, unfortunately. And then you're going to see an aircraft track racing around because that was us on the airplane. So we flew around through the icing and got all into some serious icing after we left that snow. There's the aircraft track. And so with every 5 minutes, that's the segment of the aircraft along that track. And we flew around all through this super cold water cloud. So this is a -10 roughly in Illinois, central Illinois, -10 Celsius cloud filled with super cold liquid water, putting on an amazing show of ice on an aircraft. And then we landed at Indiana. What's that? Not Evansville. I forgot. Oh, Terre Haute, Indiana. Heck, who's from Indiana that knows where that spot is there in West Central Indiana? I forgot the name of the airport in the town. Anyway, refueled, took back off and redid a pattern back to Rockford, Illinois. And so we had 2 flights. We landed in Rockford, Illinois, and Alexei Korolev, for anybody who knows him, is a very famous Russian scientist at ECCC, Environment Canada, who designs instruments and flies them around and on the Convair. And purposely they try to fly into the worst icing they can get. He's been doing this for a very long time, and I've known this Canadian group for a long time. And we land, and he's never seen icing as big as we accumulated on this aircraft. So this conveyor had chunks of ice, almost, I don't know, 6-7 inches. I've got hundreds of photographs of it because I was on that flight. It was scary. I don't know why I wanted to be on that flight. So made for great photographs. But again, you're seeing most of the cloud features handled pretty well. You can see a high altitude cloud coming in from southwest to northeast in the jet stream, plus the low pressure coming across Iowa. You can see all the major features. So the cloud forecasts are actually, they're not half bad in a lot of situations. Now, convection aside, we're not going to get the convective forecast of the supercell in Oklahoma at the exact county and time that it happens that easily. That's the harder stuff. But these synoptic features are really pretty well dealt with, pretty well. And then we can have a discussion of all kinds, getting into way too much microphysical detail about, well, is the cloud ice the right size to produce the right radiative signal here at the top of the atmosphere? Is that colder cloud in the model because it's the wrong ice size? Because that affects the radiation. So we have to have the ice size correct. To get the ice size right, you have to have the mass right and the number right. So there's so many complications here, but the forward operator has to be coded correctly too, and consistently. Okay, so I'm going to make this conclusion. You can jump at me if you disagree, but I've been doing this for 30 years, NWP cloud forecasting experience. And I have a plethora of papers to back it up that say all NWP models have a cloud deficit. Okay, sometimes there's exceptions, but mostly we have a cloud deficit. Almost in every case, you can also prove that because the downward shortwave radiation reaching the ground tends to be excessive. How are those two not in sync? Of course they are. They're perfect. That's how you know that there's a problem with clouds, is we have a downward shortwave radiation excess because we have a cloud deficit in general, all models. Okay, what do we do? These are the things that I've been involved with myself that I'm going to spend pretty much the rest of the talk on, which is there's some really, really simple things that cost you almost nothing, which I've labeled time lag ensembles. And then there's just model ensembles, which I personally haven't been involved with, but NCEP does them, right? We have the, what is it, the SREF, or is that what it's called? HREF, yeah, it's basically an ensemble of opportunity. Is that what you would call that? If I'm getting the names right, but I know about it, but I wasn't involved in that so much. The next one, the physics ensembles, I have been involved with a lot. The Weather Service's hazardous weather testbed based at SPC, Norman, Oklahoma, includes all kinds of great collaborations and stuff. And I'm so glad to be a part of it. And what they're doing is running physics, there's many papers here, Adam Clark being one of the lead authors, many papers that compare the Thompson microphysics scheme, the Morrison microphysics scheme, the WSM6, the Jason Milbrandt scheme. The list goes on and on. WRF has what now, 11 or 12 microphysics options. Guess what? I've been one of those people for forever, it feels like. And it gets a little old when everybody says, writes another paper, WSM6 beats Thompson in this way, and Morrison beats WSM6, and Milbrandt beats this, and now there's the P3 scheme. And, I've been in that business for a little too long. Maybe that's why I left and switched jobs. That's not why I did. Okay, next topic in the ensemble world is the stochastic parameter perturbation. So the next group of slides is going to be about that. And then I've been doing some work in cloud fraction schemes and also in data assimilation. So this is kind of the overview of the talk. But I swear to you, last night, or it was afternoon hours, I said, I just don't know why this didn't come to me sooner. I'm embarrassed. Why? I never asked the question, why do models have a cloud deficit? Why have I been working at this field for 20 years and not actually asked this question? I'm actually embarrassed. I haven't really thought of why do they have such a bad cloud deficit? I've only worked to try to solve it, but I've never with the what to do question. But now I come back and do this question of why. And it's partly because I have done some other research recently on this first topic, initial conditions, too dry. It's a question. I'm not saying I have the absolute answer, but I have a piece of evidence to show you. Here's an analysis I very recently did. In this case, IAGOS is a data set from Europe in which they take humidity measurements from airplanes flying around. And this is a publicly available data set. So this is like a Weissela RS-92 sensor on an airplane. If you don't know what Weissela RS-92 is, it was the Weissela radiosonde humidity sensor. Okay, and now they put it on an aircraft because we know we need better measurements of low humidity environments. And the RS-92 is actually pretty good at low humidities. Now there's RS-41, the newer version of that. So our friends in Finland are making a very good humidity measurement. Look at this distribution of RH ice in the horizontal axis there. Look how it goes from 0 to 100% up to 160%. And if you trust it, the aircraft data tells you you have lots of frequency of 100 to 150% humidity. Do you think we allow 150% humidity in our initial conditions with respect to ice? I got news for you. Not very often. Why? Because the model is going to get rid of it. This is the physics connection. The model is going to get rid of that 150%. It don't like that. I will say very clearly, the Thompson scheme likes 150%. Look at that WRF line. That WRF line in purple shows that forecast, 12-hour forecast, 24-hour forecast, it doesn't matter. This is a comparison of 1.7 million data points with 253 flights spread over 5 months, 5 months plus 5 days. And I'm proud of this. I've worked my career to make this plot, and I only just made it this year. And then look at the GFS. Why am I not surprised? GFS has how many points above 100% RH ice? Why does it have none effectively? Because they have an ice saturation adjustment scheme. That's the point. Ice doesn't just nucleate at 100% water. Sorry, strike that sentence. Ice does not nucleate at 100% ice saturation. Otherwise, we'd have snow all the time and hardly ever have freezing rain. There'd be no such thing as freezing rain. There'd be no such thing as aircraft icing. I spent a career in aircraft icing, essentially. And that's why, because ice doesn't happen easily. Ice takes ice nuclei. It doesn't happen easily. I'm going to have my Craig Boren hat on right now, looking at Jason, and jump up and down for anybody who knows Craig Boren about having to have ice nuclei. All right. So message of the day is we probably, at least in the United States modeling system, the GFS and the NAM, we have too dry of an atmosphere for our initial conditions. If you want to really think about it, even satellite data assimilation isn't going to generally help that because there's so few particles per million of water vapor at the altitudes that we're talking about for this plot. So it's not going to make the biggest difference you're going to spot on a water vapor image, for example. It's too low of an amount. So a little bit of data assimilation is going to get us a little bit more. I'm hopeful it'll get us a lot more, but it's not there yet. And the GFS would just wipe it out today anyway. So what's happening? That's why I have this possibility still as a question mark. Too dry, we start too dry.
You see the difference then between the GFS and the WRF clouds?
The WRF clouds stick around better. I wanted to have the radiosonde data on here by today. I didn't get it. So if I do show you the radiosonde data, I hope it looks as close to that blue as possible. And I think it does. It's the same sensor. The RS-92s and the RS-41s from Weissela are what's flown on more than half of the world's radiosondes. And I have all that data at my disposal. I wasn't able to make it on this plot. And I hope to show you the IFS data in a future meeting because I'm going to try to get the IFS data to see if it too has a low bias. Look at ERA5, the green line on there. ERA5 is a reanalysis product and it too is too dry. And they're even using an empirical relationship post-processing to bump that curve is what I have learned. I haven't double checked it, but I have learned that they're just statistically pushing the data toward the IAGOS data. So I'm very, very happy with that piece of the Thompson microphysics giving high values of supersaturation. Okay, what else? Physics ensembles I'm not going to talk about today. Time lags I'll take a couple of slides on. Okay, time lag ensemble. This is work I did a few years ago where we just take the HER. It runs every hour for 18 hours. So you can easily imagine you can have many, many forecasts valid at the same time. If you just say, we'll take the 1 hour before that, add 1 hour to the forecast lead time, and now we have the same valid time. So what that looks like in visuals is here's an 8-hour forecast in the top left panel, 5-hour forecast top right, 2-hour forecast, and then TLE. Okay, now this is super cold water being averaged together on this plot. So when you look at the satellite image at the same time on the right, you don't see any of the clouds in the Atlantic Ocean, the Gulf of Mexico, because those are all warmer than zero. So this is my icing work, always doing the icing stuff. But the point is going to be the same, that the cloud that's below 0 Celsius here is what's highlighted in the model graphics, whereas we're seeing snow cover, for example, this white stripe here in Nebraska is not cloud, that is snow cover on the ground, where this is a January case. Whereas this southwest and northeast cloud is actually cloud. And if you can believe it, even in that tiny amount of cloud there near Oklahoma City, there was a pilot report of icing. This is why I use this as the graphic. The 8-hour forecast has no cloud stretching down from the Great Lakes down toward Oklahoma. The 5-hour forecast has it. The 2-hour forecast has a hint of it. My point just being that as cheap as a TLE is to compute, it gives you added benefit. It's making more cloud regions because it's taking slight errors in each forecast and putting them together. And so it actually builds more cloud. It's a cheesy way to do it, but boy, is it simple to do. And it makes better icing forecasts. There's a paper on this too, where we used it to improve icing forecasting. Okay, that's it for TLE. I'm going to switch to my latest published paper of dealing with stochastic parameter perturbation. To represent the uncertainty in a microphysics scheme, both Sarah, Griffin, and Jason are here in the room. They're co-authors. Sarah has a first author paper as well on this, and I just want to give you a little quickie explanation of what that looks like. Judith Berner has this technique to make these nice coherent spatial patterns that you can change the magnitude and the temporal scales of and make it look like a bunch of amoebas moving across your map. All that is a perturbation field that we're then applying to some parameters in the microphysics scheme. So there's 100 different ways we can set the parameters to make it either fine scale on the left or very broad scale there on the right. But just take it to understand that these patterns are configurable. And then we run ensembles with the patterns, right? So we say, we're gonna mess around with some parameter that I know to be very uncertain in my own microphysics scheme. Well, what would that look like? So for those that don't know innards of microphysics the way I do, I'm just going to try to dumb it down as quickly as I can. A here, alteration of microphysics scheme A. The Graupel y-intercept parameter is one of the biggest tuning knobs in any microphysics scheme. It's because Graupel falls fast. It's big and dense and heavy, okay? But how big and how dense and how heavy? Is its density 400 kilograms per cubic meter, or is it hail-like with 800 kilograms per cubic meter? It's everything in between. That's the problem with a microphysics parameterization. It's all over the place. These schemes tend to use a figure like A here with a diagonal line, and that spot where it intercepts the y-axis is called the y-intercept. If we change that y-intercept by an order of magnitude, it changes the entire distribution. The whole mass of Graupel comes down slower or faster. The biggest Graupel that hits the ground is bigger or smaller because it's held by that y-intercept. So that's how important it is. But then again, I've been tuning that number for 10 years. There's no point to it, folks. There really isn't. There's no answer here because it's uncertain. So what do? Well, let's use that stochastic idea and say, let's just perturb it. It's a way to make an ensemble member. And to me, it's the most physical way to make an ensemble member. So Judith and I and Jason, we put together a little NOAA JTTI project and did this for 3 years, about 3 years ago, I think. And we let that thing vary because it's unknown. And I was the microphysics guy who came up with, this is so unknown, let's perturb it. Same thing about these other two items, cloud water shape parameter for the distribution. That thing varies from 2 to 12. What does it actually mean? It means you shift the distribution of your cloud droplet distribution. You either get tiny drops or big drops. What if we say we don't know what it is? We do to a degree because the aerosols control the nuclei, the size distribution. But we don't have measurements of aerosols everywhere all the time. So we know it's uncertain. Why not perturb it and find out what happens? And then the last thing is that the activated number of CCN gets influenced by the vertical velocity. Well, guess what, folks? We're predicting the vertical velocity with a grid scale of 3 kilometers in WRF, in this case. We're not resolving every updraft at 3 kilometers. There's going to be 1 kilometer and ½ kilometer updrafts that have double the speed. in the updraft or downdraft for that matter. So why not let that be a parameter that we perturb? Okay, you can take this to any value in a microphysics scheme and do this till you're dead. There's so many things you can choose to do. I mean, this could take 100 years if you wanted to do everything, but I picked the big three that I know mess around with the results the most. And then we ran experiments. I was all happy with this idea because I finally get to do ensemble forecasting, work a little bit with Jason and his friends. And the results were not what I was expecting. So there's 3 parameters that I can change independently or in combinations. So there are 7 permutations. So the top left is the GOES brightness temperature on this day in 2017, my birthday, May 16, 2017. I didn't choose it for that reason. It was a good convective day. And to the right of that is the control experiment. No perturbations whatsoever. It's Greg Thompson microphysics code run just as it was released in WRF. The next one on the right is just the first experiment where one of the 3 things was tuned and so forth till you get all the permutations to the 7th item in the bottom right hand, where all things are turned on simultaneously. And I beg to ask you, which one looks the most like observations? So do the eye test and see if you can think of one that looks like it. I hope you're going to agree with me. None of them look any better than each other. There's no winner here. And that shouldn't surprise anyone. I really believe that should not surprise anyone. Okay, what does it look like statistically? Here's the bias of 1 hour precipitation amount. And there are all 15 members in the top left corner, the biases. Can you distinguish one from another for the forecast times from 0 to 48 hours? Yeah, you can't. How about the SPP members in the top right? That's just the SPP. And then the bottom left is the whole point. We also have to have a control simulation and white noise because any perturbation is going to make a change. So we introduced very small temperature perturbations in the boundary layer only and ran 4 experiments with white noise together with the control to call that the control ensemble. And they don't differ from the others. And there's nothing jumping out at me here, right? Nothing jumping out at anybody. Well, that's kind of the point. However, the news isn't as drastically bad as I say. Here is Sarah's very good analysis of the mean bias error for the 5 spring dates in May. And you see the red versus the blue. The red looks to be a slightly lower mean bias error, but the 95% confidence interval on the data show you that it really, really doesn't look all that better. And so you can't do much, at least in this example, with 5 cases. Now remember 15 ensemble members, but make it 55 ensemble members. I don't think it's going to make the difference. However, in the cool season, January data, now look at the bottom plot of the 95th confidence interval. Control has a higher bias, statistically significant higher bias at the 95th confidence interval. So that's good. So we did make an impact in wintertime forecasting more than we did in spring. I'm not too surprised. Convection is hard. And this January cases don't have much convection. Even with a continental United States where you can get some convection in the south, it's not making, that much of a difference. So this is the good news out of this talk, is there is some improvement by this technique in doing this with the wintertime cases. Sarah also made this very beautiful scorecard with the ranked, continuous ranked probability skill score. And again, here, what you want is everything to be, you would like a dominance of blue in this case, meaning blue is better than control, blue being, SPP is better than control. And again, the top set of panels is the, of squares is the May events where you get this very largely mixed results. And the lower panel is January results where you get a more obvious improvement. So 2 different ways of showing some of the same information. So very good.
Which is the cloud top? What are we looking at?
Sorry, this is for brightness temperature, whereas the previous one of the previous ones I showed a bias of 1 hour precipitation amounts. And these other lines were from the brightness temperature analysis. So I will say that we did things like max hail size, brightness temperature, precipitation amounts, temperature. We verified a whole lot with this set of runs. It was a big deal. I'm only showing you a small amount. And there's a paper on it, so you can go dig that up if you want. So in the end, I felt, well, I shouldn't be surprised here. Why? Really, the why answer on that one is because microphysics doesn't actually make much of a difference in clouds initiating. You have to have the dynamics. If you're not lifting air up, you're not making clouds in the first place. So as much as I'll say, yes, Thompson microphysics is better than Morrison and Milbrandt, damn it. Sorry, Hugh. It matters in smaller amounts sometimes, and it matters a lot, obviously, from GFS physics for getting rid of all relative humidity of ice above 100%. So there's certain aspects that matter a lot, but in some bigger manner, it doesn't matter as much as what created the clouds. If we want to get better cloud forecasts, it's not really going to come from too many more microphysics changes. Hence, I left NCAR and I'm now at Joint Center for Satellite Data Assimilation. But we still have a ways to go, and probably with other methods. I do want to say in closing about the SPP ideas is that I was also with the NOAA GSL folks here in town who have applied SPP to the radiation scheme, to the convection scheme, and to the PBL scheme. And that's where I will say there is value, applying SPP to all four: microphysics, radiation, convection, PBL, because together that's what's going to make the different clouds form in different places and produce different dynamics, etc. The only time microphysics matters a ton for cloud initiation is a downdraft running into something and making a new cloud. That's where the microphysics matters the most when you do that, because the evaporation is what drives that situation. But on this planet, that's not happening all the time everywhere. Just synoptic fronts are making plenty of clouds. Okay, moving on, cloud fraction schemes. So I'd like to bring this up, and Jason's present as well. David Mako was a student along with Jason and I at the direction of Bill Cotton up at CSU up the street in Fort Collins. Well, this is his master's work. And I wanted to mention how we have a pretty continuous generational knowledge gap because we just keep doing something 20 years after the persons before us. So this is a Mako paper from 1994. And it turns out I dug it up because it's basically evaluating various cloud fraction schemes in a mesoscale model at 5 kilometers. Well, hers at 3 kilometers, close enough. What can we do? Because we certainly need to add more clouds. So I started thinking a cloud fraction scheme is a way to make more clouds. Why would you do it? The reason is because if you make a little bit of cloud, even if it's, let me use the word fake cloud now. So I make real clouds in the explicit microphysics. Now I make fake clouds in a cloud fraction scheme. I just say, well, it's 89.6% humidity. That probably means it's 10% cloudy, right? If it's 10% cloudy, you tell the radiation scheme it's 10% cloudy and there's 0.05 grams per kilogram of liquid water. Okay, the radiation scheme now radiates that cloud. You cool the atmosphere because of the radiative cloud top cooling, and now you bring it closer to saturation. So 89.6% at the starting value, giving it fake clouds, can generate clouds because of cloud top cooling, because it can cool the atmosphere. That's what I was going after. It works. I don't have great singular results of one to another, but I can tell you it works. You're making a radiative impact. So there is reason to think about subgrid scale is a better word than fake clouds, isn't it? I like the word fake clouds myself, but people love to throw around subgrid scales. So Mako's paper here shows you a Landsat scene off the coast of California. And then here in the right-hand side are 4 different fractional cloudiness schemes that he implemented: the Kovmasto scheme, the Sundquist scheme, Eck and Mart, which is Mike Eck here in DTC across the pathway there, Manton Cotton. So there's a Bill Cotton scheme. And then he tested even more. Here's another list: Albrecht 89, Betts and Boers, etc. So there's this big list of things that he tried. And I highlighted 2 boxes here. The Kovmasto and I'm probably not saying the name right, and Sundquist schemes identified both partial and solid cloud areas very well. These schemes are very easy to code and at the same time offer the most reliable fractional cloudiness amounts among the schemes tested. And then the other ones, subgrid scale condensation schemes, Manton and Cotton, blah, 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 did not compare to observations and took significant effort to code these parameterizations. The results may improve if horizontal spacing is dramatically lowered. Well, great. We're not getting below, this was 1994, 5 kilometers on a nested grid, admittedly. Imagine how far we are away from 200-meter spacing or something that might be needed to do this better. We're a long ways away. So what did I do? I looked at this paper and said, the first two schemes I'm going to implement are Kvmasto and Sundquist. They literally take 3 lines of code. So I implement into WRF the two schemes and find out that the Kvmasto doesn't look so good. It makes it too cloudy, and the Sundquist scheme with a little bit of tuning can give you whatever answer you'd like to get it out of it. It's so easy. The knobs are so easy to turn. So that's what I did, is I went down that route. I'm a very simplistic person most of the time and say, I'll take that route first. So reading this paper and having somebody just flat out say, they're easy to code, they produce good results to observations, I'm jumping all over that paper. So while we're on the topic of cloud fraction, Jason mentioned this, at least in the intro area, and other people hopefully are going to get this picture really, really quickly. What amount of model microphysics cloud water or cloud ice or snow constitutes a fully overcast 100% cloudy type condition? Okay, so I've got my little fancy graphic here. Is it 10 to the minus 12? Is it 10 to the minus 11, 10, 9, 8, blah, blah, blah? Which value do you wish it to be? Which value is enough cloud to say that's a cloudy pixel, not a partly cloudy or a zero cloud pixel? Why does it matter? So what does it look like on a map if you make a cloud fraction type plot, or in this case, max in column mixing ratio? On the left, I've got everything plotted from 10 to the minus 9 and higher. And the red color that is covering most of it is the 10 to the minus, 5 number there. Okay, so I'm highlighting where the really, really thin clouds are, and you can probably quickly draw your eye to Baja California and Mexico, right? Because the blue colors that show up down there are the areas where it's the in-between values. And you can clearly say it looks like a cirrus cloud, right? It looks like a jet stream cirrus. I can just look at it and say, boy, look at that streaky looking thing, southwest to northeast, looks like a jet stream cirrus. And then you can see the big cyclone in the middle of the country. And that's when I was in Rockford, Illinois, flying with the aircraft.
10 to the minus 9.
Kilogram per kilogram.
Okay.
Tiny.
Let's, if you do kilograms per meter cube, kilograms per meter cube changes.
1 order of magnitude.
So yeah,
We do that because we know that air density doesn't go above 0.1 in the troposphere. So it's 1 order of magnitude different. Okay, so how does it matter in code? Here is the Shu-Randall cloud fraction scheme in the UFS model today as we speak. That line of code near 3743 is pointed to. It says CLWT is the cloud water threshold, and it's between 1E minus 7 and 1E minus 6, because it's 1E minus 6 times the pressure divided by 1,000. So pressure of 1,000 hectopascals at the surface means that it's multiplied by 1, but pressure of 100 millibars means it's multiplied by 0.1. So it's between 10 to the minus 7 and 10 to the minus 6. There's your UFS cloud fraction scheme right there. Okay. More importantly, down here, well, I didn't put a bunch of arrows, but I've done the math on this this do loop here. And the result I'm going to tell you is there is 0 possibility of cloud fraction greater than 0 if there are no clouds modeled by the explicit scheme or the convection scheme. So if the GFDL microphysics is in FE3 today, GFS today, in about 2 years, they're switching to the Thompson scheme. I'm stunned. Probably the biggest stunner of my career is that EMC picked the Thompson scheme as a candidate like 2 years ago. And I just learned in the last year to a year and a half that all bets are in. The GFS will have the Thompson scheme in the next release of GFS, the V17. So I'm another massive surprise to me. It won't change this cloud fraction scheme, because instead of using the GFDL, it'll be the Thompson. But as long as this line is left as it is, there's no possibility of fractional clouds at what we would say is a highly moist environment in which the microphysics is not yet initiating anything because it hasn't reached saturation. Okay. Or the convective scheme, and I can't remember what they're using in that model these days, doesn't have any condensate, fake convective condensate, you could call it. Okay, so I made my own cloud fraction scheme. Like I said, I used the Sundquist scheme, but I've done a heavily modified version of that, which is shown in quickie look code here. Don't try to understand my numbers. I use back of the envelope stuff all the time. And so those crazy things in the top two lines there, RH 00, L and O, with those things that have 0.79 plus the min of 0.2 square root 1 divided by blah, blah, blah. I'm trying to put a grid spacing dependence in for the critical relative humidity for which to start my fake clouds. Okay, so I'm just mentioning that that's one of my tricks, is to try to make a grid scale dependence. I want RH critical to have to be higher in high resolution models than in low resolution models. If we're running at 20-kilometer grid spacing, our RH is going to have a harder time getting to 100% than if we're running at 5 kilometers. There's also a delta Z dependence in here, which is nice. So that's something else. It's not just grid kilometers in X, there's also a delta Z. And then all this other details here. But I do want to point out, since the last slide I had, the cloud fraction is considered 100% with greater than 0.01 grams per kilogram, or 10 to the minus 5. But it's also non-zero between 10 to the minus 5 and 10 to the minus 2 grams per kilogram. I'm mixing units. Sorry. That scales with the log 10 of mixing ratio. So all the way down to 10 to the minus 8, I am calling a cloud of some kind, but with a lesser cloud fraction. I've tuned this after GFS testing. I've sat there and played with knobs and said, this is looking the best. So I have colleagues at NOAA EMC, Anning Chang, for example, Feng Lin, boy, I always forget his last name. Help me, Louisa. Feng Lin. Sorry. Okay, didn't mean to put you on the spot. Anyway, we have great colleagues at EMC who are willing to take my changes and try to, with my changes, test it for the outgoing long wave at the top of the atmosphere, global average and tropical average, because those are their benchmarks to changing something. We have to get numbers for like 30 to 90 days to come out better, or else they don't want to talk to you anymore. So these numbers I'm playing with are for that reason, which is great to have an operational partner doing that. You want to talk about R to O, R to O to R, this is the example I can give you. And then I also have basically the fact that the way above the ocean surface, we don't care about the difference between ocean and land anymore, because it doesn't feel the effect of the ocean at 16 kilometers up or 10 kilometers up. So these tuning knobs are all over the place, I admit. And I've tuned them with WRF in order to try to get to the final answers. So maybe in the interest of time, I don't need to go over these graphics. I think what's my end time again? Oh, perfect. Okay. So I'll pretty rapidly go through this. And this is a double axis diagram here. So the grid spacing dependence is the solid lines and the axes are left and down. So if you're at 3 kilometer grid spacing and you're over the land, the RH threshold could be something like 92% before you start creating fake clouds. I'm going to keep using my digits, fake clouds. And over the ocean, it has to be much more moist. Obviously, the point there being, if you're down near the ground over an ocean, you're always humid. You don't want to make cloudy ocean everywhere. That'll really kill your radiation information. And so forth. So it has a lower RH threshold at larger grid spacings. And then the dashed curves on the right edge of it have the top and right axis. And so if we picked a point with 80% relative humidity as the trigger or whatever, then as it goes 80 to 90 to 100%, the cloud fraction goes up from 10, 20, 50, 100%. So you can see the exponential looking increase of cloud fraction at the increasing RH on the right-hand side. So I come at it with these very back of the envelopes. If you're wondering what all the numbers in those dumb equations are, they're to give me these graphs because I know in my head what I want it to look like, and I just find a function, pull a function out. I've used tan-H functions. I've used sigmoid functions. I'm a simplistic person, I say, for that stuff. And there's no good observational evidence to back this up. That's the hard part, is if I had observational evidence to back up something, I would use something better. But I'm just going to start pulling numbers until I get something that looks okay. And on the right-hand side, what's fun about this is I can take real-world soundings. This is a real-world sounding from Washington, D.C. on January 16, and I can actually use my fake cloud scheme, my cloud fraction scheme, run it through a real sounding and see what it would do. And in that case, I could compare it against real clouds as well. if we had measurements everywhere, which we don't. So in this particular sounding, I'm just showing you the example of what this cloud fraction scheme would do. It would make a water cloud in contact almost to the ground in this case. And then it would have a gap in there at, I think, what's that, 700 millibars, 700 hectopascals here. And then another water cloud through this region, which would become an ice cloud at the top part of it, because this is very close to saturation with respect to ice up here. So hopefully you get the picture. And then I can actually print the values and just, I did it here for a looky-see. And I can see how realistically I think the values of that cloud look like. So this cloud fraction scheme is doing things by layers, and it's assuming an adiabatic liquid water cloud and then an entrainment amount. So I have a high number for entrainment, 50%, because I don't want to make these too cloudy. And then after all of this fake cloud production, I make sure I'm not making it excessively cloudy by limiting the amount of integrated water and ice paths so that I don't make the atmosphere entirely too cloudy. So this is one of the ways that I've been dealing with a cloud deficit over the years. And then, of course, we compare it to radiation on the ground. On the left is the control run without my scheme. And these are USCRN, US Climate Reference Network, shortwave reaching the ground. The greatest thing about this is there's 115 sites across the US. Instead of only 7 SURFRAD sites, I can look at 116 sites to do this analysis. And you can see that most of the points are red, right? They have an excess. This is what I was saying before. We're not predicting enough clouds. On the right, with that new cloud scheme, or cloud fraction scheme, we're reducing the overall number, bias. We can look at it on individual points at every single hour. The stats are printed on the bottom there. The mean bias on the left is 107. The mean bias on the right is 70. So that's a nice reduction. Looking at it in a distribution plot, again, single case, all the other caveats. You can see here that what I like the most about that plot there, the box plot, is that the variance just lowered. So that of the errors, they've shrunk as a distribution. The errors have shrunk. So that's what we're after, in addition to better cloud forecasts. And yet we didn't solve it. We're still above. We're still high biased. I'm okay with some high biased on the USCRN network because it's a slightly, let's say, lesser maintained network, for lack of a better thought. The SURFRAD sites is only 7 sites, but they're really, really high quality data. But 7 sites across a continent of the United States is just not enough. So these sites, if they're not maintained well, literally people have to go out there and rub the dust off of the pyranometers. And if you don't get out there and rub the dust off the pyranometers, it's going to look like you have too little. So you look like you have too much. So I'm okay being above the 0 line by a certain amount, but I don't know what that amount is. And we've compared SURFRAD and USCRN side by side, and we know that there's a bias in the OBS. All right. One last touch on the verification side is this is my colleague Courtney Weeks' work in RAL. She used a machine learning technique with GOES data and created a PCA, Principal Components Analysis, for Cloud Top Phase. There's already a level 2 GOES Cloud Top Phase product, by the way. So this shows it in the middle. The left side is the image from the day. I keep bringing up the Feb 17 Rockford, Illinois day. And you see all kinds of mixture of clouds, but that great cloud over Illinois has, looks like it almost should be a flat surface of cloud. And that thing's just totally filled with liquid water. It's all below freezing. But up there in Wisconsin, you have some other cloud areas heading up toward Lake Superior that are very, what's the word? Sorry. It's not easily identifiable whether there's ice up there or a mixture of ice and water, et cetera. So with this PCA algorithm that Courtney did, she's using all 16 channels and even a couple of brightness temperature difference channels to come up with the item on the right, in which we are trying to identify, principally because of icing research, the water clouds. We want to know where those water clouds are very badly. And what's different from the GOES cloud top phase is that one, I can tell you, has been designed mostly to find the very highest cloud top type. And if it's ice and it's very thin ice, which it is up there in Wisconsin, it will diagnose it as ice because it found ice. You can ask yourself the question, how much ice is enough ice? Going back to my model world, 10 to the minus 6, 7, 8, 9, what's enough ice to call it a cloud? Well, there's no doubt in my mind that GOES is able to see through the upper level cloud down to a lower liquid cloud. And that's what Courtney's algorithm on the right is doing a little bit more of. So all of that teal color on the middle is becoming a few of those pixels, or a lot of those pixels are becoming blue, which in the right-hand case, we're calling mixed, because we're getting a mixed signal of the ice cloud, and then we're getting a liquid cloud beneath it. So we're trying to get at this thing a little bit better, because as an aviation person who cares about icing, I'm always going to look for the water cloud below. And there's some reason to consider whether that's a valuable product to other persons. I'll bet you the Air Force would say it is. You want to fly that drone around in that liquid water cloud. Super cool liquid water cloud. Okay, lastly, we can do the same thing with the model data. Most people that validate model data for cloud top, the first thing they do is say, I'm coming from the top of the model atmosphere and I'm going downward and I'm searching for a threshold mixing ratio. And as soon as I find that threshold, I'm done. I found it. So what are you going to find? You're going to find cloud ice. In far more circumstances, you're going to find cloud ice. If there's any cloud ice at all, what's the number you want to use? 10 to the minus 5, 10 to the minus 6. I can tell you what GSL uses for their cloud base height, their ceiling height. They use 10 to the minus 6 kilogram per kilogram as determining you're at cloud base. That's not a definition of a cloud base. A cloud base is a radiometer. It's an upward, it's a salometer, but it's an upward pointing near visible spectrum looking up through a cloud. Again, it doesn't detect 10 to the minus 6. It detects integrated optical quantities. So does the satellite. It detects integrated optical quantities. So why not make a cloud top phase from the model that's integrated optical properties? So you can make an integrated cloud optical depth out of the water and out of the ice and say what amount of those has to be present before you call that the cloud top. And that's what we did here on the right-hand side, the middle and the right-hand side, with different values of that cloud optical depth called tau, to say this is now fully liquid or this is fully ice. And so we have an apples to apples comparison is what I'm getting at. So for validation people in the room talking about how we're going to validate model forecasts of clouds, this to me is an important distinction. Is doing it in optical depth space, not in mixing ratio space, and stop as soon as you hit a cloud top. All right, data assimilation. I left myself 2 slides. That's all I have. So this is my newer work, and it's not very exciting yet. Trust me, I'm trying. But this is the observations, GOES 16, full disk image from last winter. And you pretty much see what you always see. It's Northern Hemisphere winter, so the convection over the Amazon and Brazil and so forth is pretty strong. But if you look at the middle panel, that's essentially the CRTM, the Commutative Radiative Transfer Model, the forward operator in the software that we call JEDI, and is the prediction, the first guess field from the model. In this case, FV3 run at C768 for all those that care. Roughly 13 kilometers horizontal spacing. And you get a pattern that's, you can clearly tell, have a reasonable representation of synoptic scale storms like this North Atlantic storm, right? With its long trailing cold front all the way down to Cuba. You can very plainly see the same thing in the model. That's good. You can see the warm frontal structure, your classic Norwegian cyclone model for mid-latitude winter. And you can see some other features here. Interesting wave off the Africa coast all the way to South America. That pretty much is shown there. The ITCZ is not shown too terribly well, because in the observations, you can pick out the ITCZ, but in the model, you can't so much, as well as the model's missing the convective cloud entirely. Now, part of this is the fact that my JEDI software that I'm using doesn't yet get the cloud from the convection scheme to put into this thing in the middle called H of X. That's the terminology for the forward operator. It's the model's prediction of the observation is called H of X. And on the right-hand side is the difference field. Well, the difference field is a little confusing here because these pure white pixels in the middle of South America are actually been disqualified by the quality control because they're so far off. The model is so different than the observations. We throw them out. So they got colored white in this diagram. They should be immensely red in this diagram to show that the observations are much colder than, the other way around, blue. So in this case, the orangey to reddish colors are cloud over forecast. I draw your attention off the coast of Chile. a little bit of over forecast of clouds in the model. Here they are, but they're low. They're near ocean surface temperature clouds, but there are too many of them in the model compared to the observations, as an example. So this is where we're headed, of course, to be able to do data assimilation in these cloudy areas to bring in the clouds better into the initial conditions. But I don't have much more other than to say all of this is now future work. We have cloud mismatches. We have to worry about correlated errors. In other words, correlated errors are when channel 13 is seeing almost the same thing as channel 14. So the errors are highly correlated. We need to account for that in the system, because there's added information knowing that they're correlated together. And then we're having some problems with solar affected channels and CRTM that I'm working with Ben Johnson on. But then a whole list of sensitivity experiments coming up. So hopefully if we do this again, I'll have more results next time. And with that, I think I should just jump to the last slide. Here's just a fake visible image, show you what we started out with a cool storm that blows up in Oklahoma. So you can make fake satellite images in visible spectrum too, which is kind of fun to watch. You see how realistic your clouds are with visible images as well. And I think with that, I have the closing slide. Is the future mostly sunny or partly cloudy? Microphysics schemes do not fix all poor cloud forecasts. Dynamics rule, baby. It's true, they do. However, microphysics matters. I'm not going to try to take that point too far because microphysics still have an impact. This SPP technique is great in multiple physical parameterizations rather than just in microphysics, is what we found out. I didn't even discuss convective parameterizations are a nightmare. Duh, convection is difficult. I hope I don't have any disagreement on that. And good DA in cloudy regions should improve the initial conditions as well as the forecasts. And with that, thank you, everybody.
Probably have time for like one question.
Great talk, Greg. Wonderful. You brought up some really good points, observational uncertainty. There is one nagging question with microphysics that I don't know if it's been solved yet or not. Whole question that came up yesterday, actually, was stratiform precipitation. Microphysics has always been underestimating that. Is there a way to fix that?
Yes, but I think it's a complex issue between the dynamics and the microphysics, because if you read Adam Clark's paper from a few years ago, the Thompson microphysics team had a better stratiform region in typical squall line situations than certainly WSM6. That just dumps it to the ground in a column. It doesn't let anything go into the anvil. I can talk way too much about that. You don't want to know all of it. But just to say that another big problem is these blobs going up in the model look like a lava lamp blob, and they need to spread out more. So the models are representing these things as very column-like updrafts when there's so much more mixing and entrainment happening, which is how you get all these cloud threads, if you will, going in all places, which give these great long trailing stratiform regions. So the size of your ice crystals matters a lot in that, and how rapidly and highly precipitation efficient your microphysics are. So if you're WSM6, you make precipitation efficiency ridiculously too high. I can prove it in many ways, and they get no anvils that go out from big convection. My scheme is at least keeping the smaller stuff and forcing it to go into the rear, which is what's giving it the stratiform region. And also the amount of conversion between snow to grapple, how fast you make that transition is a major factor, because then the grapple comes down fast. It's a high density grapple compared to a light little snowflake just drifting into the anvil region. So I think I know why, but I can't also make it any better because I've been trying and I can't seem to make it any better.
Thanks, Greg. Thanks. Our next speaker is joining us remotely, I believe. And it's either Michael Witte or Mikael Witte, depending on, so I'm going to let them tell us. And they're from NPS, which is also something that stands for something, and they can tell us. They'll be talking about constraining unified parameterizations with long-term constant cloud and turbulence observations.
Great, thank you. Michael Witte from Naval Postgraduate School. Thanks for the intro. Organizers did a great job putting these talks back to back. So I'm going to talk to you a little bit kind of more from a parameterization development side than a real forecast verification side. About work that I've been doing with some folks at UCLA on constraining these parameterizations with long-term observations, and inspired by Greg's talk. So I'll be talking a little bit about this Army and Air Observatory. Should probably have changed the title to constraining fake cloud parameterizations. So our idea here is, this idea of unifying parameterizations, I think, really gets at what Greg was talking about, where what we're interested in is, let's switch over to a laser pointer. What we're interested in is the cloud properties. That's all well and good. These are things that we need to represent in a forecast model. But a really significant component of this that I think a lot of us who maybe started out in the microphysics side have come to discover is that there's this really important interaction between what's happening with dynamics below the grid scale and what's happening with the physics below the grid scale. So this is a kind of non-exhaustive list of the things that those of us who work in this field of unifying parameterizations are thinking about. For the most part, this started in this place of looking at how dynamics cross some kind of spectrum of scales below the grid scale work together in a unified way or an internally consistent way. And now we've started expanding to get this back and forth arrow where we're bringing in the cloud information, and I see radiation as kind of the logical next step there. This is not an exhaustive list of your subgrid process of choice isn't on here. It's just because it's not in my scheme. So some examples of this, and a unified parameterization is not a one-size-fits-all thing. There is some sort of unified parameterization in almost every operational model that I'm aware of, either for NWP or climate prediction. The amount of unification varies widely. For the most part, these days, these schemes use some sort of assumed distribution to represent subgrid variability. So coming back to Greg's talk where he's talking about cloud fraction, many of those schemes that he brought up assume some sort of simple distribution, and the ones that we had available in the 90s weren't very good because the assumptions were so simple. So I'm going to kind of go the other way from Greg's pure simplicity approach to talk about something that's a little bit more complex. Some examples of what we might see in operational models, on the NWP side, pretty much everyone now uses an eddy diffusivity mass flux framework for PBL turbulence. At NCAR in particular, you have a different approach that's using some of the other US Earth system models where you're assuming something like a double Gaussian. So we've got here on the bottom figures, we've got some joint histograms here on the left two, showing how you can make some assumption about how the variability follows some sort of double Gaussian distribution. And that's being compared with an aircraft transect of a shallow cumulus cloud that has this very skewed distribution in terms of both vertical velocity as well as thermodynamic quantities. You see this both in total water mix ratio and the water potential temperature. You've got this long tail, and we can just drop a saturation line across here where everything moister and cooler in this PDF is in the cloudy side of things. And this is really what we're trying to get at, right? But what you can see even from this figure is that the choice of PDF can really impact what this cloudy area that you diagnose is. And so this is kind of what I'm going to be trying to get at, is what we can learn about subgrid variability in dynamics, turbulence, and turbulently set variability in thermodynamics that leads to clouds formation, and we'll see how we can do with that. So on the operational side, I'm really going to focus on EDMF. Operational models are not that useful to me in this sense because really all we get is the dynamic side of things, where we can break down what an EDMF does into just a scheme that's being used for predicting fluxes, where we break it down into some contribution from what we call local mixing or turbulence, which is often parameterized through an eddy diffusivity type parameterization, where we're just getting something from a TKE, turbulent kinetic energy, defining this diffusivity and then applying that to the mean field gradient. Then the convective side of this is a traditional plume updraft model where we've got some number of discrete plumes. We model their velocity and then they're transporting some sort of perturbation thermodynamic value upward. But here we've got only turbulence and dry convection and operational models. I'm not sure if there's any that really get into moist convection at all. So then you hand off to your convection scheme and that's that. What I'm going to talk about is more of a development type model with some folks I work with at Jet Propulsion Laboratory in UCLA, where now we've not only got dry updrafts and some local turbulence contributing to mixing, but we've also now got some of the moist processes. So we allow these updrafts to condense if they reach the point of saturation. In the environment now, we can form stratiform precipitation by looking at our assumed distributions of saturation excess, which comes out of that joint histogram of temperature and moisture, as well as some assumed distribution of rainwater. And from this, now we can construct this kind of grid mean precipitation rate just using what we've got with our internally consistent subgrid assumptions about how the environment and convective updrafts are distributed. So there's a lot going on in this model. I don't have time to get into the details of it, but happy to follow up with anyone about what we've been working on. So from the development side of things, often what we'll do is we'll be taking some sort of LES, large eddy simulation output, which gives us a three-dimensional diagnosis of turbulence. We can pick out coherent objects. We can play all these great games. Then we can go and compare with what we get out of the model. Usually in the development world, we do this in a single column model to make things easy. And we can end up with some results like this, right? So here I'm on the left figures, I'm showing some plots of the joint PDF of a large eddy simulation, which are the gray contours. This outer contour corresponds to about 3.5% of the data. Inner contour, you can't really see, is 70%. So we got the LES in gray, joint PDF from what we're calling here kind of the ED scheme, but really it's this binormal in black. And then over here now we've added some mass flux plumes in, and you can see that these mass flux plumes are huge for giving you that skewed part of the distribution. Great, we're doing a lot better than this binormal thing by itself. All well and good. We can do the same thing looking at time height curves of cloud cover, where we're looking at the LES versus whatever flavor of parameterization we've put together. And that's fantastic, but we're comparing with these hyper-idealized cases. This is a horrible thing to do if you're trying to tune a model to work over the whole globe, which is why so many of you do this with satellite constraints. But we're missing a lot by comparing with these hyper-idealized cases. So it's more preferable to do this with respect to observations. I'm just going to show this one example here from Algerman Forbes, where they were using some data from an observational site to evaluate low cloud representation in IFS. They really just focused on cloud cover and radiation properties because of the retrievals they had available to them. But they made some small changes to the model in terms of the microphysics and cumulus triggering that reduced radiation biases in the 3D model. Okay, that's great. But I'd like to move from just focusing on the radiative properties of clouds to now thinking about coupling between the dynamics and microphysics. So what we're going to do is use some observations from ARM's Eastern North Atlantic Observatory. I was showing you kind of the zoom out of the island on the first slide. This is a site that's been around for about 10 years on Graciosa Island. I'm going to be focusing on a very small subset of the observations here. So zenith pointing observations from Doppler LiDAR and radar, Ka band, and then we'll get some integrated moisture information from microwave radiometer. So then what we work with in terms of retrieved variables, it's more like radar reflectivity, retrieval fraction, vertical velocity is the big one, right? This brings the dynamics in, it's integrated water paths. Look at this over 2 years. We've got about 2,400 hours of PBL cloud observations. We'll take these. This is now just looking at some curtains of radar reflectivity and vertical velocity. And we're going to work on 3-hour time spans that we'll average over with a mean boundary layer wind speed of about order 10 meters per second. We've got a 100-kilometer fetch. So very relevant for climate model scales, maybe a little bit coarse for NWP. But we need a starting point, and this gives us enough averaging to do some statistics. We can come up with something like this then, where I'm just showing you profiles of vertical velocity variance and third moment of vertical velocity. Breaking this down into 3 categories: coupled stratocumulus, decoupled stratocumulus, and shallow Q. Avoiding everything with ice, which most of us probably don't like, but gotta start somewhere. And combining the LiDAR and radar vertical velocity retrievals would come up with these beautiful profiles that look very similar to what you'd expect from one of these hyper idealized LES. So if we composite a bunch, we can kind of pull out that picture that looks very similar to what we might see from a 3D dynamic model. This is just to show you that we can take this retrieval fraction where we're just looking at the basically the max, kind of a max overlap assumption applied to the retrieval fraction at every level or at every range gate from the radar. This is pretty good, especially when we're looking at the low cloud cases here, where you get poor agreement. It's typically when there's a lot of high cloud, some cirrus passing over, where the coverage might be very much defined by some larger scale stuff. And so now we're going to take these observations, compare them with a single column model, blow through this. Again, I'm not going to talk about how the model is set up, except to say that we've got dynamics, macrophysics, microphysics in the EDMF parameterization, and we're coupling to a radiation code, just so we can have that kind of close to a full physics setup, even though this is a very idealized development framework. And we'll compare with these 800 to 3-hour periods that we've identified subjectively. We're working on doing this objectively, but again, I have to start somewhere, and we'll compare with the observations. So all I'm doing here is taking reanalysis, forcing, running the single column model, freestanding, running for 3 hours, and we're saying, how does it look compared to the observations? So let's start with some turbulence results. So here I've got that same observed profile for variance, that same observed profile for third moment. And now let's see what the model does. We're not doing perfect. There are some things I'd like to point out that we're doing pretty well at. For one, kind of the shape of the cumulus profile is pretty close. We miss that topmost bit of things because we start to lose retrievals higher up we go. We're really just relying on a couple of in-cloud Doppler radar retrievals in cumulus cases, whereas for stratocumulus, we've really got that full view of things. You've got a nice layer cloud. But cumulus case shape is good. In our stratocumulus cases, we've got this anomalous, low turbulence down here just below the subcloud layer. It's because we start to get a little bit more stable, so we lose that ED transport. But overall, I'm not too concerned about this because we look at the scale of these two things. The simulated turbulence is about a factor of 3 too strong in terms of peak magnitude. So that's a big issue for us that I think is really a tuning thing. So that's kind of what we're looking at yet. I just wanted to get that full set of 800 simulations to start with. On the skewness side of things, you'll notice that in our model, everything is positive. Everything is positive because we've assumed that our turbulent environment is Gaussian, so no skewness there. And then we've only got updrafts in the model, so the only thing we can have is positive skewness. This is fine for decoupled stratocumulus and cumulus, which are really going to be dominated by surface force updrafts. But in coupled stratocumulus, where we've got much more generation of buoyancy reversal at cloud top, now we're kind of in a downdraft dominated area. So this is a big area for model development that we've identified. Going from the turbulence, now let's look at cloudiness. Here I'm showing you joint histograms of cloud cover on the x-axis and liquid water path on the y. For all of these cases, you see kind of the same patterns. So for coupled stratocumulus, decoupled, and shallow Q, we're doing pretty well in terms of cloud cover. but we tend to massively overpredict liquid water path. So you can see these are pretty coarse bins. These are 100 grams per meter squared. So we've got way too much liquid water in here, and the problem gets worse and worse as we go to more of a shallow convective situation. So this is definitely something we need to take care of. I think this is tied to having too much variance, because the variance that we get in the dynamics sets the variance we get in the thermodynamics, and then that's setting the stage for this joint PDF where we're trying to say, just cut this off at the saturated line, and everything that's saturated we call cloud fraction. We can get into the issues of that definition another time. Last thing I want to show is some results from the microphysics dynamics coupling, where now I've taken each of these cloud categories and broken them down by precipitation state. So non-precipitating, virga, or surface drizzle. And what we can see here now, if we're comparing observed and simulated subcloud variance, is that there's only one regime, this decoupled stratocumulus regime, where we're getting the right correlation, where subcloud variance increases with the amount of drizzle that we see in the atmosphere. Whereas the other two cloud types have differing, or kind of the wrong relationship between the model and the observations. And our first thought is that this is tied also to this lack of downdrafts, and in particular, lack of cold pool representation. So like Greg was talking about, you get these evaporatively forced downdrafts that then can induce further updrafts by collisions. So this is a tricky thing to do in a subgrid scheme, but it's a focus of our ongoing work. So that's all I've got for some preliminary results. One of the big things that we'd love to do going forward is to get actually retrievals of the turbulent fluxes. This is really the fundamental thing that these schemes are predicting, usually using a combination of Doppler LiDAR for the dynamics and Raman LiDAR for water vapor mixing ratio, for example. But I'm not sure how generalizable these retrievals are. This is data from the arm of the Oklahoma site, SGP, and they only did this on non-precipitating shallow cumulus. So I don't know if we can do this in rain, if we do this in the full spectrum of boundary layer cloud conditions that we see in the real world. And I also wonder if this can be extended to do sensible heat, since you can also get temperature usually from the Raman LiDAR. So this is something that we're working on getting into the mix of things to kind of build into our framework. All right, so I'm running short on time, so I'll give you a quick summary. We've got this model that predicts turbulence intensity as well as cloud properties, because these are things are really intimately coupled at the process level. We find that we over-predict turbulence intensity in the cloud layer, under-predict it in the subcloud layer. Somewhat of a tuning issue, somewhat of a missing physics issue. We do all right with cloud cover, but we massively over-predict liquid water path, probably because we're producing too much turbulence. Looking forward, we think that missing skewness and some of this underprediction of subcloud variance is caused by a lack of downdraft and poor coupling between the microphysics and dynamics. I like to say that most of this work has really been wrangling observations. We're just getting started on evaluating EMF with it. But you could do this, take this framework and apply it to any model output. So this is most easily done with a single column model. We could just as easily do this with 3D column output if you just want to pick out a specific location. So I'll leave it there and hopefully can answer a couple questions. Thanks so much.
Thanks, Michael. We started about a minute late, so if there's a good question, if not, maybe offline, can talk to Michael. So thanks again, Michael. Go ahead. So our next speaker is also from the Naval Postgraduate School, and it's Scott Powell, and we'll be talking about understanding fundamental dynamics in humans. So go ahead, Scott.
All right, thanks. All right, so I'm going to kind of keep with this theme of talking about cloud dynamics here in this session. And specifically here, I'm going to be thinking more about the cumulus and cumulonimbus clouds and that transition between the two states. And as Greg said, microphysics are very important, but dynamics are really fundamental and key. You got to get the right dynamics before you can have the cloud express the right morphology for the microphysics to be right in the first place. So I'm going to be asking a couple of questions here. One, what controls the transition of clouds from shallow to deep? And then at a more granular scale, in a population of shallow convection, what controls which among them ultimately grows deep? All right, so I like to start off with some sort of satellite imagery just to demonstrate what the complexity of real cloud populations look like. This is a Himawari image from the West Pacific taken a few months ago. And you can see lots of different types of clouds in here. You can see cirrus clouds, cumulonimbus clouds, some shallow cumulus clouds. Some of them are organized, some of them are isolated. I'm just going to zoom in on a box right here. And we can see things a little bit more up close. And I'll put this in motion. And this will just loop through a few times as I talk. And you can kind of look at this and listen at the same time. This is a realistic cloud scene. It's very complicated, right? Our goal is to try to model this. We have cumulus clouds that are rooted in the boundary layer. Some of them grow deep, some of them don't. The ones that do grow deep contribute to the expansion of these cirrus clouds in the upper troposphere. These have radiative impacts at local and up to large scales. And we're trying to capture all of this type of process that's happening on relatively small scales with these numerical prediction systems that have grid spacings that look kind of like the black checkerboard that I've got in the background there, right? So this is like roughly like a half-degree grid that I've got outlined here. And you can see that all the processes that are happening at the cloud scale are, of course, much smaller than the grid spacing, which just kind of highlights the importance of cumulus parameterization in our numerical weather prediction systems. We need those, as well as the microphysics, to be as close to truth as possible in order to really have a hope at predicting where all of these different clouds are occurring and when they're occurring. So I'm going to focus, like I said, on dynamic processes in clouds and motivate this by stating maybe the obvious is that a lot of what I just showed you is dependent upon cumulus parameterization, but many of the assumptions in various different cumulus parameterizations are questionable, to say the least. Assumptions about the vertical mass flux, about the life cycle of convection, about organization of convection, clustering, all of these things are not necessarily well handled. And in this talk, I'm not going to be able to cover all of them. But like I said, I'm going to be focusing on the growth mechanisms of shallow convection into deep convection. What causes that to happen, when and where? Just to kind of illustrate the problem here, this figure that you see here on the left is from a paper that John Peters did. I was on a few years ago. And what we're looking at is a metric of vertical mass flux in cumulus clouds. The red line here represents the mass flux that you would get in a parameterization. This is a Zhang-McFarlane parameterization, just as an example. And you see kind of this peak up here close to in what would be in the tropics around the 0 degree sea level, around the freezing or melting level. And this dashed black line is what we got as the vertical mass flux in convection when we modeled a isolated convection population in LES. This blue line is, I'm not going to have time to go into details about this in this talk, but this blue line is a revised treatment of the mass flux in his map scheme that also handles where detrainment occurs and has a size dependence of entrainment and mass flux on the cloud. Yeah, on the cloud entrainment and the mass flux is a size dependence. One reason this might be important is for prediction of things like the Madden-Julian oscillation. So over here on the right, this is actually a figure that I had in my proposal for NOAA's CVV project that's underway now. And on the left of this little figure here is what might happen in a traditional cumulus parameterization if the mass flux is, or if the detrainment, is too bottom heavy. So this red line here is supposed to be kind of the entrainment profile that might result from having a mass flux profile like the red line on the left. And what you tend to get is anvils that develop too low. So you have long wave warming down here on a deep layer of long wave cooling aloft. If you get the detrainment closer to the equilibrium level up high, you tend to have long wave warming through a deeper layer of the troposphere. And without getting into much detail, this is really important for the fundamental dynamics of large scale features in the tropics, such as the Madden-Julian oscillation, including its maintenance and its propagation. So getting these types of things right in cumulus parameterization could have not just impacts on what's happening at the cloud scale, but downstream impacts to large scale phenomena as well. So I'm going to ask the question, what actually forces convection to deepen? And when I say the word force, I mean it quite literally, like F equals ma. And typically when I have a longer talk, I flesh this out a little bit more, but I'm throwing everything up here in one slide. What we see up here, the top equation is a sort of a truncated, simplified version of the vertical momentum equation with just two terms on the right. The B is our Archimedean buoyancy, which is what I'm highlighting over here. This is the rightmost equation. And when a lot of people say buoyancy, this is what they're thinking about. They're thinking about the thermodynamic component with the temperature, the humidity, and then hydrometeor loading. But one issue with just thinking about buoyancy by itself is that you had to define a reference state. Like this theta naught is some reference potential temperature. The QV star represents a difference from some reference humidity. The issue with that is, how do you define what the reference state is? Is it 5 kilometers surrounding a cloud in the environment? Is it 10 kilometers, 100 kilometers? Is it the nearest sounding? The point is that it's arbitrary. So just calculating the buoyancy by itself is, this Archimedean term is not all that meaningful. So we have this other term here, which is a vertical pressure gradient acceleration, and that can be decomposed into two components. One is a dynamic pressure gradient acceleration. One is associated with the buoyancy perturbation pressure. And actually, when you add up these two terms that are not in the yellow box over here on the right-hand side, you get something that we call the effective buoyancy. And these two terms are generally mostly offset each other. Both of them are dependent upon the base state, or the choice for the base state, but when added together, that arbitrariness essentially cancels out and you get something that's more quantitatively meaningful. And then finally on the left is the total acceleration in the Lagrangian sense, the dWdt. And what I've got plotted down here on the right, bottom right, is from a model simulation I ran a couple years ago, where we're looking at the model domain mean rain rate on the y-axis versus that dWdt on the x-axis. And you can see that for certain values of the acceleration, you basically get no rain. And only when that acceleration reaches a certain value, which happens to be a little bit above 0.004 meters per second squared for this particular simulation in this environment, you start getting this kind of quasi-linear increase in rain rate as the acceleration begins to increase. So it tells us that there's a strong sensitivity to precipitation, at least in a model, to what is happening dynamically inside the clouds. So key question I'm asking here is also not just what controls when a population of clouds transitions from shallow to deep, but among those clouds, which ones can you locate this cloud versus that cloud versus this other cloud over here are going to grow? And the basic hypothesis here is, say you have a shallow cloud here, that's the left cloud on this image. There's two potential ways that it could grow into a deep cloud. And those two potential ways are shown as the two deep clouds over here. The red arrows denote the vertical velocity. So in this shallow cloud, we've got some cloud-based vertical velocity. The purple arrows an acceleration that the cloud experiences after it leaves the boundary layer. So a downward acceleration causes the vertical velocity to be reduced. In this example, we increase the acceleration, or in other words, we decrease the downward acceleration, and that allows the cloud to get deeper because it slows down less quickly. Or we could juice up the cloud-based vertical velocity with the same downward acceleration, and that would allow it to get deep. So we're going to take a look at this. Is it something about the cloud base that's changing, or is it the features in the middle of the cloud, the reduction of the downward acceleration that's changing that allows it to deepen? Now, we're taking a look at this right now just in LES. This is just an animation of what cloud population looks like. This is a tropical marine simulation of isolated convective clouds that ultimately end up organizing by the end of the simulation. These are just some model specs. I won't belabor this much, but we're running at 100-meter grid spacing with a reasonably large size domain, 64 by 64 kilometers, time step every second. You can see the convection kind of organizing in the background there by the end of the simulation. Periodic boundary conditions, of course, so that has some impact on things I'll talk about in a little bit. This is the bottom part of the sounding that we used, or I guess I used for the simulation. Red's temperature, green's dew point. This is just to kind of show you where the LCL and the LFC are. LCL is, a little bit above 500 meters. LFC is closer to about 1,000 meters. Pretty typical for Indo-Pacific tropical regions over the ocean. Interesting thing about this particular model simulation, though, is that we've initialized parcel trajectories. And by the way, this is all in Cloud Model 1, George Bryan's model, CM1. We've initialized parcel trajectories at every grid cell below 1,000 meters. So we have over 10 million different parcel trajectories that we're going to analyze. And the reason that this is important is that we can essentially follow these parcel trajectories from the boundary layer up into the clouds and into the upper troposphere. And that is going to keep track of the properties of the cloud as, following fluid, essentially, in a Lagrangian sense, as it moves through the cloud. And what we're going to end up doing is comparing the ones that ended up getting deep, the parcels that ended up getting deep versus the ones that didn't. And that's my definition down here, the red versus blue, the growers versus the non-growers. The growers are going to refer to those parcel trajectories that got to at least 6,000 meters. The non-growers, they started to get into grow in a cloud, but they stopped between 1,500 and 3,000. So in the next few slides, the red's always going to be for the deepening parcels, and the blue's going to be for the non-deepening ones. And we've got some passive tracers in here too. There'll be one slide that shows the difference in dilution between growers and non-growers. This is just an animation of the same simulation, but each dot is a different parcel trajectory. Early in the simulation, you see a lot of blue dots, and here we see some red dots in the background. We see some growers start to pop up. So we're going to be separately essentially analyzing the red dots versus the blue dots to see if at the low part of the cloud, there's some difference that we can see between the ones that end up growing and the ones that don't. And so I'm going to show you a few different slides that look like this here in the next few minutes, just to kind of compare these. So again, red is growers, blue is non-growers. And in particular, I'm going to focus kind of below this 1.5 here, that's 1,500 meters. Vertical velocity, roughly the same. The shading is a 95% confidence interval, by the way, of the median. Effective buoyancy, again, roughly the same. Different above that. And we'll look into why that might be the case. That dynamic pressure gradient acceleration term is not really any different. Hydrometeor loading, okay, we've got more hydrometeor loading in the deepening convection. That's going to be offset by some thermodynamic term that's not plotted here to give you this effective buoyancy. But down low, it's roughly the same. What is different, though, is the size of the clouds that grow, or the size of the clouds containing the parcels that grow versus the ones that do not. This is the area of the updraft containing the parcels. The middle is the area of the cloud, and you can see that the red, there's no overlap between the red and the blue at any height. The clouds and the updrafts that end up deepening, they start out wider to begin with. And that's kind of the key point of this talk and from this slide in particular. Now this, I said I had passive tracers in my LES. This is just looking at the passive tracer value as a function of height. And again, we see that if we look at the red line here, the red line decreases less with height than the blue line. Well, what does this mean? It means that the growers here are being diluted through the process of entrainment less than non-growers. The wider clouds are being diluted less. No surprise there. It makes sense, but this is just kind of confirmation of that hypothesis. And another interesting thing is that we can look at the temperature of the parcel and the specific humidity of the parcel relative to the non-cloudy background surrounding the cloud that the parcel's in. And at low levels, the temperature is roughly the same. So it's not like these parcels are warmer than the non-grower parcels, and that's why they grow deep. There may, however, be the possibility that they're growing in slightly moist environments. So the fact that this red area here is less than the blue area below 1.5 kilometers, that means that the parcel relative humidity and the background humidity of the environment are closer together. Since the parcel's in a cloud, it's saturated. So that means that the background humidity is actually a little bit higher. Whether that's because of some sort of, preconditioning by previous cloud or some other, or just, random process, unclear. But it does appear that the growers that are wider do tend to occur in slightly moisture backgrounds. And so the basic idea here is that, narrow cloud tends to be more diluted, while the wider cloud is more protected from the environmental air and is able to grow deeper. Really quick here, just left versus right, growers on the left, non-growers on the right. These are kind of vertical profiles of different slices where the black line represents the outline of a cloud. This is in composite form. I'll just show you the top right here. The blue shading is the vertical velocity. You can see that the growers here is just another way of seeing how much bigger the growers are than the non-growers, and that the vertical velocities are significantly stronger once you get above kind of this 1,500 meter level. And then the last thing here is the last couple things here, and then I'll wrap up is, we also investigated the difference between growers and non-growers before they even got into a cloud, when they were in the boundary layer. And so you see here on the y-axis, so the heights only go up to 600 meters. And basically each one of these plots is exactly the same, except for the bottom left, which is the area of the updraft containing the parcel. So even before these parcels rise above the LCL and form clouds, the ones that end up growing tend to be contained within these subcloud eddies that are wider than the ones that don't grow. I don't have time to show this and explain this right now. The point basically is that sometimes growers will sit in not wide convection for a long time before they actually grow, maybe even up to an hour at some point in some cases. They only grow deep once they get to within convection that is a certain size. And in our simulation, that size is about half a square kilometer. However, that's not a one size fits all value. It may vary depending on the particular environment. And the last limitation here, and this is the last slide here, is that one issue is that the temperature perturbations in the boundary layer for the model do not match what you get in observations. This graph over here is just a bar chart showing the temperature distributions at 300 meters in the model, and you see that it only ranges within about a half a degree Celsius. And most of the values are within just a quarter degree Celsius. Over here on the right is just a random sample of aircraft data through a similar tropical marine boundary layer. And you can see just within a few minutes how you get much larger temperature variations. Part of this has to do with the periodic boundary conditions and the fixed SST that's homogeneous everywhere. It's one caveat. We're finding that there's no thermodynamic difference between growing and non-growing parcels near cloud base. But we're doing that in a model that doesn't really have proper representation of boundary layer heterogeneity. And that's something that we need to really pay close attention to in the future moving forward, I think. Throwing the conclusions up here, gather there's no time for questions, but thanks for your attention.
Right, thanks. I'm grateful for the opportunity to speak to everybody this morning. The lineup of talks has really been great. I think really well put together. I am going to talk about boundary layer cloud with synoptic systems, particularly in the marine environment. First, I'd like to acknowledge my co-authors, Jordan Eissner, who's a PhD student. Raise your hand, Jordan, PhD candidate working on this project. She's done all the heavy lifting with the modeling and the analysis. I'm Dave Mechem. Also like to acknowledge Virender Gate, who's been supplying a lot of the, at Argonne National Lab, been supplying a lot of the retrievals. And I'd also like to, from NRL, acknowledge Yoo-Jeong for helping out, for her heroic patience and helping out with I'd like to frame this first by just by talking a little bit about marine low clouds. And marine low clouds are very important to this crowd, certainly for marine and aviation operations. And probably somebody may have their mic on. Hot mic alerts, please mute. Exactly. I withdraw that statement. I'm sorry. What we've learned generally about marine low clouds has been in the context of sort of subtropical coast, off the coast, subtropical marine locations. So these are regions characterized by large scale subsidence, to a great degree horizontal homogeneity, and in many cases kind of fairly thermodynamically simple barotropic type systems. When we do that, this has been kind of the topic of investigation in many field campaigns and modeling exercises. There's sort of two themes of approaches that come out of that to explain sort of model or to explain sort of cloud evolution. One is sort of more of an entrainment based idea of this warming deepening mechanism from Wyant and Bretherton. And then there are some cloud breakup explanations associated with the precipitation and aerosol precipitation feedbacks, okay? So when we look though more deeply, these clouds aren't just associated, we don't find these clouds only in subtropical barotropic systems, okay? We find them all over the place in synoptic systems too. So if we look at a composite here of clouds, okay, we see oftentimes, if this is going through, oftentimes stratocumulus behind the low, sort of in the cold sector. We see also cumulus in the cold sector behind the cold front, and also in the warm sector too. And if you look at this sort of nice conceptual model of a synoptic system, the boundary layer structure is highly complicated, to put it mildly. And then we've done a couple studies. These aren't in the marine environments, but these are over the continent, looking at boundary layer clouds associated with synoptic systems. So both as kind of a traditional post-frontal, sort of cold, sort of after the cold front stratocumulus case, and then a case during MC3E of transition from cumulus to precipitating congestus clouds. Okay, so this sets up our sort of issues here. In short, we understand marine low cloudiness to a pretty solid degree in marine barotropic environments. We don't really have a good conceptual model of synoptically influenced boundary layer clouds, though, associated with synoptic systems. And we also don't really have a great handle on how well or how poorly our mesoscale and NWP models handle them. So our goal for this project has been to basically take what we know from these clouds and from previous studies in barotropic subtropical systems and apply that to synoptic settings, okay? And to do this, as part of this, we've developed a synoptic relative kind of analysis framework. And ultimately, the idea here is it's always to improve forecasts, okay? So ultimately here is to be able to better evaluate and improve model parameterizations, particularly the boundary layer schemes and the microphysical schemes. So to do this, we're using COAMPS in a pretty vanilla configuration, okay? I mean, as researchers, we may want to always like crank the resolution up as high as we can do it, but we're trying to maintain some some operational relevance to what we're doing. So we're doing basically a doubly nested COAMPS simulation, set of simulations, 9 kilometer and 3 kilometers. This is over the Eastern North Atlantic. So others have also kind of shown that they've used some of these observations at the DOE Graciosa site. That's where we've got this fine mesh domain centered on as well. We do kind of crank up the vertical, the resolution in the boundary layer. We like 20 to 80 meters of grid spacing in the boundary layer. We try to not go too much coarser than that. In that we also do LES work, and oftentimes LES we want the grid spacing about 5 meters. I mean, I know that's not something we can do in NWP. So this is though a fairly vanilla off-the-shelf COAMPS sort of COAMPS configuration. We're using single moment microphysics, but with a kind of the stock scheme, and then a Krudinoff-Kogan 2000 non-interactive, sort of I'm calling it KK 2000 light scheme with their auto conversion and accretion. So here's this example here of a frontal passage. I'm gonna keep your eye on it. Here's comes the front right there, passing through the Azores, and then this high pressure system kind of drifting to the east. And just the point here is if you've sort of grown up like I have looking at subtropical stratocumulus and the sort of like these huge sheets, this is much more synoptically active. Okay, you can see there's fronts, cold fronts, there's the low, there's deformation zones. It's kind of crazy. So this is what we're after, is trying to see how the models are performing here. I know there's some mention of aerosol. We're also interested in aerosol too. That's less a part of this project, but it's something that we're considering. And so we kind of look at aerosol too. We're picking periods to do our simulations in that coincide with the ACNA field campaign that was done a couple years ago. So there's extra soundings, and there's also aircraft flights. So we'll be able to, we haven't used the aircraft a lot in this study, but those are available when we if we decide to use them. Okay, so we've chosen 7 case study periods, sort of 3 in the winter, which, you could imagine the winter is going to be highly synoptically active, 4 in the summer. Even in the summer, even though this is Eastern North Atlantic, is thought of as a kind of boundary layer cloud regime, even in the summer, the clouds are synoptically influenced. Okay, a lot of times cloud bands are associated with these kind of dead, decaying fronts that kind of sag over the region. This is again kind of what we're after. So the first thing we can do is point by point comparisons. Okay, that's what anybody would sort of start to do. By and large, if we look at potential temperature, and this is sort of at the Azores, sort of potential temperature down near the surface, 500 millibar heights, and wind direction on the bottom. As far as the meteorology goes, the model is doing quite well. I'd characterize it as doing quite well. Liquid water path. So liquid water path is a vertically integrated liquid water, column liquid water, grams per square meter here. It's struggling, okay? Too little condensate. I actually think we have this PBL height. I think it's actually doing a better job than we're showing here. Having models give PBLs that are PBL height, don't get us started. Quantifying PBL height from model output is a challenge, and there's multiple ways to do this. Okay, so we can also do point by point comparisons with the soundings. Okay, I would say especially after the cold frontal passage is kind of earlier in this period. We have time going from left to right, and then kind of wrapping around to get on the bottom. So the black lines are the SONs, the radio SONs from Graciosa Island. The green lines are coamps. And I would characterize this as, we have formal sort of metrics also, but characterize this, especially kind of later in the period, as not doing too bad. I've seen models do great violence to the boundary layer structure. So this is actually, I think, doing fairly well. You can see the inversion structure is a little mushy in the model, but that's because we are only crudely resolving it. So we're not too displeased with that. And then what we've got when we plot it like this, we can plot it sort of as these sort of light boundaries, or this light sage green that basically represents COAMPS cloud boundaries. The observed cloud boundaries are in gray, and then the darker ones are where they overlap. Okay, and so it's in the ballpark much of the time, getting the cloud structure right, even if the total condensate isn't so great. Oh, what? Say that again.
The cloud boundary in the model.
So typically, we're using 0.01 gram per kilogram, so threshold, to follow on Greg's talk, right? No ice, we have it easy. Yes.
Because it went to rain from Kordoff and Kogan auto conversion.
I'll show that a little bit. I think there's a little bit of drizzle here. In fact, more than I think there should be. So this is, we're doing liquid water path, or doing the PDFs over basically a 150 by 150 square kilometer layer here. One of the things we see is that this is with the stock microphysics. One of the things we see is the model seems to not be really picking up on the kind of juicy stratocumulus part that we would ideally like it to. And it's actually overdoing the rain, even with the stock microphysics. It's not doing, I mean, you may disagree just aesthetically here, but it's not doing a terrible job on getting the cloud base and the cloud top. Okay. And this is when we add the Krudenhoff and Kogan light. We still have the same problem though. It's still raining out too much. In the past though, we've done a lot of work in barotropic systems. Typically changing over to KK 2000 really helps things, has been my experience. But here it seems to not be helping a lot yet. Okay, so this is talking about here our system relative framework instead of just doing it sort of point by point comparisons. What we use is the Naud et al. Frontal identification algorithm applied to COAMPS output. So here's an example of this is just plotting it with over the Era 5 domain. We can also see just the COAMPS and the Era 5 surface pressure lines, at least sort of passes the eyeball test. So we pick the blue here as our cold front. We draw a line normal to the cold front. Is it coming up? There we go. Wow, lagged correlation there. And then we can draw analysis volumes, okay? And there's some, this is not fully automated yet. There's definitely some human art to this. Thank you. And we can then sort of do the analysis here. So look at cross sections. These are composites of about 8 different cross sections. It looks good. We have subsidence, okay, behind the cold front, and we have nice sort of post-frontal and prefrontal thermal structures, just as we'd expect. We can sort of slice and dice this with liquid water path, with surface fluxes of heat and sensible and latent heat flux, and the boundary layer height and stability. Ultimately, scientifically, what we're after here is an improved or a conceptual model here of this transition. We can also slice and dice these clouds by region, sort of in parameter space instead. So we have stability on the x-axis, we have vertical motion on the y-axis. When we do this, we get this just kind of nice, the clouds just kind of fall into basically a prefrontal cumulus, forced frontal convection, and then post-frontal, where it's more strongly stable, cumulus and stratocumulus. Okay, so we can look at these things not just spatially, temporally, sorry about that, but in parameter space too. And then finally, we can make sort of like whisker plots, okay, and compare observations of the distribution in the model against observations. Again, this kind of is showing how we're struggling with liquid water path. The boundary layer height is kind of wishy-washy. Stability, it's doing a good job in stability. That's basically the background meteorological state. And the latent and sensible heat fluxes, don't pay any attention to these observed dashed values. These are out on the model, or these are on the island itself, so not representative of the open ocean. We're still begging to put a buoy out there, okay? And so that's kind of where we're at. So just wrapping things up, this compositing in the context of synoptic system structures provides a really nice pathway to evaluate cloudiness forecasts that kind of are immune to phase error, like forecast phase errors. Okay, because ultimately, kind of what we're after is structural model uncertainties and trying to improve those. Kind of just the quick conclusions. COAMPS seems to be doing a pretty good job on the meteorology, a less good job on the cloud properties, especially compared to our previously, we felt like we had it going pretty well in the subtropics, okay? We've tried to kind of maintain this balance of resolution versus operational dependence. And here's the one thing, before, when we were just working in the subtropics, we could have this narrow-minded view of we're trying to improve stratocumulus, warm rain stratocumulus. Here, when we're dealing with synoptic systems, we have to consider ice. I mean, we have whatever improvements we make still will have to play nicely with the ice phase schemes and all of the rest of what's going on in the synoptic system. Okay, so I will, if there's any time for questions, I'll be happy to address.
Probably have time for a couple of questions. Well, as I'm glad to say, is you using the ACE ENA dataset or somebody else use Eissner's data. Actually, I'm one of the co-PI for this field campaign. Sure. It's my group is provide all the retrieval for cloud, marine boundary cloud, and also drizzle property, and we'll also analyze air path data. But what's the one problem we found during the winter field campaign is a sub-layer cloud, is below the cloud layer, is CCN concentration even lower than cloud number concentration. That's a problem we still cannot figure out what's the problem. Is it due to the precipitation washout or something else? That's the problem, is when you're using the, the sub-layer cloud is, CCN is a simulated cloud.
Yeah.
When the summer is okay, and also is the summer, they are dominated by the sinking motion, and the winter dominated by the upward motion. So that's a scenario pattern is different over there.
There is, it's wildly variable, and,
Right.
and that's why it's so different than the kind of typical barotropic kind of environment. I do have a separate project looking at cloud CCN processing, but that's sort of beyond the scope of single moment microphysics.
Any other questions? Yeah, right. Oh, sorry. So pointed way in the back, sort of like, for the model setup, the 9 kilometer, the outer grid there, did you have the cloud microphysics schema active at that point, or were you still using the parameterizations?
I had both. So I had, you mean like the cumulus parameterization? Yeah, that was on, and it's doing the explicit microphysics too. At 3, we turn the cumulus off.
Yeah.
Sorry, thanks for muting me. Dave, great talk. One comment, one question. The comment is that I think that was Shichuan who was asking about CCN being lower than cloud concentrations. I have a feeling that's because of the free tropospheric source that Rob Wood and his group have been investigating. I'm guessing you're kind of going along that same track.
So in just that there's sort of nucleation of those entrained particles or activation with entrained particles. Okay.
Yeah, so there's that. And then the other question was just, so you mentioned, yes, you have to deal with ice processes once you're starting to look at these frontal systems. And have you considered trying to just do more of like a Lagrangian? I guess this is hard with coamps just because the framework isn't really set up for it. But it seems to me like you could get around some of those complications of mixed phase clouds if you could just track maybe a post-frontal 5 or 10 kilometer or smaller domain. But I think for what you're doing, it's without going into coamps and making some big changes, you're a little bit stuck.
Right. We're actually doing that for. Oh no, I've got an echo. We're doing that for our LES framework, but we haven't dreamed about doing that with coamps. Thank you. But yeah, I agree. That's kind of where everybody's going these days with the Lagrangian framework.
Thank you.
Okay. So, yeah, thanks, Michael. So I guess we're have a break now. So we can thank our speakers again.
Morning, everyone. Let's get started with the second session of today. My name is Thompson, so I'm going to chairing this session. Our first speaker is virtual. Can you hear us well online?
Yes, I can.
Okay, perfect. So Paul and Antonelli are going to talk about some of the advanced cloud predictions. So I think you can advance slides from your side. So please take away.
Thank you. Good morning. This talk will focus on the integration of satellite data to improve the operational forecast accuracy and the validation of the model forecast. Essentially, we will cover 4 areas. One is the prediction of cloud cover through the assimilation of satellite data and products in form of transform retrievals. Now we'll define them later. And they're derived from hyperspectral infrared data and microwaves. And we do this assimilation in a rapid update cycle numerical weather forecast model. Now the talk covers the advantages and the challenges of employing this kind of data and products for cloud forecasting. And it also shows the enhancement of the validation that we can achieve using VIRS and AVHRR in a statistical learning framework. From that, we will try to move to the future work where we want to replace the statistical learning with a deep learning framework. Essentially, the idea for us was to improve a numerical weather capabilities at the Mauna Kea Weather Center of the University of Hawaii. And they produce forecasts for the observatories on top of Mauna Kea. And the idea was to improve the accuracy of the initial conditions, which clearly are a key element in the forecast, in any forecasting system. So they had a WRF model, and we developed that. We transitioned that to a rapid update cycle WRF model, which is capable of assimilating those transform retrievals from the hyperspectral data. Transform retrievals have been introduced by Stefano Migliorini in 2008 and 2012, but they really took life from an idea of Clive Rogers in his book of 2000. They are in the reference. Now, the system developed at the Mauna Kea Weather Center, this rapid update cycle system, has been tested on the Central Pacific area, and there are 3 publications. The latest one is by Cherubini 2023, and over the Arctic region within the thin ice experiment. In both cases, the assimilation of the hyperspectral data and the microwave data proved to increase the accuracy of the forecast, especially in the water vapor field, and that's a key of this talk. Now, I've been talking about transform retrievals. So what are they? Essentially, they are retrievals, Bayesian retrievals of hyperspectral data, and they're obtained given that we have an a priori knowledge of the atmospheric state, and that would be the field. It's represented by the relative humidity field on the top left corner. And that's our best knowledge before something happens. Now we get an observation from a satellite in high spectral resolution infrared observations, and we want to update that knowledge and move to a better forecast. So with those 2 elements, the a priori and the observation, we can generate what's in the middle, which are physical retrievals, vertical profiles of temperature, water vapor, ozone, surface temperature, surface emissivity, all the elements that characterize the radiative transfer. From the physical retrievals, thanks to the Migliorini transformation, it's a linear transformation with a truncation, we can generate transform retrievals. What are the benefits of assimilating those quantities? Essentially, we bring thousands of infrared channels into about 15 numbers. And those 15 numbers are not biased by the a priori knowledge, by our first guess. So Migliorini demonstrated that transform retrievals are, in a given situation, are equivalent to radiance assimilation, but they're much easier to assimilate because they're independent on the instrument characteristics, such as noise or number of channels or any characteristic, and they have an observation error, which is the unit matrix. So it's extremely easy to assimilate them into a data assimilation system. With this, we do the assimilation and we do the forecast. This is the rapid update cycle that was put together at the Mauna Kea Weather Center. Essentially runs every 3 hours. And the nice part is that we can take advantage of YASI observations and CRIS observations that would fill about 4 slots of in the simulation cycle. To give you an idea, this is the simulation, those are the innovations in an assimilation which uses only conventional data. And in particular, here we have Ravinsons, buoys, and some aircraft data. This is over Hawaii. On the left side, you have the relative humidity innovation, an horizontal cross-section at about 460 hectopascal. And on the right side, you have the temperature innovation, always at 460 hectopascal, and for the same level. Now, if you assimilate, along with the conventional observation, the transform retrievals and the microwave, you would end up with this kind of scenario. Now, the first thing that hits your attention is really the definition, the number of, really the resolution of the water vapor field. It's much better characterized. And the temperature, it's different, but it doesn't show the same impact. Now, all the study, we did a test over a month of data, running the model every 3 hours, and they proved that when you simulate the transform retrievals and the microwave with respect to the conventional observation run, you have an improvement, a significant improvement, about 30% of relative humidity between 800 and 200 hectopascal. And all the results, I can't really explain them in great details, but they are in the Cherubini et al. Paper on 2023. Now, why did we push so much into simulating transform retrievals? If we take one step backward and we look at the hyperspectral data, hyperspectral infrared data, we want to really show what's the information content about the relative humidity field. Now here you have a scene over the Arctic Pole. This was the thin ice experiment just did last year. And here we take fields of view along the red solid line, and then other fields of view on the broken line, which are with the cyan circles. Now we want to take the retrievals, the physical retrievals along those two lines and create cross sections of relative humidity. Here you see that the scene has water, rock as the background. It has a cirrus cloud and it has low clouds. So when we do the retrieval, we end up with one case like this. On the top in the corner, you see which field of view we are looking at. It's over land, and it's about 60 kilometers for the yellow dot, which is a Robinson station. And if we do the retrieval there, the physical retrieval, so before the Migliorini transformation, but that still has all the information content in it, then you would end up with the retrievals on the left side, where the red curves are the retrievals, the black curves of temperature and dew point temperature, the black curves are the Robinson, and the blue curve is our first guess, what was used to generate, to activate all the Bayesian inversion. Now, in this case, you see the profile, they don't show any contact between the dew point line and the temperature line, indicating that there is no condensation. But if you move to another field of view, right next on the Robinson, you would see that in 2 points, the dew point temperature crosses the temperature, indicating that there is condensation. Now, the Robinson is co-located, but it's about 30 minutes, and actually more, because the Robinson launch is at 11 o'clock. The overpass is 12:29. But it shows that there is, according to the retrieval, there is condensation and there is a cloud. Now, if we go back and we take all the fields of view along the two lines that I show you, the solid and broken lines, you end up with a cross-section like this. This is relative humidity on the, clearly you have pressure on the y-axis, and you have latent long, so the 5 fields of view on the x-axis put together and just interpolating in a color map. And as you see, there is a cloud about 400 hectopascal, which covers those 4 fields of view. Now, under the cloud, there is a dry layer, and then there is another saturated layer, which is another cloud below. Now, point is, we're working in the infrared, so whatever is underneath the cloud, it's really unreliable. And the thicker the cloud, the more unreliable is the retrieval. This is a heavy limitation that we have right now. That is due to the fact that our Bayesian system has a clear sky forward model in it. So main effort for us at this point is to transition from the clear sky model into a forward model that can explicitly handle clouds, and that would be CRTM. So what we are doing now is we would like to get information even below the clouds if it's semi-transparent. If it's a thick overcast cloud, there is no way the infrared can see through it. But in this case, the upper layer is really a cirrus cloud and is relatively transparent. So if we move to the next cross section, you would see, and it's about 12 kilometers westward, because It's not north. We are close to the pole. So we move westward for about 12 kilometers. And we have this scenario. It's only one field of view is cloudy. So everything below that is unreliable. But you would see really the edge of the cloud where the relative humidity is approaching 100%, but it's not there. And there is the dry layer and there is the oil structure. That is the reason, the main reason why we really pushed hard into hyperspectral data, because they can give you a tomography of the relative humidity field, of the humidity field, and they can really give you a great representation of the cloud on the edges where other satellite instruments would have really hard time detecting the cloud. This is not new stuff. These results comes from about 20 years ago when we went to Maine and we did the HREC field campaign with scanning Ease, which was a precursor of Yazian Crease. It was MAS, which was a precursor of VIRS and an imager, VIRS and MODIS. And we had on board of the unmanned plane, that was the first time we used a drone, it was the CPL LiDAR. As you see, we validated the scanning is a relative humidity cross-section, which is the same concept as just shown, with the CPL LiDAR though. Now, wherever you see the black dots, that's where the LiDAR detected the cloud optically thick. And that's only the first layer detected by the CPL. There were also other layers, but I didn't put them there. So it's about 3 optical thickness. Where you see the white color or gray color, then the optical thickness decreases. And you can see how the water vapor field from the retrievals really matches nicely the cloud distribution. Clearly, I keep emphasizing this, whatever is under the thick part of the cloud is absolutely meaningless. That's it's not modeled in the radiative transfer, so cannot be retrieved. And that's why we want to move to CRTM. So the point for us was really taking advantage of the hyperspectral IR data, combining them with a microwave, because they still provide information through the clouds, even if at lower vertical resolution. Now, you can imagine what's going to be like having a geostationary hyperspectral instrument like MTG-IRS that will be launched in Europe next year. It will make a big difference. But like over the Arctic, the polar constellation is actually representing a geostationary satellite. So it works really nicely. And with CRTM, the capability, the forecasting capability and accuracy should really increase significantly. Now, we have fully understand that everything is moving towards a deep learning framework. But our approach is like, we did invest a lot in the simulation. We want to keep a simulation and the model. And what we want to do is this transition to the deep learning, module by module. So we want to replace really the small components of the overall system with the deep learning boxes. And one case, for example, it's the validation of the model. This is just an example of why we are transitioning to the deep learning. So once we did the simulation of the transform retrievals and we got our forecast, we validated with Ravinsons, we validated with the GFS and ECMWF analysis, we validated with the TPW, total precipitable water from the GPSs, and we validated with clouds using the VIRS cloud mask, the VIRS cloud detection system. So what we did, first step was to get the VIRS cloud mask and collocate on the WRF output. Essentially, we take the cloud fraction using the VIRS cloud mask and putting all the pixels, the VIRS field of view within each model, WRF model grid box. And we end up with a VIRS cloud mask on the WRF resolution. And then we compare the output, the cloud generated by the model before the data simulation. So this is only analysis, just before the data simulation and immediately after the data simulation. And we were hoping that ingesting the transform retrievals and the microwave and everything, we would get a better representation of the clouds. When we went to check the differences between our two outputs before and after the assimilation, and compared to our truth, which is Wirtz co-located on Whorf, we ended up with this histogram. Not only it's bimodal and it's not centered in zero, but also there is a slight degradation after the assimilation of the transform retrieval. So we go from an RMS of 0.513, that's on the top corner of the image, to an RMS of 5.19 after the assimilation of the transform retrievals. This was disappointing. Either the transform retrievals didn't work, or the assimilation didn't work, or the way we were generating the clouds that at that time was a black box for us was not working correctly. So we went to check the way the model was generating clouds was through a routine was called WRF-Pi, which is a very simple one, no big deal, but it was interesting for us. This routine divides the atmosphere in 3 layers, low, middle, and high, and has 2 thresholds to define the 3 levels. And for each level has a linear relation between the maximum value of the relative humidity in that layer and the cloud fraction. So we ended up with a total of 8 parameters that were preset in the model. And they were just producing clouds according to some values defined from who knows who. What we did, we started with a simplest possible approach. This was about 3 years ago that we did this. And we use a genetic algorithm. So statistical learning, very, very simple approach. We try to optimize our parameters, the 8 parameters, the threshold for the layers and the parameter of the linear relationship. And we ended up from the lower plots, which is the Whorf-Pi output in green, and we want that to be as close as possible to the target, which was the Wirtz cloud mask on the Whorf resolution in red. And that was associated to the blue histogram that, as you see, is bimodal and it's not centered in zero. After the training, with the simplest possible algorithm, it was a genetic one, we ended up with the orange distribution, which has still very large tails, but is nicely centered in zero. And we ended up with a purple image on the top, on the left, which is closer to the target cloud mask for Whorf. Doing the optimization over a month, we could reduce the root mean square error of cloud fraction from 0.56 to 0.037. So with this optimization, we went back to our case, doing the comparison before and after the assimilation. And we didn't see any significant improvement. But we improved, first of all, it's centered in zero, and we slightly improve after the data assimilation. The whole point of this story is really, we don't want to go with Whorf-Pi with a subjective system that goes from the relative humidity of the model into cloud. But what we would like is use all the prognostic variables within the model, feed them to a convolutional network, and have directly as output the cloud fraction. We have a huge amount of data that we can produce in using Wirtz data. And the idea is to start going towards this module. This is just one example how on the way we would like to use deep learning. But the point here is we try to improve the forecast of clouds, improving the definition of the initial field, assimilating hyperspectral data, which for us carry a lot of information with a 3D field of water vapor. And we try to use other satellite products to improve also the validation of the forecast. Now, there are things that we are going to change, like the use of CRTM to be able to handle also cloudy scenes. And more important, we are slowly moving through deep learning frameworks because, as in many talks you have been proved, they just work nicely. So this concludes the presentation. There are more references that you could find in the slides. And please allow me to really thank Carrie and Fletcher for the nice support they provided and for the patients they had. Thank you very much.
Thank you. For the interest of time, so we're going to move on to the next talk. If folks have any questions, feel free to email him. So our next speaker is Yoo-Jeong. She's going to talk about the 3D clouds.
Okay, I'm Yoo-Jeong. People call me YJ. I'm working at CIRA. It's 1 hour driving from here. I'm talking about, it's a little bit new concept based on satellite data, 3D cloud data field from satellite. So this is a big project. Of course, it's we are working with so many CIRA researchers and other collaborators are listed here. Okay, it's a little slow. Okay, so it's here satellite is just a conventional passive sensor carrying satellites like a GOES or GPS spheres. So here is some sort of a background. It's a new concept actually. It's usually this conventional satellite sensors, passive radiometers are not designed to provide the cloud base. So most information is for cloud top or vertically integrated contents about clouds. So our team has been developing statistical cloud-based height algorithm using NASA A-Train satellite data, MODIS, CloudSat, and Calypso here all together. So based on global statistical, okay, can I use this mouse? Okay. Global statistical relationship between, okay, not good, okay. So geometric thickness from active sensors like a CloudSat radar and the Calypso LiDAR data to connect this quantity to cloud water path from MODIS. So we came up with a global lookup table to drive cloud geometric thickness here. So cloud-based height can be derived by subtracting geometric thickness from cloud top height like this. So I have to say this cloud base is optimal for single layers. It's actually designed for the uppermost layers. It's again, this is a satellite cloud base. So this information is also used to improve another cloud product, cloud cover layers. Originally, we always using cloud top information to drive a cloud layer information like a high or mid or low layer information. But with this cloud base height, we can drive some sort of a vertically extended cloud vertical layers like a high plus mid or mid plus low or high plus mid plus low like a deep convections. For aviation users, this information is classified for 5 flight levels as shown here. So this algorithm is operational, and if you are interested in, you can find this level 2 product from GPS spheres and the ABI data. So this is a little success story as an algorithm developer. But problem is, yeah. Next page, please. Why it's so slow? Okay. Yeah, it's this is one example to show how effectively a cloud base can provide more information for vertically extended cloud layers. Goes 16 ABI over corners. So you can see cross section from CloudSat radar data as a ground truth. So when we are using a cloud top information only for this deep convective storm here, we only can get the high layer information, but adding cloud-based information, we can now get vertically extended information here. So this algorithm is all applicable to general geostationary and polar orbiting satellites. So this is popular. Hopefully you can know this CIRA's web-based slider satellite data display too. So you can see it's on the right, left. yeah, on the left, and so you can see geo-color image with the GLM overlaid over corners. So now we can see a little more quantitative cloud particle layer information. I cannot show all the details about our new approach utilizing machine learning for improved multi-layer cloud. You can see a little pink here. So it's actually for multi-layer clouds to detect the low layer clouds on the cloud top. So here is a official NOAA enterprise cloud product list. You can see so many. So actually, our team has been involved in some sort of NOAA satellite cloud product demonstration for aviation users. Interacting with the aviation users, a big lesson we learned is there are too many products and forecasters too busy. The users are already overwhelmed by numerous data sets. They have no time to look at additional cloud products. Even most time, they don't know this kind of product exists. So we are trying to find another way how to promote the use of satellite-based cloud data. Actually, our big policy to provide us this satellite data is how to support our users with this expensive instruments. So we're trying to develop a new concept to provide the satellite data here. So we develop a new data processing to provide a satellite-based 3D cloud build like this, combining multiple 2D pixel-based satellite cloud data into one box with some additional information useful for aviation users, for example, temperatures or pilot data or train information together. So interacting with, again, aviation users, based on their insightful feedback, we developed this new product. So this is one example from VIIRS. You can see cross sections here, Alaska, Nome Airport to Anchorage. You can see this cross sections, terrain information in brown, from cloud top to base, colored by cloud phase, another cloud product from satellite. So based on user feedback, we added the async and the turbulence information from PIRAPS. And another satellite sounding product like a new caps, we can add temperature information. If satellite data is not available, we can replace this temperature information from NWP, of course, here GFS. Yeah. So with the very positive user feedback, we extended this effort to corners area with addition of ABI geostationary data here. And recently, it's a very popular topic, Canadian wildfires. So as requested by aviation users, so we want to provide a better visibility information. Here we added the HER smoke model data into this cross section. So you can see some yellow dots from heavy smoke. So this experimental satellite-based 3D cloud data is available for user feedback and evaluation on our CIRA aviation websites here. So it's extreme case. If you like to fly from somewhere over Hurricane Ian case, you can get these cross sections based on satellite data. And with the new addition from the smoke data from our model, you can see not just the cloud cross sections, you can see small cross sections here too. So it's not operational website, so maybe sometimes slow, but you can test our product and directly can provide feedback to us. So for this research, interaction with the aviation users are a key point. AWC, Aviation Weather Center, is our big partner for this one. And thankfully, Alaska pilots are having some good relationship with for our research, and they always support and provide very valuable feedback for that. And recently we started providing this cross-section information for NTSB aircraft accident investigations. So this is one example over Alaska near Fairbanks. So actually, this satellite data is very critical for data sparse region like Alaska. This is one example. So we published one paper about this overall satellite cloud 3D data construction and the user developer interactions last year. So you can find some more information for this Beers 10-year special issue. So you mean it's so far, it's 10 years passed by for this work. So now, why not for global scale? So we have a chance, of course, sponsored by ONR. We are now extending this effort for the global scale. Satellite-based 3D global cloud field analysis. We call the CIRA Overcast project. It's pretty new. For this project, it's not just the satellite-based cloud 3D layers over global. We are adding so much other new advanced techniques, leveraging various research field and CIRA. Of course, we are being mindful of the past and current and future global cloud data development efforts like WIMCA and ESCAPE next generation. So we are so closely working together with our partners for this effort too. So not just the 3D, for this case, we should say it's 4D because we have a nowcasting component. Yesterday, Major King presented about all these things utilizing optical flow. So I don't think I need to explain more. So this is one example for geostationary. We call the GeoRing sensors. We combine the all cloud product. First, we applied all NOAA cloud algorithms to individual geostationary sensors and combined this cloud product into 2D-dimensional first and 3D-dimensional later. So our vertical resolution is 250 meters now. And internally for preliminary test, we are producing this global 3D data hourly, but our target is, of course, is native time resolution about each satellite is 10 minutes. Of course, we are working on to add a Apollo satellite into this field. So this is animation hopefully working here. So visualization tool development is not our major part, but we understand how important to demonstrate this kind of product to users. So this is one example based on our 3D data. So you can see all the clouds over the globe. And of course, we have more extra to figure out how cloud phases are different or time difference for this 3D visualization. But I can give another chance to our colleagues to present this pretty result here. And of course, it's not easy to blend all kinds of different sensor product here into one grid domain. So time difference, of course, you can imagine it's an API case for this, say 2 UTC, doesn't mean the all scans are 2 UTC. It's time difference. And video accessory has a different scan geometries. So 215 means starting from this bottom side. So different time changes, or of course it caused the cloud displacement. So we are also utilizing to match up these time differences, reduce these time differences using optical flow here again, and the spatial blendings, including parallax corrections. We're examining all the big discontinuities and checking all the data stitching. It's the one dashboard. It's a lot of work, but it's just one page slide. So here we are utilizing AI schemes in many ways. It's one example to drive a whole vertical cloud water profiles here. Various channels are training against the cloud set radar data vertical cloud water profiles. We are using fully connected convolutional neural network to drive whole cloud water profiles from satellite. This is to complete the whole 3D cloud structure information here. and hopefully we can help improve cloud visibility and some aircraft icing potential detections to provide some supercooled liquid water profile information based on this AI model. So I found very interesting topic yesterday about CFLOS. Here is another example using our almost near real-time satellite-based 3D cloud data. We can now drive deterministic cloud free line of sight. So it's almost like a near real time, and we can calculate which distance cloud free line of sight here. So this is one example. Just example, not target over West Virginia, but something like that. So we can just assume this kind of targeted aircraft location. So when we just assume the all distance is stopped by any cloud, we can calculate the cloud free line of sight. The distance is 90.6 kilometer. And we can assume some sort of a transmissivity, like in cloud cirrus, we can see through the cloud layer, we can get much longer flight CFLOS distance. So this is one just the point-to-point calculations, but now very recently we completed the whole calculation, like a whole area to point CFLOS calculations at any certain levels and within certain areas. So it's all codes are based on Python and very fast, even in very just a small size Linux I'm using. So this case, it's CFLOS calculation 2 seconds, and some area calculations that takes 2 minutes. So we can instant cloud free line of sight calculations. So it's more to come because it's a huge project and cover the various areas here. So multi-layer cloud improvement utilizing machine learning and some other global high resolution microwave and synthetic radar data. You may heard hear about some Gremlin synthetic radar data by Carl Hilborn. So it's a little compound for this project. Nighttime clouds is another big topic for satellite cloud retrieval. So we're working on that. Of course, it's now casting components there. Transition to operation is very important. We are working on transition here. Validation is another component. The whole team is working on that. We are working on various levels of validation of product, like a level 2 cloud product, 3D global stitched output, and even including AI-based output. So here, I just briefly introduced our CIRA research for satellite-based 3D cloud. Here's a summary. Yeah, that one. Okay. So leveraging NOAA research, and now we are extending this effort toward the global scale sponsored by ONR and several different areas. I cannot show all the details, but any comments, feedback, and collaborations are welcome. With that, thank you. Any questions?
Some questions?
Are you guys using JEDI at all for any sort of management, like the IOTA tool or R2D2? I'm not sure how familiar you guys are. And what file format are you using for your ultimate output?
NetCDF.
NetCDF, okay. Yeah, so are you guys looking at integrating with JEDI at all for?
No, not yet.
Not yet.
Any other question?
What projection are you guys using for, or what gridding are you using for your merged cloud analysis?
Oh,
So GDAL?
For now, it's the equal distance coordination, but we have other options to consider.
Use CloudSat over Calypso.
Oh, so question. Okay.
What went into the decision to use CloudSat versus Calypso? Do you use both?
Both.
Both, okay.
Yeah.
cloud that processing center is a part of the lab.
Okay.
So we were taking advantage to access all kinds of data.
Thanks.
So I have a question about C plot. I know the output is distance. What's the input?
Any location, any latitude, longitude, and we can imagine some sort of airplane.
Okay.
And target. So we can calculate at any point.
Okay. Thank you. All right, let's thank our speakers again.
Yeah, so and thanks again for the opportunity to present our work. And this is somewhat related to what the previous presenter showed, in the sense that we're trying to generate a global data set of cloud properties with a high temporal resolution, at least at this point, hourly resolution, by merging geostationary satellite and synchronous satellites. And this is a big effort of our group at NASA Langley that includes myself, Bill Smith, Louis Nguyen, who is fortunately he's in Boulder. So if you have more questions or you want to discuss details of this presentation, feel free to reach him out. And if you have any criticism, you can always send me an email. And I'm representing NASA Langley for this presentation. And next slide, please. We have a long history of producing satellite cloud retrievals. More than 20 years, we started producing cloud retrievals for the climate data record, specifically for the NASA CIRIS program and the radiation budget science program. And essentially, we provide satellite cloud properties to the CIRIS algorithm. And by ingesting this information, we are able to produce shortwave and longwave fluxes at the top of the atmosphere as well as at the surface. The design of this algorithm allow us to apply the methodology to more than 20 different satellite sensors, and during the series record starting in 2000. But we also use these cloud retrievals for a number of other applications and for supporting field campaigns and for many other near real-time applications and historical cloud analysis. And they are currently used for numerical weather prediction groups and centers, and for validating models, and also for improving cloud parametrizations. Next, please. And this is a very brief introduction of what we can get from satellite retrievals. By combining a few channels, we can get a number of cloud parameters, and which includes cloud mask, and that is whether the pixel is cloud-free or cloudy, and the type of cloud phase, and cloud optical depth, and thermodynamical properties, and cloud effective radius, liquid water path, and many other cloud properties that are relevant to the study of clouds. Our strategy, our philosophy is to combine, next slide, please. Combine in satellite channels that are common to all the satellite instruments, and apply a common algorithm with some tweaks to adjust the changes in the radiometric channels of the instrument and calibration. Next, please. And this is a brief example of the geostationary satellites that we are currently producing. This figure needs to be updated because we are currently producing data using GOES 18. But here you can see a snapshot of 5 different channels, 5 different satellites. And on the upper panel and the lower panel shows the corresponding cloud top height for that specific UTC time. And so we operate and we utilize a number of LEO and GEO imagers for real-time and historical applications. And the challenge here is put together all these 5 images into one coherent and seamless global data set. Next slide, please. And the steps that we need to take before moving to the stitching process is to make sure that the multiple instruments are properly intercalibrated, to have a cloud mask algorithm that provides consistent results across different satellites. And then we have a cloud algorithm in place. And essentially, it's an inversion algorithm that utilizes a one-dimensional radiative transfer model. And we match this one-dimensional, the radiances from the one-dimensional radiative transfer model, we match it with observations. And by matching these two parameters, observed and simulated radiances, we can derive a number of cloud properties, as I just mentioned. And obviously, these algorithms are dependent on the viewing geometry and illumination. We validate our retrievals. We have a long history of validating our retrievals, a number of papers that shows that our retrievals of cloud microphysics and cloud height and phase compare quite well with other satellite instruments, such as CloudSat of Calypso, and also data collected from in situ field campaigns, aircraft campaigns, and the ARM program dataset as well. And we are currently working on improvements, and we are going to talk more about these improvements in a few more slides. Next, please. Next slide, thanks. So here I'm going to introduce the concept of global cloud composites from the satellite. So our objective is to optimally combine geostationary and synchronous radiances to derive cloud properties and radiative fluxes. So the idea is to do this in such a way that visually you're not going to see this discrepancies when you move from one domain to the other, and when moving from information derived from one satellite versus other satellites. And our goal, and what we are producing currently in a testing environment, is a 3-kilometer grid data set, and with a temporal resolution of 30 to 60 minutes. And here, in the upper figure, it's a nice movie of optical depths, the Darn cycle of optical depths for one specific day. And you do see that we can see that the algorithm allows us to have a global view with no gaps, which is quite remarkable. And there are some, however, we can see some discrepancy if we see some strange vertical lines, and I will explain more that what's going on there in a few more slides. So in the lower panel, the lower figure, you see the satellite where we got the data to produce the composites. So each color represents a different instrument and different satellites. So as expected, non-polar regions are mainly contributed by geostationary satellites, except for these funny circles that you see once in a while. And these funny circles correspond to sunglint. So to get rid of the issue of sunglint, we make use of sun synchronous satellites to fill the gap produced by sunglint. And of course, in polar regions, mostly the radiances and cloud retrievals are contributed by MODIS, Aquanterra, and NOAA-VERSE. Next slide, please. And here's another snapshot on another example of how the global composite look like. So the upper map is the scene identification, and each color tells you the information about the type of clouds we are observing. The white color is water cloud, for instance. Cyan is ice cloud, and blue is clear sky water. And it's nice to at least visually see a very continuous global view of the cloud face. And the lower panel is the equivalent figure but for cloud top height. This is again as a snapshot at the 1030 UTC, and you see again that that there is no gaps in the image, and the cloud variability is quite consistent. You see clouds with high altitudes for the extratropics, and also some convection over significant convection of the maritime continent. And we are generally, currently, we are implementing a number of improvements in our algorithm, and we are making satellite-specific atmospheric correction. We're improving our clear sky radiances, and we also implemented a better or a more realistic ice cloud scattering model. Next slide, please. And of course, we have a number of issues in our system, and they are inherent of using satellite data. For instance, you sometimes have bad image quality or bad scan lines, and we are currently resolving those issues using a combination of visual inspection with a convolutional neural network. And we are currently successfully able to replace those bad scan lines with good quality data. And a very important issue that was mentioned in the previous presentation was the inconsistency between day and night. Most of these retrievals are designed to be to use daytime observations. You use the reflectance, and at nighttime you have a minimum signature of for reflectance. So how can you address the problem? And I'm going to talk about this issue in a few more slides. And the same thing with the solar terminator, and that is the transition between day and night. Generally, the remote sensing algorithms have some issues deriving cloud and high quality cloud properties for the solar terminator or the sun glint. And we are implementing a K and nearest neighbor to resolve the issue. And we have a list of, I'm not going to go through all this, but I'm just mentioning the ones that I will be talking about in a few more slides. Next slide, please. And this is the nighttime, the problem with nighttime cloud properties. And it's shown in these two maps on the upper right. So the upper figure, it's a cloud optical depth, daytime cloud optical depth from aqua modis. And the lower map is cloud optical depth from MODIS as well, but for nighttime. And there's clearly, if we compare both maps, there's clearly a Darna cycle that is clearly an artifact. Because of the limitations, the infrared black body limit, we cannot produce physical retrievals of cloud optical depth and many other cloud properties when the cloud is, the optical depth of the cloud is more than 5 or 6. So that essentially means that if you're using a physical retrieval, you're not going to get cloud optical depth greater than 5. And this is what happened in the lower panel. So we're trying to do our best to fill gaps when we think that we have optically thick clouds, but still the algorithm is not perfect. And obviously, because we are underrepresenting the clouds, it has a big impact in the way we see clouds during nighttime, and also in radiative fluxes or even in aviation weather hazard application or icing conditions. So we're trying to address this using a K nearest neighbor. Please, next slide. Thanks. So this is what we're trying to do. So we're using daytime data and daytime observations for the day before, and we are matching the cloud optical depth with two infrared channels, the 6.7 and 11 micron bands, and we're extrapolating the relationship we found for a few hours later during nighttime. This is a very brief explanation. The long explanation requires a standalone presentation. But what I want to show here on these maps, on the left map, is the nighttime, the all nighttime retrievals. Okay, and this is a mean and monthly mean. Just this is and on the left again is the all cloud optical depth retrievals for nighttime, and on the right is the daytime counterpart. And again, we see clearly. And they're a cycle artifact. You cannot have such a thin clouds during nighttime. By applying the KNN algorithm, and next, please, could you make it one more click? Excellent, thanks. And you see here the results of combining the KNN with the theory to produce a better transition between day and nighttime. At least now they are comparable. We're not going to have a Darn cycle artifact, but of course the magnitude of the difference, it remains to be demonstrated whether this amplitude, the new amplitude of the Darn cycle is realistic or not. But at least we're not retrieving a Darn cycle artifact. And the figure here, the figure on the left is the old algorithm. If you focus just on the left, you are going to see clearly that there is a clear transition between night and day, and this is completely an artifact. And when we move to the right map, the right panel, with the new retrievals and the new methods, you're going to see that such artifact disappear, and you clearly see the transition of clouds, and there is no significant contrast between day and night. At least it's not a step function. You're not going to get values of optical depths of 5 at 5 in the morning, and 1 hour later you're going to have optical depth of 20. This is clearly an artifact. And next slide, please. And this is a similar example. This is for cloud mask. I'm sorry, for cloud phase. And the issue we're having here again is the terminator. The terminator is the day to night transition. We're having issues during the transition. And for instance, on the left, you can see a very strange vertical line that moves to the west, which shows the location of this terminator transition. So, and on the right, we have the new algorithm with the new KNN method. And to some degree, and to a significant degree, we were able to get rid of these day to night inconsistencies in the cloud mask. And next slide, please. And I would like to finish my presentation with a different topic, but I thought that we thought as a group that we should bring this up because it could be relevant for the modeling community and for weather forecasting. And it's a new tool that we are currently implementing. And next slide, please. And what we are doing is combining hyperspectral information with geostationary data and microwave sensors to produce a new data set of satellite-derived temperature and humidity profiles. So we're using data fusion techniques to come up with a new data product that is that it can be retrieved even when you have clouds, and it can be interpolated in time using information from geostationary satellites. So the fundamental retrieval still comes from the hyperspectral retrievals, but when we have clouds, we fuse these hyperspectral retrievals with microwave, and the geostationary data gives you temporal information that is all ingested in a new algorithm. Next slide, please. This is a very, very brief summary of the results we are getting. So one of the things that we are doing is try to test the sensitivity of, in this case, a WRF model to the simulation of the new satellite retrievals and of temperature and humidity profiles. So what we are seeing here is the error in expressing in terms of standard deviation for temperature, humidity, and wind velocity. So the blue profiles is the control simulation, the simulation that does not ingest any satellite retrievals, and the red profile is the one that ingests the new humidity and temperature profile. So the main message here is that in this preliminary exercise, at least, we're getting better simulation of temperature and wind speed and humidity than when you don't assimilate these satellite retrievals. But obviously the benefits of assimilating these satellite-derived profiles need to be further evaluated. And next slide, please. So we developed a system to create an hourly global composite of cloud properties, combining geostationary and synchronous images, and with a spatial resolution of 3 kilometers and an initial temporal resolution of 1 hour, but it could be up to 30 minutes depending on the needs of the future users. we're incorporating a number of techniques, neural network techniques and other forms of artificial intelligence to improve level 0 satellite radiances and get rid of the artifacts and really clean the data before producing our cloud properties. So our goal is to produce a multi-year data set, and it's going to have, as I mentioned before, it's going to be hourly. And our hope is that it's going to be useful for the modeling community. It can be used for validating the models, or it can be even used for data simulation. And we're in the process of producing relative fluxes using our new global composites. And we are using this global composite in combination with the radiation transfer model. And we're going to make available this data set freely at no cost. And yeah, more is coming. And it's going to be a web mapping coverage service for visualization and analysis. And that's my presentation. If you have any question and if you have any time, I will be happy to answer them.
Thank you. Any question? Maybe just one quick question. If there any question for the audience?
I'm not sure it's a quick one. I'm interested to know kind of at a basic level how different this system is compared to the previous talks, just in terms of the basic retrieval algorithms. I know there's going to be lots of differences in detail, but can you comment? Are there any fundamental differences?
Well, I'm not quite familiar with the previous effort. In this case, we're actually and it would not be fair at this point to say anything about the other system, because I don't know what the stage of their project. What I can tell, but what I can tell you is that in our system we are able, and we are currently ingesting all this data and geostationary and some synchronous satellite observations right now. So we have a system in place, and we have an algorithm in place, and we have a methodology to select the best pixels based on this, based on the available data. But that will be a good question, and probably we need to discuss with our colleagues there in Colorado to see what's the progress versus what is ours. But what I can also mention here is that our goal, and probably is the same for our colleagues, but our goal is to produce near real-time data, and we're working and we're working hard to make this data available with a very low latency. But again, I cannot comment on beyond what I just mentioned.
I can add one comment on that. It's a big difference is a NASA algorithm versus NOAA algorithm, and ours is a 3D cloud.
I guess I'm asking at a fundamental level, are those algorithms hugely different, or are they basically the same?
Because radiative transfer model and some radiative transfer theory basically similar, but it's algorithm development history itself is totally different for a long time. I can say it's different.
Yeah, I mean, there are many details about algorithms, cloud algorithms, the way we do calibration, the way we do intercalibration. So our intercalibration is based on the CIRS program, which has in mind the climate data record. And also depends on the way you do the retrieval algorithm, how you implement the algorithms. And comment on other algorithms that are not ours is it's something that I would not do at this point, I think.
Well, thank you. I think that's a long answer for a quick time, for a short time. Thank you. Thank you for your presentation. So we're going to move on to the last speakers. Please hang tight for the Oscar VSTA from Egypt.
Real quick. I know the lunchtime is coming up, so I will make it quick. So here I will share with you our new developed capability for all sky radiance data simulation for tropical cyclone application. First, let me acknowledge my collaborators. First, my colleagues at NRL, Qin Yunzao, he is the major developer for the ENKF system, and then Nancy Baker, Jim Doyle. And we also have David Riglicki, who's here today. He's our former colleague, but now with MyRadar. And we also collaborate with Robert Nystrom at NCAR and Xinzhao Chen, Jerry Zhang at Penn State. Just a little bit of background or introduction. Okay, so this we developed this new capability for CIMSS, which is Navy operational regional tropical cyclone forecast system, and by assimilate GOES data, mainly the IR water vapor channel, and this capability, this technique was developed first at Penn State, and then encouraged by ONR, we collaborated with them and implemented in the CIMSS. And we also developed some new technique for its effectiveness and efficiency. For example, we have to develop some methodology for the moving nest for tropical cyclone application. And so we have tested this system for different tropical cyclones at a different intensity stage, and also from different ocean basins. For today's talk, I will show you some example for tropical cyclone Patricia, very strong hurricane from the East Pac, and Harvey from Atlantic 2017. And here briefly is the diagram showing you the ENKF system. Basically, the main idea is we use the ENKF data simulation system to do hourly data simulation for a period of 6 hours. Then we launch one deterministic forecast from the ensemble mean for the next 5-day forecast. And for we have 60 members. We found that the large number of ensemble members help to generate a positive impact. And for the comparison, we also did a control run, which initialized with the from the GFS analysis. This is how the operational CIMSS forecast is being done currently. And notice that we have a 3 nest configuration with the innermost 2 nests following the storm automatically. And the all sky radiance data simulation is performed for the innermost nest only. And shown here is the evaluation for Hurricane Patricia, the upper panel, and the Hurricane Harvey, the lower panel. The left corner, column is for track comparison. Middle is for the minimum sea level pressure, and the right column is for the maximum surface winds. The best track showing black, the control run showing blue, and all sky run showing red. So for Patricia case, the track is pretty similar between these 2 experiments, but you see there is a significant improvement in the intensity forecast from the all sky data simulation, and especially the intensification rate is well simulated. And for the excuse me, for Hurricane Harvey, you can see here there is also moderate improvement for the intensity. And one thing interesting we saw here for this case is for the track forecast, there is an improvement from the all sky data simulation. We will come back to this later. And so these 4 panels shows you the 4 prognostic variables impacted directly by the data simulation system. So it's a clouds and the water vapor, we see this QV, and the temperature lower left corner, and the pressure at the lower right corner. And so this is the difference between the all sky run and the control run. So at the 0 hour, the all sky data assimilation generates lots of clouds at middle to upper levels in the inner core region and also near the center at low levels. And for the moisture, the QV difference, you can see there is increased moisture near the surface in the inflow. Or I should have mentioned this is radius and height view of azimuthally averaged fields. And so there is increase of moisture near surface in the inflow layer, also near the center. And then you can see there is warm in the temperature fields in the middle to low levels, and especially there is warm core developing at the upper levels by the all sky data simulation. And there is a general pressure drop from the data simulation in the tropospheric area. And so now let's look at the dynamic fields, which is not directly impacted by the data simulation, but indirectly through the E and KF system. So shown here is also the azimuthally averaged wind, the radial winds in shading and the tangential winds in contour the left panel for control the right panel for the all sky run. So you can see at the beginning, so the data simulation helps establish the secondary circulation really early into the simulation. And it also enhances the secondary circulation at a much faster pace than the control run during the first 12 hours. Over the next 36 hours, this is during the rapid intensification period. This impact persists, and the all sky run also still had much stronger secondary circulation. Now, with the help of this organization of the dynamic flow, you can see the organization of the convection in the inner core region. Shown here, shaded is the total clouds, and the black contour is the vertical motion. So the enhanced secondary circulation in the all sky data simulation run, you can see in general, there is a better organized convection in the inner core region than the control run. So the next one, we show the comparison of the simulated composite radar reflectivity from this control run, the upper panels, and from the all sky run, the lower panel. So at 1 hour, this model starts to generate clouds, try to organize the convection around the storm center, but it's a much looser structure. With the data, all sky data simulation, you can see the clouds now is concentrated in a much smaller area with much detailed structure in the all sky run, in the lower panel. And then during the next 12 hours, that's the initial period, we can see the storm center is being organized into a very tight structure by the all sky data assimilation compared to the control run, and which this impact from data simulation is carried through the development of the storm. So now I want to show you the impact on the storm inner core structure. Shown here are now let me move to the case Harvey, and similarly showing the impact on the 4 model prognostic variables. And for this case, similar to the Patricia case, you see the generation of the clouds at the initial time, also the reduction of the tropospheric pressure in the deeper layer. There are also differences in the impact for this case. That is, for this case, the all sky radiance data simulation actually cools the boundary layer and also dry up the boundary layer. So it's very interesting to see that the impact from the data simulation are different and it's a case by case. And as we mentioned earlier, we see the impact from the data simulation on the Harvey track forecast as shown here below during the initial time, and it persists for the first 24 hours. So we want to understand a bit about this impact. So we look at the synoptic environment, the magenta contours on the 500 hectopascal geopotential heights, and the shaded region is the lower level potential, low level relative vorticity. So this vorticity shows the location of the Harvey at this time. And you can see in the control run, there is spurious low pressure center over Mexico in this run. But when we run the all sky data simulation, this low pressure center is removed. And so which results a much improved track forecast from this all sky data simulation run. And if we zoom in further, you can see that this low pressure center existence is more prominent from the control run. In the control run, these low pressure center also disappear within several hours. So in summary, we have developed this all sky radiance data simulation system through our collaboration with Penn State for tropical cyclone forecast application. And so our preliminary evaluation suggests that the impact on the storm model prognostic variables, including moisture, temperature, pressure, can be carried over for extended period of forecast. And we see different impact from the all sky data simulation system for different storm cases. So this is all I have, and I'm happy to answer your questions.
Do you have any questions?
It's always good to see data simulation making impacts on, tropical cyclones in general, but how many other cases can you do to find out if it's really, really consistent, or do you, everybody shows the sexy cases that work well. How about the others? Do you have some that didn't work out so well?
Right. So we have run many cases during the past 3 years, 3 seasons. And we see in general, the statistics show improvement. But the Patricia is a particular case for this significant improvement. And we also run the data simulation for very weak case because we want to make sure it doesn't over-intensify the storm. And we were happy to see it actually didn't over-intensify the storm. So I can show you other storm cases.
Any other questions? How do you handle the bias correction for the radius for the ridge line?
We in the system they already did the technique developed at Penn State. They already take care of.
Bias correction.
Yes. What we did is to try to decide the influence range for tropical cyclones in the innermost nest.
All right. Well, thank you for hanging out. And
good afternoon, everybody. Are you guys on the virtual listen here as well? Can we get a thumb up over there? Okay, good. Okay. Today, the first talk for this section would be Eric, and he was talking about a comparison of spatial dissimilarity measures.
Yeah, thanks. And our UCAR decided to change all our web addresses. And so I know all of you had my staff page bookmarked. And so if it doesn't work anymore, you can just search on my name and I'm one of the first things that comes up. And I say that because for the references, if you do decide that you want to look at any of them, I'm mostly going to talk about the ones that are highlighted and the others are more background, but I noticed, like, for example, I will talk at the end about the Ivette et al., which, so I should have highlighted that one as well, but just so you know, you're not scrambling to write down DOIs or something. So I'm going to be talking about binary fields. And so you can imagine setting a threshold like 60% for cloud amount. And so it's just zeros and ones. And the thing to pay attention to in the few equations that I'm going to show is whether or not we're summing over the entire grid. So I label as script D, or whether it's just over a set like of ones, basically. And so when I say a set, I mean the one valued areas. Now, if we're thinking about a point in the grid, it's relatively easy to decide what is the distance from that point to a set A. There are different things you could choose, but what we're going to be talking about entirely here is the shortest distance from that point to the nearest point in the set that we're interested in. So I labeled that as D, and then I'd say it's located at some point in the grid, and then it's a distance from that point to some set that I labeled in this case A. And you can imagine doing that at every point in the grid, right? And if you do that, it's something called a distance map. So a lot of times I call these spatial dissimilarity measures now, but in the past we talked about them as distance map measures, or I think we also had other names. But it's a little more challenging. So it was easy to decide from a single point, but now if I want to compare two sets of points, and imagine if I just overlaid two fields, right? So set A is maybe in one field and set B is in another field, and I've superimposed them on top of each other. And I want to know how similar or dissimilar are the two sets in terms of their spatial orientation, right? Not just orientation, but distance and all of these, size and everything. It turns out it's a much more difficult problem to do, as we'll see. And there's really no one, just like always, there's no one summary that is the be all and end all of it all. So in trying to compare all these different methods, we came up with a bunch of different test cases. The first of which I call the pathological cases, and that's kind of where you have an empty field, because it turns out a lot of these measures don't work if there's no set at all. So that was one. And like, what if the entire field is covered, right? Like you might have 100% area of cloud. And it turns out maybe some of them don't work so well then. But what if you have nothing in the field and then you turn on one grid point, right? Some of the measures give you a drastically different answer, depending on where you turn on the grid point, or, so that's why we came up with those cases. Generally for clouds, you're probably not so interested in those, but if you're aggregating or you're doing it for a lot of cases, then it's important to kind of know how they behave. And I'm just going to give a sample of some of the test cases we came up with in this 2017 and 2020 papers. So one is like, what if you have the same two features, but they just show up in different parts of the field, right? So ideally, you get the same answer, but it turns out you don't always, depending on the measure. So it's important to know that. This one is supposed to be frequency bias. I chose the case to show here that's kind of off on the side, but we also had one where they're in the same spot. And so it turns out some of them give the same answer regardless of whether you have extra circles there, right? And so it's important to know that. So that's sort of like, is it sensitive to a frequency bias or not? And then rare events maybe isn't so much of interest here. You know, this came up in precipitation when you have a small area with like, but that's a lot of, you know, strong thunderstorms and such. And you have a huge field and then just this small area. You know, a lot of them say, well, it did really well, but maybe it didn't, you know, and so it's important to know which ones work there. And then I think Gregor came up with this one, you know, what if you get a partially perfect match, but somewhere else is not? And I think he talked about it more in terms of rewarding the forecast for giving a partially perfect match. And I think of it, well, what about correctly penalizing the forecast for getting it partially incorrect? So you'll see some of them behave differently for that. So the first measure I'll talk about is one that got used a lot, I think largely because of mode, the method for object-based diagnostic evaluation. And I should have said too, I'm thinking about this as taking the entire field, but you can also just take individual features and do the same thing and, you know, use them with mode, for example. So centroid distance is an obvious thing you could look at. And it actually works pretty well. But there are some issues, like, for example, these are all perfect scores for, you know, so I'm thinking of the gold and purple are the two sets. But by centroid distance, these are all perfect, whereas these give a worse value, right? Because these are all 0 and these are a little more than 0. So it's not, no, so that's an issue. I think a lot of these test cases I came up with just to break the centroid distance because it was so easy to do. And then, you know, something, so earlier in my career, I was really into the image warping idea, you know, because that's, if you're familiar with the spatial verification problem, I think most of you are, which is why I didn't talk about it, but image warping is really what you want to do. You want to morph one field so it looks exactly like the other field in terms of the spatial alignments and everything, and then do your root mean squared error, and then analyze, okay, how much did we have to warp it, and in what ways did we warp it? And but it's challenging to do image warping, and even if you can code it up and you do it, it's challenging to summarize all that information, as it turns out. And so really these spatial dissimilarity measures are like just a brute force way to just kind of summarize that information essentially without having to do any image warping. And just so some things that I would think about is, well, what if we have like these two circles and and we're comparing with a field that just has this circle, superimpose them, you know, I could warp it by just doing a rigid transformation, move it up, or I could go down. Or I could probably get a better thing if I really do some crazy warping, you know, in the more. And so the answer is, well, what do you do? Right. And so that's one of the reasons it's so challenging to do that. So these spatial summaries are just, you know, okay, how good or bad is it in whatever sense? So in terms of trying to come up with the different points, and I realized I only put points that were in one or both of the sets, but you could think about taking all the points in the field and calculate those distance maps, and or you could take just points from one field and how far are they to the nearest point in the other set, you should say. So all the points in one set to the other and vice versa. So there are different ways you could do that. The Baddeley delta measure, and the main thing you want to look at here is I'm summing over that entire grid, right? That's the script D. And so I basically take the distance map for A, the distance map for B, and basically just take the difference between them and then average them, okay? It's an LP norm. So if you set P equal to 1, you get the average. If you set it to 2, you get Euclidean distance. And if you set it to infinity, you get the maximum of those differences in distance. And then, you know, of course, you'll notice there's also this weird W thing in there. Don't worry about it. I don't use it. So, but it's essentially because we're summarizing over the whole field, it has these boundary effects and these positional things. It changes the value, right? So that was, it's not real bad, but it does give a different answer depending on where those two circles are in the field. And that's because of the summing over the whole domain. Turns out if you do set it to infinity, you get one of the earliest proposed measures. So Baddeley was designed to fix this measure. And although this measure is a special case of the Baddeley. And really what they didn't like about it is that it's highly sensitive. So if I remove this little part from set A, suddenly I get a whole different answer, right? So it's highly sensitive to small changes, which means that it's really, really good for rare event, for analyzing rare events, because you want that high sensitivity then. So there's that. Now, mean error distance is one that I really like. Just back when I was just playing with a lot of these methods, the only one I found useful, to be honest, was mean error distance. And so that's why I wrote the paper about it. They didn't like mean error distance in the beginning because it's not symmetric. And I'll talk later about why I like that it's not symmetric, okay, for our purposes here. But what it is if I'm looking at the mean error distance of A and B, I'm going to take all the points in the set B and calculate the shortest distance to the nearest point in the set A, and then take the average of that. And because I'm only averaging over points in the set B, it doesn't have those positional problems, right? So it'll give you the same answer regardless of where those circles show up on the field. And then of course, if I turn it around, then I take all the points in A and calculate the shortest distance to the nearest point in set B. And so what that does is if one's an observation and one is a forecast, in one direction, you're getting information about the false alarms. And in the other direction, you're getting information about misses. And so that's why I like the lack of symmetry there. And then I came up with a couple measures to kind of fix a lot of the problems that we were discovering. And as we came up with these measures, 3 minutes, okay, wow. Okay, so just quickly, if I take that's all right. If I take the number of points in A that are not in B, and the number of points in B that are not in A, that's the symmetric difference in the sets. So I basically take that and then a weighted average of the two directions of the mean error distance, multiply them together, and you get a really big number. And so you need to contain that somehow. So one idea is you take the cubed root, which gives you an area. And then I learned or realized later that Baddeley, Hausdorff, all those give you units of grid points and not grid points squared, and that it would be kind of nice to have them in the same units as the rest. So if you take the square root of G, then you've got units of grid points. And then for time, I won't go into what G beta is, but it's a unitless, essentially unitless. So it's from 0 to 1. 1 is a perfect score. 0 is not necessarily perfectly bad, but it's your idea of essentially what is not acceptable, basically. And then these measures are nice because these distance maps can be calculated very quickly, as it turns out, because of this distance transform method that somebody discovered a long time ago. So to summarize all these measures, you can see I fixed the pathological problem. That was a big one. So these G measures are the only ones that handle those pathological cases well. No positional effects. So the only one that does is the Baddeley delta because it sums over the whole grid. And again, it's not a huge problem, but it's nice to be consistent. Sensitive to frequency bias. So most of them are, except for centroid. The mean error distance is not, but you look at the two different directions and you kind of get the information. And then useful for rare events, depending on your choice of beta, G beta can be, but again, I would just use the Hausdorff if you're interested in rare events. And then reward partial perfect match, you can see which ones do the Baddeley and the mean error distance depending on directions, right? And then correctly penalize is the opposite, right? So that's just kind of a summary of those cases from our paper. And if you're really interested in this stuff, you can go read the paper and all the other cases and what we found. And then some of you may have seen from a paper in the early days when we were doing spatial methods, we came up with these cases. So the green, they're all the same intensities for my purposes, but the green is the observation and then pinks are different forecasts, you know, right? and so the 1, 2, and 4, I'll give the same traditional verification measures, right? And then you get different for the ones that are bigger. And in some cases, this one's the best, which is maybe okay because it's the only one that overlaps. But looking at how some of these different methods rank them, this is kind of an old figure, so my notation is different, but this one's Hausdorff method. Did I say that right? So the best is the one that looks most like itself. And it gives that one to be the worst. And you can see with the mean error distance, so it doesn't like this one. Sorry, yeah, that wasn't the example I wanted to look. I wanted to look at this case. So in one direction, that's the best. And in the other direction, it's one of the worst. And that's that, you know, miss. So if you're coming from this and looking at the other, you did really well, right? So there's not a lot missed. But if you're thinking false alarms, and so you're looking from this to the other, then it's really bad. And so that's that false alarm versus miss. I think I'm going to kind of ignore this because I'm running out of time and I messed up. These were old data and I forgot what things were. And so we're just going to ignore it. But that's a real, you know, cloud reanalysis from a particular day. So anyway, just to summarize, I think that the spatial dissimilarity measures are relatively easy to understand. I mean, you know, there's some spin up to learn what they do. They're fast to compute, so they can be done operationally, for example, or just, you know, it doesn't take forever to do. You can get your results quickly. So I think for cloud, where it's pretty easy to choose a threshold, at least the cloud amount. I think they're especially useful there. And you can use them within more complicated methods if you want to, like mode, and they do, right? Centroid distance. And, you know, some of them give complementary information to each other. So, you know, like I say, it's good to use more than one. It's also good, I think, to use frequency bias. It's a very simple measure from the traditional that I think gives useful information in this case. There's my software package in R, and then of course the Met software has these methods all in there. The only other thing I'll say is just from watching this morning, I realized like something that would be really nice is to look at the 3-dimensional so that you also have the heights and things in there. Now mode has the time domain, which has these 3D objects. But as far as like comparing with different cases, I don't know if anyone, I haven't seen that. I haven't looked for it. So I don't know if that's been done. But that'll do it, I suppose. Is there time for questions or did I?
Actually, we only have 1 minute for a quick question before the next talk, so we're on time.
You kind of touch on it a little bit especially with mean distance and the fact that you're asymmetric and how you can use that, but just the idea, instead of coming up with a measure that completely answers your question, a set of measures that each focus on one way that they can be wrong. Right. And then the user can combine, you know, weighting according to what's important to them. Yeah. I wonder if you've thought about that.
Yeah, I've tried like different things in like kind of the mode type of framework using spatial VX because it's real easy to mix and match things and do. And yeah, I haven't played with it all that much, but I do think that's a good idea to do. You know.
We have our next talk is Sarah Griffin. Her talk is verifying cloud forecast with satellite brightness temperature. She from CIMSS, University of Wisconsin for Madison.
Yes. All right. Good. I figured out how to get this. All right. Hi, everyone. We are almost to the end. So I'm going to talk about verifying cloud forecasts. And I do this with satellite brightness temperatures. So I know we asked the question yesterday, what is a cloud? Well, in my world, a cloud is visible from satellite imagery. And so if I look at this image, this is after a dahlia made landfall. Based on visible imagery, it's very easy to see what is cloudy. Unfortunately, this is only available during the day. And at least in my very limited experience, I tried to simulate this once, it didn't go well. So we like to use brightness temperatures instead. So this is an example, same time, this is the band 13, the 10.3 micron. And this is something that we can compare to models. So bring it up. Here's an example of the HER forecast, 2-hour forecast from 13 Z-val at the same time. It's a pretty good comparison. It passes the eye test. Unfortunately, not all models can do that. This is an example of the Rufus from the same time. It doesn't look nearly as good. And so different models, different parameterizations, different initial conditions can give us different results. So, and that's the motivation for this talk is how can we look at different models? Like we can look and see, does it pass the eye test? But I'm not going to look at the, whoa, go back. I don't think I hit anything, but anyway, we're not going to look at the eye test for everything. So how can we do this statistically? So some of the work that we did, this is using the 2019 and 2020 hazardous weather testbed data. And this was very nice because they're in multiple models for the same time. And a lot of the stuff was very similar. So like, especially we're gonna look at a lot at 2019, we have this control simulation. And it's not called the control because it's what we're trying to beat. It's called control because it has something that every other model listed here either has one or in some cases down here, 2 things that are different. So we can compare to the control and see exactly how each thing impacts, like how does microphysics scheme, if we change it from the Thompson to the NSSL, what does that do to our brightness temperatures? So looking at some errors, this is really slow. If you're identifying errors in simulated brightness temperatures, you can do basic, I don't want to say basic, but traditional pixel measurements. You can do your mean absolute error and your mean bias error. And you can learn a lot from this right away. Like if we look at the mean bias error, we can see that this red, which is the MP-NSSL, it has a high bias. It produces warmer brightness temperatures than the Thompson scheme does. This green one down here, that's our LSM-RUC surface min. It produces a low bias. But that doesn't tell us anything about displacement. It doesn't tell us anything about the number of clouds. You can kind of infer, but we don't know that. We can also look at trying to split it into clear and cloudy pixels. This is only available, we can only do this because we're looking at May. So I'm going to assume that there's no snow on the ground. I live in Wisconsin, we have gotten snow in May, but it didn't stick. So I'm going to assume there's no snow on the ground. So if we take a cloudy pixel, just say it's lower than 270 Kelvin, over here is our mean bias error. If we break that into cloudy pixels, we did the mean difference here, and we have to do a mean difference because we have different number of pixels, but we can see that every single model does have a cold bias. The brightness temperatures are lower for cloudy pixels. But we're still not entirely sure why. Are there too many pixels, or is it just related to the simulated brightness temperatures? Are they just too low, even though there's a correct number? So one way we try to address these questions is we like using, we've heard about a lot, using mode to make and analyze objects. And again, mode defines objects in both forecast and observations. So this is an example of a GOES forecast, this is GOES 16, from 2019. And then we made these objects here using a threshold of 235 Kelvin. So those are gonna be our objects. Obviously you could do this with any threshold. We chose this because we were going after the coldest clouds in this example. So what are some things we can do? We can go back to our pixel estimates, but now we have objects. So let's start with some paired objects. Obviously the objects are displaced, no surprise, but we have centroid distances. and centroid locations. What happens if we, there we go, overlap the objects? And then we can kind of get an idea of mean bias error and mean mean absolute error without a displacement. So we have our images from the previous slide. And if we do it with just objects, there we go. I had a fun dissolve in there, and this doesn't come through apparently. But as you can see, like, it's a much messier system, and we still get these errors of down here, the NSSL still has higher brightness temperatures. LSM Ruck, this green one, is still lower, but we're more closer to the zero line. But this is only for objects that have a match. It doesn't account for objects that don't have a pair, either in the forecast or in the observations. So let's use more stuff that mode provides. Mode provides when you make an object and they do these object pairs, they create an interest score. And it pretty much tells you how good is the match from a scale from 0 to 1. And you can give it any sort of weight that you want based on certain predictors. So like centroid distance, what we just heard about, I thought that was important. I gave it a 4. Boundary distance, I gave it a 3. I thought it was slightly less important. There's convex hull and angle difference. I'm not going to look at very much. I gave them a value of 1. And then we finally have area ratio, which is just the ratio of the objects, their sizes, and the intersection area ratio, which is how much the objects overlap. So with this interest score and with area sizes, we like to calculate the object-based threat score. Basically, because what it does is it takes the area of all objects, the area of paired objects, and multiplies it by this interest score, a value of 1 being perfect. So if we look at our results from 2019, okay, somehow I just hit my step goal standing here. Yay me. If we do this comparison, we have control on top, and then all of our comparisons, we can see first that forecasts are more accurate in the forecast cycle early than late. No surprise there. But if we do this difference from the control, like I said, everything is slightly different, which is why we difference from the control. We can see here that this PBL-SH, this is a Xing-Hong PBL scheme. At least early in the forecast, it creates more accurate clouds than the min forecast does. We can also see down here, this LSM or the LSM Ruck forecast. They always have the steepest reduction in OTS. So why is that the case? Well, let's look at the number of objects. Look at the number of objects. Again, we're looking at like this green and this orange. You can see that they produce more objects than any other model setup or the observations, especially later in the forecast hours. They also produce more object area than other model setups, especially later in the forecast hours, which is when we saw this reduction. So if we take our object-based threat scoring side to tear stuff apart, one thing I really like to do with stuff is tear it apart to try to figure out what the hell's going on. So if we kind of break it down into components, here we have the percent of object area being matched, the percent of forecast area being matched, and then our average interest score. And we can see here is that this LSM Ruck, this Ruck land surface model, for some reason is producing many more forecast area like we saw, and it's reducing this percent of forecast match. And that's one reason why we're seeing a reduced OTS. So great, we figured out why the LSM Ruck model surface min is producing a lower OTS. Great. What's going on here? Like if you look at this, we have a local maximum and average interest scores around 24, forecast hour 24 and forecast hour 48. These are all initialized at 0Z. So this is around, 0Z the next day. What's causing them? I feel like when I was doing this, it kind of reminded me of my toddler, but why? Why, mommy? Why? Why is this happening? So we can look at the interest scores even more and break them down even more. Up here we have that same graph, slightly different x-axis. We have our comparison of interest scores. This is the average. Again, we have our 2 local maximums. What we can see here is that in our centroid distance interest score and our boundary distance interest score, we have the same cyclic nature. We have an increase in these interest scores at the 24-hour forecast and the 48-hour forecast. But we don't see them in the area ratio and the intersection area ratio nearly as much. So what's going on? Going back to the total area, I didn't mention it then, but if you look back at it, maybe squint your eyes, turn your head slightly, you can kind of see we're getting the cyclic nature and the total area of these forecast objects, again, especially at the 24 and the 48 hours. But if you look in the observations, that cyclic nature isn't really there as much. Maybe it is a little bit, like we got a little bit of it going up here, but it's not nearly as obvious as it was. And so that's why we think that we're getting the cyclic nature in the centroid distance interest scores, because we have larger objects. If we go back, no, let's see, can I go back? These objects are much larger. You can see the observation objects are this gray bars are much lower. We have these larger objects, which is maybe artificially impacting the centroid distance interest score. Like we just heard from Eric's talk, you know, it doesn't really count, the centroid distance doesn't really count for object sizes. So it's not including, or it's not noticing that. But since we don't have it in the observations, we get that artificial increase. But since we don't have that cyclic nature in the observations, we don't see that in the area ratio or the intersection area ratio. It shows up a little bit in intersection area ratio, but it kind of gets lost in the noise. But in the actual area ratio, you don't see it because forecast objects are getting larger, the observation objects aren't. So if anything, you're going to see a local minimum at that time. So just some conclusions. I feel like I went really fast, but that's probably good for timing. What we decided to use in a lot of our research is that we use simulated brightness temperatures as a proxy for these clouds. And when we have our simulated brightness temperatures, we can use traditional metrics like mean absolute error, mean bias error to verify these forecasts, but they don't account for displacement between objects. If you have two objects that are perfectly matched that happen to be offset, you're going to get mean absolute errors and mean bias errors that are off. So we can also calculate the mean difference though based on the, thank you. Calculate the mean difference based on the threshold for a cloud. That's all I'm going to say on mean difference, but I'd use mean difference a lot in the work. I really like the mean difference. And then we can use mode then to define objects in brightness temperature imagery. And by doing that, we can remove this displacement and check brightness temperatures when we actually have objects. That doesn't account for added objects. But by calculating the OTS and then its components and breaking it all down, we can see why are we seeing a decrease with that RUC LSM compared, and that was compared to the NOAA land surface model. And you know, why do we have these local maxima and interest scores at 0Z? So with that, I actually finished on time. Yay.
Let's round for a few more questions.
Yeah.
Great. Yes.
Yeah.
So, great work.
Thanks.
Do you have any plans to move on to the region, like Monterey?
Our current plan right now is trying to take this. We started with using the HER and now we're using Rufus to look at radar reflectivity and brightness temperatures. We have not looked at going into microwave. In theory, a lot of the methods will work though, because it uses mode, and mode is pretty much just, you know, get a threshold for objects, make the objects, and then do the analysis. But we don't have any plans at the moment, but that's something we could definitely do if there was interest.
When you select the brightness temperature for comparison, do you consider involving a similar brightness temperature to your actually observed brightness temperature?
So we don't actually simulate the brightness temperatures. We get the simulated brightness temperatures from the model, but when we do the mode objects, they are all based on the same analysis. So it's like we use a convolutional radius of 5. When we do our analysis with the HER, we have to do some sort of a little bit of tweaking because HER is the GOES 13 brightness temperatures and we're using GOES 16. But otherwise, everything is the same from the same that we get from the model.
Oh, yes, your question first, yes. Then you sorry, yeah, very simple. It's a similar question. Like, guys are simulating visible channels and do any comparison?
I simulated visible channels once for a different project. I was using a nature run and they were trying to simulate, make visible imagery of a hurricane that was a fake cloud. It was a fake hurricane, which confused me because I'm just like, this isn't lining up. But I only did that once. And it was, in my experience, very difficult. Now, I'm not very experienced with the CRTM. I kind of did it by the seat of my pants the entire time. But I think that could be a reason why, like, HER doesn't produce simulated visible imagery. I don't think Rufus does either, but if you can, Rufus does? Okay.
It's RRGMP output 6 microns and spits out that, I thought.
Is it better than their IR imagery?
I really don't know what they're doing there, but what you showed for that hurricane, it just makes me think there must be a code bug. I doubt it's that bad. But
I hope so. But Yeah, I mean, I didn't make it, but her stuff I made, like we run that in real time. Rufus stuff I didn't make on the fly, so there's a chance I messed something up there too, definitely.
Is they actually just take the band that's in our RTMG that most closely matches 10.8 micron or whatever, and they output that. So that's not CRTM.
Okay.
One would assume if they were to throw the hydrometeors and all the other variables into CRTM, you get a very different view potentially, since our RTMG does not equal CRTM.
Okay. Yeah, I've recreated her simulated brightness temperature to get Go 16, but I've never like recreated the Rufus.
Right.
Jason.
Okay, that was quick.
No, we have time.
Yeah, I think I
go
fast.
Yeah, we have time.
It's kind of related to Honey's question. Could you comment a little bit on why you chose the convolution of radius and other parameters? What was your goal to comparing it to the original distribution of
Yes.
why did you choose the parameters you did? That's hard.
It is hard.
Very user.
Now I'm trying to find the slide where I had it. Sorry. There it is. I know I was going to put out an order. So these are parameters that we chose a while ago. So initially we used a convolutional radius of 5 because we wanted to get smaller scale. Usually the research that we have done so far has been like the really cold clouds. So 235 Kelvin is what we use for this research. Other research we use, we took the 10th percentile, the upper 10th percentile, use that. So we go with 5 because we wanted to be very small and get those very small clouds. The reason why we chose this, especially, central distance has 4, but boundary distance only has 3. And those numbers were specifically picked because if you have boundary distance, let's say you have a very large object and a teeny tiny object. And if they happen to be overlapping even a little bit, your boundary distance is 1. But obviously, like there is still a lot of distance between the two objects. So even though centroid distance would be artificially inflated, especially compared to like the mean error distance, boundary distance is even more artificially inflated. So that's why we gave it a slightly lower value. Same thing for the area ratio. If I have a large object and a small object and I have, slightly overlapping, you're going to have a very high area intersection ratio because so much of that smaller object is encompassed in the larger object. Now, if you did it in the opposite, and obviously you did the larger object compared to the smaller object, you'd have a small number. But what mode does is it finds the highest value in that pair. So that's why we gave it a slightly lower value. And again, I have run mode, and there was one time where I gave it an area ratio weight of 1 and everything else was 0 because that's all I care about. But you got to figure out what is it that you care about. But that's why we give it a slightly lower value instead of making it equal. We want it to be slightly less important. Sometimes it's not the best thing because then when I go and break stuff down and then your attribute weight can be 0.25 and then 0.187 and then you're trying to explain to a reviewer why it's slightly lower. And that's okay, but.
It'd be nice to have a consistent list of accepted values so that we can all compare with different.
Yeah, like every paper that I publish, I would make sure that this table is in there so you can replicate it. Also, if any paper that I publish, odds are it's this exact table because I decided on this years ago, like 2015 years ago, and just kept going with it. But that's why we initially made the changes that we did.
Our next talk would be Jason Otkin from University of Wisconsin-Madison. And his talk would be using satellite or sky infrared brightness temperature for model verification.
Thank you. All right, good afternoon, everybody. Okay, so in this talk, I'm going to discuss results from a few projects that we've done over the past decade, where we've used all sky satellite infrared brightness temperatures to assess the accuracy of clouds and water vapor within high resolution model simulations. So this work is going to build upon what Sarah presented in her talk. First thing I want to do though is to spend a minute here discussing the utility of satellite brightness temperatures for model verification. So various sensors on board geostationary and low Earth orbiting satellite platforms provide detailed information about the atmosphere and also the state of the land and ocean surfaces. So this information is obtained from a large selection of visible shortwave, infrared, and microwave bands. But for our work, we've primarily focused on all sky infrared brightness temperatures because they provide very valuable information about clouds and water vapor. And, as we've seen many times during the past 2 days, these two fields can be very susceptible to large errors in NWP model forecasts. So anything that we can do to make better use of the information provided by these infrared observations could lead to, much more accurate forecasts. So I want to start out then by discussing results from a couple of projects that we did a few years ago, where we assessed the accuracy of the cloud and water vapor fields within high resolution model forecasts, in this case from the HER model. So the first study looked at results from a 24-hour case study from July 2015, and we used it to assess the merits of different verification methods when used with the all-sky infrared observations. So we used observations from the 10.7 micron window band because they are sensitive to cloud top properties when clouds are present, but will then see down the surface when skies are clear. And we assessed the forecast accuracy using a variety of methods, including grid point statistics such as RMSE, neighborhood-based methods like the fraction skill score, and then also object-based tools from MODE. Now, I want to point out here that the use of traditional neighborhood and object-based verification methods, in combination should provide a more complete analysis of the forecast accuracy than you can get if you just look at one of those metrics or methods by themselves. So this particular case study, again, looked at a 24-hour period, and it was chosen because it contained different types of convection across different parts of the United States. So this included widespread severe convection across the north central U.S. in the red box, and then there was more isolated convection in the central U.S. in the black box, and then a third area of widespread severe weather reports and mostly wind reports across the southeastern U.S., and that was associated with stationary front and sea breeze circulation across that part of the country. So one of the ways that we assessed the forecast accuracy was by computing the fraction skill score, which is a neighborhood-based verification method that can be used to determine at what spatial scale a forecast has skill. So for this project, then we used the 10th percentile of the observed and forecast brightness temperature distributions as the threshold when computing the fraction skill score, which means that we're focused on evaluating the accuracy of the coldest upper level clouds. So we did this separately for each of the 3 regions, shown on the top panel again. And then in the box the bottom diagram, or the bottom image is a box plot diagram, which is showing the range of the fraction skill scores for each of those 3 regions that were computed using all of the forecast times that verified within that 1 day period. So remember, the HER is available at 1 hourly output frequency. So in that bottom panel, then you can see that the forecast skill or the fraction skill score increases from left to right as you go from one grid point on the left to a spatial width of 101 grid points on the right. That's to be expected. You can also see that the HER model had forecast skill pretty much at all of those spatial scales in the north central U.S. in the red box, a little bit lower skill in the southeastern U.S. in the blue boxes, and then the lowest skill was for the central U.S. in those gray boxes. And on the main reason why there was a different skill for these 3 regions was due to the mode of convection, where the widespread and strongly forced convection in the north central U.S. was the easiest to forecast. And then on the more isolated convection in the central U.S., which was not as strongly forced, was the most difficult to forecast. So then in a second study, then we assessed the forecast accuracy for the HER model using MODE. Similar to what Sarah showed in her talk, we're going to look at this table again. We gave equal a weight to the 2 distance attributes in the top 2 rows compared to the 2 area ratio attributes in the bottom 2 rows. And we chose to give these weights or give these attributes these weights because ideally a forecast should have cloud objects of the correct size in the correct location and at the correct time. So we ran MODE for 2 different 1 month long time periods. These include August of 2015, and then what was it, January 2016. So the top row here shows examples of the observed and forecast ghost brightness temperatures for just single timestamps within each of these 1 month long periods. And then the middle row shows the cloud objects that were identified from mode based on those brightness temperature fields. One of the ways that we assessed the forecast accuracy then was by looking at the number of forecast and observed cloud objects. In this case, plot as a function of time of day. So we're going from zero UTC on the left until 22 UTC on the right. The red boxes are for August, and then the blue boxes are for January. The lighter red and lighter blue are for the observations, and then the darker colors are what we got from the HRRR forecast. So the one of the more notable things here is that there are more cloud objects in August than there are in January. It's important to note that because we use the 10th percentile to define the edges of these cloud objects, they should have the same spatial area in both of these months. So the fact that there are more cloud objects in August means that the sizes of those cloud objects is smaller. And this is consistent with the fact that you just have more convective scale cloud features in during the summer. That's also borne out by the fact that there is a much more distinct diurnal cycle in the number of cloud objects in August. You can see that there's a minimum around 12 UTC and then a maximum around 20 UTC. And that is very different than what we see during January in the blue boxes, where the number of forecast and observed cloud objects remains pretty constant with time throughout the day and the night. And then here we're looking at the number of cloud objects that's plotted as a function of the forecast hour. This is going from the 0 hour analysis on the left to the 12-hour forecast on the right. And in this case, the most noticeable thing is that the 0 hour analyses had way too many cloud objects during August. That's seen by the dark red box being much higher than the light red box on the left side of this image. You can see though that this overabundance in cloud objects was rapidly replaced by pretty noticeable deficiency in objects just 2 hours into the forecast, which continued to become larger with time until about the 4 hour forecast. And then those differences started to subside, so that by the time we got the 12-hour forecast, the forecast and observed cloud objects, object numbers were pretty similar. But what this is showing though is that at least during the warm season, that the HRRR forecast or the HRRR analyses have too many cloud objects, but that they then rapidly congeal into a much larger cloud objects that then lead to a deficiency in the cloud objects by the time we get to the 2 hour forecast. And what these results also show is that's very important to assess the forecast accuracy for different seasons, because if you just look at just bulk statistics averaging across all seasons, it's going to potentially obscure very important signals in your model performance. Okay, and then in the rest of this talk, I'm going to shift gears a little bit and show results from a more recent study where we assessed the impact of land surface models on convection of the Southeast United States. We did this using high resolution model simulations and then GOES 16 satellite observations. So the motivation for this project is that there's a long-standing challenge to forecast the location and timing of convective initiation across the Southeast United States. Now, unlike much of the country where convection tends to be associated with stronger synoptic scale or mesoscale forcing, in the Southeast, they can get a lot of convection during the summer that develops in the absence of any noticeable forcing mechanisms. But the thing is that these storms still make up a very significant portion of their warm season precipitation. So it's very important that we can accurately forecast them. Unfortunately, numerical models tend to struggle with accurately predicting location and timing of the convection. So we wanted to look at, is there a role in the land surface in driving that convection? So geostationary satellites are very important when studying convective initiation because the high spatial and temporal resolution that they can provide allow you to track the evolution of thunderstorms, with very high detail in both space and time. And then, once you can identify cloud objects within the observations and the forecasts, you can then compare their characteristics. You can look at things like the cloud top growth rates and also the brightness temperature distributions. Then if you take that one step farther and say that you're only going to look at cloud objects that have very similar characteristics to the observations. So basically you want to ensure that the forecast objects match the observed objects. You can then use the model simulations themselves to more closely evaluate the processes that lead to differences in the convective initiation, and also the different or the roles that different parameterization schemes can play in the generation and the maintenance of that convection. So for this study then, we ran 2 WRF model simulations. These contained 3 nested domains with the innermost domain containing 500 meter horizontal resolution. They used identical configurations except for the use of different land surface models. So one of them used the NOAA land surface model, and then the other one used the NOAA MP land surface model. So the cloud objects were identified using the object-based identification method that is described in Henderson et al. From 2021. With this method, we use the coldest brightness temperatures to first find the core of the cloud objects, and then we build outwards using successively warmer brightness temperature thresholds. And this process is performed iteratively until a cloud boundary of 285 Kelvin is reached for a given cloud object, or when two cloud objects intersect with each other. Okay, so here I'm showing a comparison of the cloud top characteristics for these convective initiation cloud objects. These are shown over a 3-hour time period. So it's going from 17 UTC on the left until 20 UTC on the right. On the top panel shows a number of these cloud objects. The observations are in gray, and then the cloud objects from the NOAA and NOAA MP simulations are shown in the green and blue colors. And then in the bottom panel, it shows a box plot diagram that shows the size of these cloud objects that were identified using this method. So in the top panel, then you can see that that the number of cloud objects is larger in the NOAA MP simulation than it was in the NOAA simulation. This is true through most of this 3-hour time period, and that more closely follows the number of objects that were in the observations. In the bottom panel, you can see that both the NOAA and NOAA MP simulations were pretty similar until around 19 or 1930 UTC, but that then in the last 45 minutes or so, the range of the cloud object sizes became much larger in the observations. And that was accurately depicted within the NOAA MP simulation, but it was not within the NOAA, within the simulation using the NOAA land surface model, where the size of the cloud objects remained more constant with time. So we looked more closely at the evolution of these cloud objects by looking at the evolution of the 10.35 micron cloud top brightness temperatures. So this allowed us to look at the cloud top growth rates within these objects. Now for this figure then, this again is a box plot diagram depicting the average cloud top brightness temperatures within these objects. All the objects were recentered so that the timing of convective initiation occurred at t equals 0 in the middle of this image. So when you look at this image, then you can see that these cloud objects within the NOAA and NOAA MP simulations, again, were quite similar through the timing of convective initiation, but then you start to get some pretty large differences once you get to about 15 to 20 minutes after the timing of convective initiation. And, for example, you could see with the NOAA cloud objects that their brightness temperatures remain quite constant after convective initiation. They stay pretty flat as you move from left to right. But that the brightness temperatures continue to get colder for the cloud objects in the NOAA MP simulation, and again, those more closely matched what was actually observed. Now, one of the reasons for the different cloud characteristics in these two simulations was due to differences in the surface radiative balance. So here I'm showing a time shot or just a single image here of the sensible heating for the NOAA simulation on the left and for the NOAA MP simulation on the right. So what we can see here is that the sensible heat fluxes were larger in general for the NOAA MP simulation within forested regions. That's where you're seeing the yellow and in the lighter green colors. But they tend to be smaller within the cropland and grassland areas, such as that north-south band of lower heat fluxes in the middle of the domain, and then I'm also scattered across the northern part of the domain. I can also see that there's greater heterogeneity within those heat fluxes within the NOAA MP simulation. So those differences in the sensible heat flux then led to large differences in the low-level divergence and also the vertical velocity. You can see that the largest differences in these two fields occurred wherever there were large horizontal gradients in the sensible heat flux, for example, across the east central part of this domain. And then, of course, these differences in the low-level convergence and the vertical velocity then led to large impacts on the higher to medium mixing ratios within these cloud objects. So here I'm showing a time height cross section of the cloud mixing ratio, graupel mixing ratio, and then the rainwater mixing ratio over a 2-hour time period, where the red colors are indicating that the cloud objects within the NOAA MP simulation had more mixing ratio than occurred with the NOAA simulation. So when we look at these images, then you can see that the stronger updrafts and mass flux within the NOAA MP simulation led to much more cloud condensate, and especially after 18 UTC. These results also helped to confirm that we needed higher ice formation and the latent heat boost associated with it in order to sustain the cloud growth beyond the time of convective initiation, and that we got more of that because of the change of the sensible heat flux within the NOAA MP simulation. Okay, so then just to summarize this particular study, what we found then was that differences in land surface models actually had a very large impact on the magnitude and spatial structure of the sensible and latent heat components. This in turn led to large differences in local circulation patterns, large differences in the updrafts, which then naturally led to very large differences in the evolution of the convective clouds themselves. And what this shows then is that more research is necessary to improve the accuracy of the land surface models, because they can have a very big impact on the evolution of convection. And the last thing I'll note here is that, trying to build off of this a little bit, we do have a NOAA project that we're working on where we're using surface sensible latent heat flux measurements. So both from observations and then from model reanalyses to examine the accuracy of UFS S2S forecasts. We want to look at are these models, or is that model able to accurately represent the land atmosphere coupling strength? So with that, I'll stop here. Might be time for a question or two.
We have time for one question for the next.
That kind of the results relate back to Reed's talk earlier, where he was talking about the size of the updraft matters. And sounds like the OMP, the updrafts were larger and more likely to become deeper.
Yeah, that's what happens in the case study. But
we actually have a new project now with through the DOE where we're going to be looking at this again using surface-based observations that they're in the process of obtaining around Huntsville now. So we'll be able to have some more observations to constrain this analysis. Yeah.
Our next speaker is Christophersen. I'm sorry, I couldn't speak your last name. Her title of her talk is that regional cloud forecast verification using traditional spatial and object-based methods.
Thank you, Julian. So can kind of follow along what Sarah and Jason presented in terms of the model verification. So most of the work is using Met Plus as well. But what I'm verifying here, presenting here, is not radiance-based. It's a cloud region derived, physics-derived cloud region-based verification. So I want to thank my collaborators, Jason, especially Jason, derived all these cloud types for this verification. And now we have a contractor, Wesley Davis, working on this project as well. So the main motivation, does it come through? It's a delay, okay. We try to understand how well does the Navy's regional and global model predict clouds. And then there's a lot of buzzword talk about object-based verification. We also try to understand, does the object-based verification offer additional insights compared to the traditional standard grid point verification? The project scope, it's a significant delay from the computer to the projector. So as Sarah and Jason already kind of illustrated in using the MET, and as in particular the mode, there's a number of parameters that need to be tuned. And for this work, I'm not going to present, but we actually tune a number of parameters in the mode in order for our mode cloud verification. And we also have a regional and global cloud that kind of coincide in the same domain. So we're going to use compare some of the verification from the regional model and the global model. But ultimate goal is to try to formulate a set of verification matrix for our potential transitions. So next few slides, I'm going to go through very quick what I mean by the traditional verification, just mostly the contingency table based, where you look at the hit misses, false alignment, correct negative, you derive all these biases and actual threat scores, and etc. What I mean by the special verification scores, in particular the fraction skill scores, as just a neighborhood-based verification. What I mean is by verify different neighborhood lengths that may give the model, show model have some verification skill, some forecast skill, which otherwise, if you verify at a grid point verification, may show model has no skills. And object-based verification. Previous two talk a little bit about what objects, some of the parameters. Here just kind of give you an illustration. What I mean, some of the metrics we're going to use in letter, some of the intersection error, how the two forecast object and observed objects, how much error they intersect, and the other parameter is called the symmetric difference. Basically, they don't overlap, how much error they don't overlap at all. We're also looking at the union error, which account for basically the total size of the objects. And the other, the centroid distance, which the previous three talks basically talk about the centroid distance of the objects. And from this, we can derive a number of derived metrics, such as just, you minus the forecast error, the forecast error minus observed, that give you the quantitatively how much the error they differ. And you can derive the intersection error normalized by the union error that gives kind of how much the ratio, overlap ratio, just another way to look at how much they overlap. And for the object-based, you also can derive the skill scores, which is what the calculation is used the grid points within the defined objects. You can derive those kind of contingency table-based skill scores. And the data set that I'm using is a regional model, is co-Armstrong over the called the Norfolk regions. Mainly the domain is the yellow highlight, the outer domain. The cloud types, different cloud regions, which Jason probably can do a better explanation about how he labels the different cloud type regions, basically is, we consist of 5 different cloud types, where mainly is the low, where it's separated by stable and unstable clouds, and mid and high, and we're also separating the deep precipitating clouds. The 5 different cloud types, they are over this yellow domains, and then we're mostly looking at the forecast initiated at the 12Z, so out forecast to the 12 hours at every 3 hours. So it's mainly for the daytime verification, and MET and mode are used for this verification. So first we look at the object-based verification calculate the skill scores. So the middle 2 panel are the what Jason have calculated in terms of at the grid point verification, in terms of the frequency bias and the actual threat scores. On the most left and most right is what we use, the object-based calculated the threat scores. And I think the message here is the object-based calculated skill scores are very comparable to the grid point skill scores. And the other is looking at the friction skill scores, mainly looking at the stable, showing here the low clouds, the stable clouds on the left and the unstable clouds, sorry, on the right. So different color indicating we basically increasing the neighborhood length scales. So the message here is for the unstable clouds from just one grade point neighborhood to, for example, one of the 11 grade point scale score, the improvement rate is much faster. You know, that's consistent with the unstable cloud. They're most sensitive to the localized errors. This is the object-based in terms of the central distance. So they offer central distance both in the like XY direction or a Y direction. So we plot these two metrics in a one map that give you kind of a joint distribution. So to give you a distance error, and this additional metric that the traditional metric basically cannot offer. So we think this might be an additional insights. What I'm showing here on the top is the stable clouds, discipline error. And each of the orange dots are each individual objects. And the contours here is one of the kernel density estimate functions, and we represent 30, 60, and 90 of the distributions. And the top axis and the right y-axis is basically the univariate distributions. I think the message here is generally the CIMSS, they place the clouds in the right location, and then there's slightly showing the east to west propagation errors more than the north south direction. So next, so this is looking at the object error size. So on the top is looking at these forecast, the observed object error size varies over the over the 12 lead times. So this is showing on the unstables, and then the bottom is showing the error difference, right, where the observed error minus the forecast error minus observed. So that basically give you quantitatively how much error they differs. So the message here, we see the box basically plot for the error that over the throughout the day that's showing kind of a slightly diagonal pattern. And then CIMSS generally forecast the first till 9 hours is decent job, but the forecast lead at 12 hours showing the larger error difference. And I think this is largely due to the observed clouds that we verify against has a potentially larger biases at the less optimal sunlight times. And this is for the stable clouds verification, and throughout the day, basically the object error this remains throughout constant, and generally CIMSS showing under prediction of the cloud errors. And this is consistent with some of the skill score that the frequency bias is negative. So next few slides are going to show the global and regional, they basically over the same domains. So on the left is the Navy's global model, the NAVG model, and on the right is the regional models. So the middle is basically where the mode identify the clouds. I think the immediate messages here, the global model, they tend to show a very, very large objects as compared to the regional model. And the other caveat is to when you, even though you verify using, in this case, we're using the same observations, but how the modes, they match the two, the forecast and observation, you can see that they basically give you different object definitions. So the results here is showing the overlap ratios. So for the regional cloud, for the global and the regional CIMSS, I think the immediate message is the global model showing up very less overlapped errors. And this is mostly due to the, the symmetric difference, which is they don't overlap, is much larger for the global model, even though we're normalized by the union error, basically the total error. And the last one, I'm just showing this global model, the displacement error on the top for the global model, and then CIMSS is on the bottom, and immediate message is the global model basically showing a much larger spread for the displacement errors. So in summary, basically we're using the verification, looking at both the standard, spatial, and object-based verification that try to give you a kind of different way to look at, evaluate the model performance, and overall they're a complementary way to look at model performance. In some other ways, they actually can good for us to detect some of the bugs in terms of how to process the label of the cloud regions. Generally, our original model, they predict the cloud location well and showing a very low displacement error as well as a good, decent skill scores. And the global model, which is showing a poor performance, largely due to the model resolution is much larger, as well as the model physics is parameterized. So this is what we had originally for the direction for the past 2 years. We have done this regional and global at the same domain, and we originally tried to look at the global ensemble, but that direction might be changed depending on different research focus. So with that, I'll happy to take any questions.
We have time for questions. Jason?
So I noticed after watching Lisa and Sarah's talk, I wondered if there's the idea to combining objects, the way we did. It's almost a question for you two as well. Did you combine multiple cloud shields in one object, or did you just look at individual cloud shields?
I use clusters, and like if you look when you had your examples and you had the dark outlines, those are the clusters. That could be multiple objects in one field combined to multiple objects in another field. So yeah, when I did interest scores and stuff, I would use clusters when possible. And then simple objects. After like calculating the OTS, I would start with the highest interest scores, which were your clusters, and then after going through those, I would do any single objects that still didn't have a match.
So you're saying that your clusters were dependent on models, even the observed clusters were different. Is that the general thing with load, or is there a way to control that?
Good question. What I guess was you guys using? So in this case, the regional and global model that we're feeding this different forecast model, but the observation we verify against is the same. But mode somehow give us different, objects, so that give us idea of how mode define the merchant matching process. Is
I think what you're asking is what you're explaining. And it does depend on both fields.
Yeah.
So if you go to a different field, it's going to compare possibly different clusters.
Well, and looking at this photo, I wonder if it's just the different resolution.
Yeah.
If you say, look at the object in southeastern New York, it's a lot bigger in the collapse than it is in the nav gem.
And so I want to clarify the model, the forecast model, they're both integrated at a 5-kilometer resolution. So they are the same resolution in terms of the correlation.
But the model output.
The raw model output, there are different resolutions. The raw model comes much higher resolution, and then NavGen is like 50 kilometers resolution. So the global model is integrated to this 5-kilometer domain.
So one thing that's interesting with mode and that we run into problems with is, when you give it mode, you give it a forecast and an observation, and it will make your objects, as you can see, based on your forecast. One thing that we found when we wanted to compare the same observations, different forecasts, is we actually had to flip those. Even though it said forecast, you gave it the observation, and because then it would pick the clusters based on the observations because it thought it was the forecast.
We actually did that test and get the same result. Yeah.
Good. It's very confusing when you do it though.
Exactly that. We figured we tricked the software and put this observation and forecast, see if it could give the same answer. It actually give the same answer.
I was surprised to see that the average errors, displacement errors of the objects were 0.
Why that surprise?
Models have timing errors, location errors. I wouldn't expect it to. I'm surprised there's not a systematic bias towards.
Yes, but and then I follow with his question is what is the smaller, because we compare objects. So what is this? Do you try to test this? What is the smallest size of the object that the method is still accurate? Because the bigger the object is, the easier for you to compare, but what is our limitation, how small of the resolution? How small of the object compared to the resolution? That this could give you a correct answer.
Yes, clustering is.
Yes,
Yeah.
yes.
But Matt, these are 3 to 12 hour forecasts. We don't expect cloud forecasts to be that bad in 3 to 12 hours. They're gonna drift a lot worse, but 3 to 12 hour forecasts, it better be pretty good. So this was a short term.
Yeah, those are only out to 12 hours, so it's short term forecast.
But do you think about that, like how small, how big of the object compared to the resolution when we have the class comparison? Because if the object too small compared to the resolution, what will happen?
That's one of the things about the convolution radius that we can test on that. I think that can give you obviously some insights. Like this is one of the mode before I didn't present this slide, but when we tune how you convolve the original raw field, I guess that can show you how much it represents the original raw field. That could give you some insights. And I think there's some paper on that work to represent the raw fields, depending on how much you convolve the raw field. Sure.
And our next speaker will be virtual and Zoom phone from Pacific Northwest National Laboratory. And his talk is about PyFlex, an overview of the Python feature tracking software and research applications.
All right, thank you. Can you hear me okay?
Yes.
Okay, great. Thank you for the opportunity to present. I'm sorry I couldn't be there in person. So today I'm going to give an overview of this new feature tracking software package that we recently developed called PyFlex Tracker. I would like to acknowledge a list of my co-authors, many of them who are at the same lab as PNL, and this work is funded by several projects under the Department of Energy. So, right, what is PyFlex Tracker? Right, so this is an open source Python-based framework designed to primarily track atmospheric objects, primarily working with 2D data sets. This is a general feature tracker, so you can basically track any objects of your interest, but it has some specialized capability to track convective cloud systems, particularly in high resolution data sets. It works with multiple variables. Here's sort of a schematic here showing you can, if you're interested in cloud, you can do that, or if you're interested in rain within clouds, you can track them as well. It has multiple different kind of object identification algorithms, so it works on different data sets and different scales of the clouds that you're interested in. We treat merging and splitting explicitly in the tracking. And we've done quite a bit of work to optimize this package to run on large data sets with scalable parallelization. So you can run it either on your laptop or scale it up to HPCs. And we also keep building many visualization and statistical analysis tools and Python notebooks to help the users to analyze the tracking outputs. So this package ultimately, our goal is to facilitate advanced model evaluations by extracting the most relevant storm statistics. And if you're interested in knowing more details, we just have a paper published on GMD, and that code is publicly available on GitHub. So currently, the capability of PyFlex Tracker, and I'll show some examples, we can track individual convective cells using radar observations or model simulations. Here's an example of applying tracking on next-gen radar data, tracking individual convective cells. And scaling up a bit, we can also track larger convective systems like mesoscale convective systems or MCSs using either satellite or geostationary satellite data or model simulated OLR. Here's an example of a continental scale tracking these larger convective systems. And then we have capability of using optional co-located precipitation or 3D reflectivity data to further identify these robust MCSs documented in our previous work. And as I mentioned, it's a general feature tracker, so you can track things that are not necessarily clouds. And we have some built-in some tools using image analysis technique to different ways of defining objects of your interest. And here is an example showing we're tracking basically height anomalies, geopotential height anomalies in global reanalysis data. I mentioned that we have lots of sort of visualization analysis tools to help the users use the tracking outputs. So here is an example of a visualization of looking at the WRF simulated cloud top temperature that tracked MCSs in these color shaded objects. We provided a lot of sort of one-step demo scripts where demonstrating basically different types of input data, for example, radar data sets, satellite, model simulations. So the demo strip, basically you run it, you would download the sample data, run the tracking, and produce these visualizations to look at the outputs and demonstrate how you would what you would get basically. And we also continue building a gallery of these statistical analysis tool sets, notebooks in the form of Jupyter notebooks for those who are familiar with Python. So here's some examples of that, where you can compare, observe, and model simulated, say, MCS track densities over a period of time and look at their differences. You can look at diurnal cycles, for example, here as a function of time and longitude, validating, comparing observations and simulations. We have MCS statistics, for example, here looking at composites of the time evolution of, so composite of evolution of MCSs, sizes, lifetime, rainfall, etc. Lots of these different types of statistics. And we continue to add this as our research builds on these tool sets. So in the next few slides, I will highlight some examples of our own research applying these tracking tools. Here's the first one where we are tracking convective cells with radar observations over South America, well, in central Argentina. This is a DOE field campaign called Cacti. Here, this example shows that we have a radar set up at a location that have very frequent convection initiation because of a terrain in there. So we develop a cell tracking database using the radar data set, and then we co-locate it with geostationary satellite cloud property retrievals and the nearby sounding observations to derive a lot of environmental metrics at the time of convection initiation and tag it to each of the track cells. So for example, here's a time series of an individual cell that you can pull out, that you can look at the time evolution of the cell in terms of the size, the depth, and then the different kind of environmental metrics at the time of the convection initiation. So we have a database of this released. And using this kind of data set, sort of multi-platform observations, we try to quantify the environmental controls of the deep convection initiation, or CI. And here, in this figure, we shows that, so the contour is the terrain, and this is where the site is located, on the radar is located. And the color shading is sort of a heat map of the cell initiation locations. So we found that during the field campaign, most of the CI occur very close to the peak of the mountain range, just a little bit east of that. And then when these cells grow wider and develop deeper, and they move eastward to the lower lands, where you see the maximizes in the size and the depth, showing how they evolve in time. And then because we have these co-located sounding measurements, we then can look at what kinds of environments that can differentiate CI. So in this example here, we're showing composite sounding profiles between all CI events in green and then the non-CI events in red. And so we found that for the non-CI events, they tend to occur in a much warmer and drier lower troposphere compared to CI, suggesting that the entrainment-driven dilution processes are very important in controlling whether you have CI or not. But then if you look at those that do have CI, and then sort of compare the ones that are relatively shallow versus those that are deep, which is to the right here, we don't really find a significant difference in sort of the initial environment. So right now, we are leveraging the simulations at high resolution LES scale from the ARM program to further look in these processes. Stepping up in the scale a little bit, we've also used this tool to produce a continental scale size of an MCS tracking data set here. This is over CONUS. We produce this MCS tracking data by combining the geostationary, so GOES satellite, cloud top temperature data, and the 3D NextRad reflectivity data along with the radar-derived precipitation. So the MCS data set, currently we have about 18 years. This is hourly and 4-kilometer resolutions. We have, besides these tracking, we also have convective stratiform anvil classifications, radar echo top heights, masks, and things like that. We also have a different version where we include both MCSs and isolated deep convection. And so this QR code here would point you to, these are publicly available tracking data sets that if you're interested in using that. And then using, because with the tracking and co-located multiple observations, we have a suite of the MCS properties for each of the tracks. And here shows an example of one individual tracks. Obviously, we have the location and timing of the tracks, but because of the radar data set, we also have convective stratiform sizes, their rainfall, the vertical depth of the convective features, the precipitation associated with it, and a lot of other statistics available. Beside these tracks, we also have masks of the MCS tracks on the 4-kilometer grid, so that they can be easily used to derive additional quantities of interest. So with this kind of tracking data set, we've looked at regional contrast in the MCS characteristics. So here we broke down the eastern CONUS into sort of 4 different regions, and this is showing the seasonal cycle of the MCS, number of MCSs. We found a fairly strong seasonal cycle in the Great Plains. But then we see a fairly clear regional contrast, which is shown in different colors. So for example, if we look at the composite evolution of the MCSs between spring and summer, we see that, for example, in the Southeast, during the spring, the MCSs produce much larger amount of rainfall than the Great Plains. But then if you look at the sort of proxy for convective intensity using the depth of the echoes, we can see that the Great Plains, the MCSs that occur in the Great Plains, particularly in the summer, has much more intense convection. If you look at how much the depth of the echo reaches compared to the Southeast. And then here's an example where we combine the MCS database with the NOAA flood event to look at the impact of MCS on flooding. So here, this is showing the fraction, the color is showing the fraction of the MCS related floods for slow rising floods and flash floods. So anywhere you see these darker colors, basically saying that MCS has dominated the flood events. And for this is during the warm season. And so this plot here shows the frequency of floods by month, and different colors, again, showing different types of flood. And then these hatched bars are showing the floods that are associated with MCSs. So you can see earlier warm season, it's mostly dominated by MCS, while in the summer season, it's about half and half. And we further looked at the MCSs that are clustered, meaning that you have multiple MCS occur closely in space and time. And what we found is these cluster MCSs are more effective at producing floods because they tend to have larger rainfall area, wetter initial soil conditions, and also and then resulting in greater runoff compared to those isolated MCSs. And so these are some more recent work in connecting the surface flooding with MCSs. And then we further asked the question of how might these flood producing MCS, cluster MCS change in a warmer climate. So here we apply the tracking to quantify future MCS changes using convection permitting simulations. Here we chose an event that occurred in 2015 that result in record-breaking flood in the Southern Great Plains. So here's observed MCS rainfall during that period, and we run a WRF simulation using the historical conditions, and the simulation reasonably reproduced what was observed in terms of the MCS tracks and the amount of rainfall they produce. And here is when we apply a warming signal to the simulations to simulate what if a similar event were to happen in the future, what would happen. So anywhere you see these green colors is a pretty significant increase in the MCS rainfall with the future warming. And the reason we found is under this future warming, we see a more favorable environment. That's so shown here, where we look at the distribution, and just an example here for the most unstable CAPE, so convective available potential energy, about 60% increase, and about 30% increase in the precipitable water. That results in the MCS having much wider and stronger updrafts and increased convective rainfall volume. And this figure here, we also found that these stronger MCS produce up to about 3 times increase in extreme rainfall over the central SGP area, while the weaker precipitation, so the stratiform rain frequency, is reduced. So the implication on flooding is that these more intense and concentrated convective rainfall in a warmer climate could potentially increase the flash flooding probability. And so this paper is currently in review. And then
interrupt, you have 2 more minutes.
Okay, thank you. So I'm just briefly going to talk about recent work. So we then apply this to a global satellite observations to derive a global MCS tracking data set here, basically showing where we see MCS most frequently, and this bottom figure here shows the percentage of rainfall that the MCS contributed. And we've been sharing this MCS data set with a lot of research groups. And more recently, we are starting to look at how does the global storm resolving models simulate these MCSs by applying this tracking to the diamond experiments, where we have many different kinds of global models at convection permitting scale. And just this is my last slide. We find a pretty surprisingly diverse range of the frequency of tropical deep convective system of MCSs in key climate regions. So that just because these models can resolve deep convection doesn't mean that they can converge. And the model typically tend to produce too much intense rainfall and then not enough stratiform rain. And so to summarize, we showed that we developed this tracking software package that can be applied to both observations and simulations. And we show that by combining the tracking with other complementary data, particularly model simulations, would enable a wide range of research topics. And I'm currently organizing a community activity called MCS tracking method and comparison, where we are looking into how does the different feature tracking methods affect how we evaluate the global MCS simulations, and how does it affect our understanding of convective organization. That's all I have, and I will take some questions by time. Thank you.
We have time for a few questions. Jason, you keep score with questions.
Have you compared this to how mode works? Is this similar to mode?
So we are actually currently have a paper that are about to be submitted where we have participate 6 different tracking methods to participate in an intercomparison. That's the first effort that we know of, where each tracking, well, we have a standardized observations and simulation data sets where we run the tracking on the same data, where we agree on how to define an MCS, and they differ quite a bit. Depends on the different types of metrics that you look at. Some metrics compare a little bit better, others differ quite a bit. So I think it's important that now we have this effort where different tracking tools are now becoming available. We get together, and so that's why I talk about this effort. And we currently have, I think, more than 6 now that participate in this, and we can all run the tracking on global models and look at how, whether the finding depends on the tracking and how do we move forward as a community.
Yes.
I just saw your reference to WRF PGW. Did you end up not just adjusting the temperature, but also the water vapor in the PGW run?
Yes, we did.
I also had a small comment. It's not trying to be overcritical. I saw in your animation for the CONUS scale satellite plus radar, you had a feature coming out of basically Minnesota that took a sharp right turn and moved about 1,000 miles per hour briefly.
Yeah. So if you just look at the centroid, right, for any kind of these bigger systems, it's affected by the morphology quite a bit, right? So if you have merging and splitting things occur, the centroid could jump quite a bit, which is why the mask is important, right? The centroid is just telling you where what is representative. But when a system at that scale, which is many hundreds of kilometers and different shapes, what does a centroid really mean, right?
Yeah, I saw that one just happened to be a deteriorating MCS that must have picked up on a new one that initiated nearby, or not nearby, but in the radius, and it jumped massively in one step. Yeah.
Right. Yes. Yeah. That tend to occur when you have more complicated situations, different life cycle stages. Yeah.
With that in mind, couldn't you just say it can't move faster than some threshold speed and just stop it from doing those, numerical errors, let's say?
Well, so we don't use centroid for tracking, right? We actually use the mask overlap. Yeah, you can set up, there's many different parameters you can set in tracking. We make it easy, configurable. And if you want, it depends on both your spatial temporal resolution of your data set and your research interest, right? So if you relaxed it, then you can track longer lived stuff. But if you say, my data set is fine enough resolution that I read higher fraction of overlap to be considered the same object, then you can tweak those, and that would affect the tracking results. Yes. So we make it sort of configurable for the user, and you can tweak it however you like. Yeah.
One more question.
It's quick.
Yeah.
You mentioned that this is available in GitHub. Are there plans to make it available in other locations, such as like maybe PyPy?
Oh, yeah, yes, yeah. I was trying to see if I can make it even easier, like Conda, for example. I do want to make it easier to like become a package that you just install. I just haven't get the time around to doing that yet. But yeah, we do want to do that.
Let's give the speaker another applause.
Thank you so much.
Our next speaker before our break is Ivette Hernandez Banos from the National Center for Atmosphere Research. Her talk is about investigating the impact of assimilating all sky window channel infrared radiance from GOES ABI and Painemal AHI, I'm sorry if I say it wrong, on cloud analysis and forecast.
Good afternoon, everybody. So my name is Ivette, and I work at NCAR MQ within the Panda C team. And today I'm going to provide an update of our latest activities on all-sky window channel infrared radiances assimilation. So in the last decades, we have had a lot of advances in assimilation of satellite radiances, which has allowed us to assimilate directly the cloud-free and more recently cloud-affected observations. However, most of those have been using microwave radiances with significant improvements in the short-range weather forecast, as reported by Gear et al. 2017, where they report that around 20% of impact on the short-term forecast at the ECNWF. Efforts have been also made towards the assimilation of cloud-affected infrared radiances, but has been mostly used in water vapor bands. And that's it because window channels that exhibit less Gaussian characteristics as compared with water vapor bands. So window channels, they remain a big challenge to the scientific community, especially because of the observations error distribution, nonlinear observations operator, diverse mechanism that we need to apply to the radiances, different quality control procedures that can vary, and of course, the cloud representation in the forecast model as we have seen through the day. In the PandaC team, the team have been developing the interface, the JEDI interface for the model prediction across scales, MPAS, in the last years. And JEDI has this concept of being model agnostic. So we leverage several quality controls, variational bias correction, observations operators in UFO. Among those, we have available the CRTM, which is the one that we use for all-sky operator. We also have several capabilities that we have enabled. And one thing that allows us to do all-sky DA is that we have in our analysis variables, we have these 5 mixing ratios. And we have the capability to assimilate a number of observations, and we have demonstrated the all-sky assimilation of MSWA already in Liu et al. 2022, and we have some work on the way to assimilate all-sky ATMS. We also have developed a workflow that allows us to run cycling experiments. This is very helpful. And of course, we run HFX a standalone application. In this case, we use it mainly for verification purposes. So the goal of this talk is just provide an update and examining the simulation of infrared observations from channel 13 from ABI and AHI using MPAS JEDI. And for that, the first thing I'm going to talk is about the error estimation for these 2 sensors for channel 13. Then about the estimation of the observation bias for the bias correction. Then the experiments that we run for these tests, and finally some verification of the results. So an important part of this is the observation error model that we use. We use the scheme proposed by Okamoto in 2014, which is adapted from Gear et al. 2011 that was initially developed for microwave. This Okamoto scheme is adapted for IR observations. So the principle is that infrared channels, they exhibit errors that are highly non-Gaussian. And in order to to tackle these, we do it by calculating this symmetric cloud impact parameter that the goal is try to make the departures closer to a Gaussian distribution. So this is the formula that we use. So it is the average between the cloud impact from the observations and the cloud impact from the models. And those are the difference between the observations and the simulated observations, the brightness temperature observations, minus the diagnosed clear sky background brightness temperature that we obtain from the CRTM without considering the cloud scattering effects. So this is our scheme and how we do it. So we need for this O minus B statistics. So we use the H of X application with MPAS-JEDI, and then we need the background, right, to simulate the observation. So we use a 30-kilometer forecast from a previously cycling experiment using hybrid 3D and VAR. For this, we use observations with no bias correction. A thing that I forgot to put here is that our observations in our converter, they are super odd in a grid that is 15 pixels by 15 pixels. So it kind of will match a 30 kilometers grid that we use as our resolution. So here we are only focusing over water for this study. And this is the maximum zenith angle that we use. And this was for a period between April 20th to May 18th. So once we calculate all the O minus B, then we proceed to calculate the symmetric cloud impact. And then we get to aggregate those statistics, right? So this looks pretty similar to what we find in the literature. This is for channel 13 for both sensors. So this is the cloud impact average. You can see in the red line, this is the observations count. The blue line is the standard deviation. So you can see that in the beginning, they start very close to zero, as we will expect, right? Because that would be more like a clear scenes. And then as the cloud impact increases, the standard deviation also increases until it reaches a maximum point, which is like the saturation point of overcast situation. And then after this saturation point, it decreases. So the goal here is try to match this standard deviation curve by applying a fitting curve. So from this, we get our parameters that are the ones that we use for to assign the observations. So we use this function that is available in UFO, and these are the parameters that we derive from this fitting function. And here is important to mention that we derive a clear bias value for the whole almost month. That is the one that we are going to use for the bias correction, the constant bias correction in our experiments. And this clear bias is like the cloud impact for the observations. So this is the set of experiments that we run. We run a benchmark experiment in which we assimilate our conventional observations plus AMV, Genesis CIRA bending angle. We also assimilate clear sky M sway and clear sky MHS from several sensors. And then we run an experiment that I call here like channel 13 raw. So it is not purely raw because it is already using super observations, right? But here we add ABI and AHI channel 13, but with no bias correction. That's why I call it raw. And then another experiment in which we use bias correction. In this case, we only use the constant offset for the bias correction. So on the left, you can see this is the configuration that I use for this experiment. I'm not going over those for the sake of the time. So these are some of our preliminary results, and this is a sanity check in which we evaluate our results in terms of the root mean square error of the observation minus the analysis and observation minus the background. So we would expect that if our analysis, if our variational system found the optimal analysis, the RMS of the O minus A will be smaller than the O minus B. And we can see that correctly in all of these panels. So this is by cloudiness from clear to all sky pixels. And this is for both experiments for AHI and similar we obtain for both experiments from ABI. Also, in the verification, we run separately an H of X using the background, the cycling background that we use for the analysis, and then we can compare with independent observations. In this case, we can see the verification against channel 10 that we didn't assimilate, and also channel 13 that we do assimilate. So on the left is the RMS from the benchmark experiments, and then the two other columns are the relative difference, the RMS difference comparing with that benchmark experiment. So blue values here are the ones that are good, they show improvement. And overall, we can see that despite the fact that the results look a little bit mixed, we see more blue than red. So I think that we successfully, we got these good results. And if we compare between both experiments, it's sometimes hard to see the differences, but with the experiment with the constant bias, we see larger improvement in some areas, which is what we would want. So this is a verification in the model space. This is against GFS analysis, the 6-hour forecast against valid GFS analysis. And if we compare results in, between these 3 experiments, and specifically the raw experiment versus the constant experiment, we can see that we get improvements, several improvements when we add the constant offset to the bias correction. We can see, I highlight here some of the differences. And also, if also in the model space, those before we're global. So if we look at, for example, the ABI region and the AHI region, we can see that we also get some degradation. But with the experiment, with the constant bias correction, we actually see some improvement. But of course, it's not perfect, right? We see some degradation, in some levels, and for example here for the wind. So this is preliminary. This is not final. We still have a lot to investigate. So my final result. So this is probably what we all want to see, right? How we are looking in the when we look at well, this is brightness temperature, but it gives us a good idea about clouds, right? So here, this is the most left panel is the observations, and then we have the benchmark experiment, the raw experiment, and then the constant bias correction experiment, and this is for AHI. So I put here a circle in red, so I want to focus on this area. There are other areas that are improved. There are other areas that we will see some degradation, but this is the 3-day forecast. And then if we look at day 2 and finally day 1, we can see that, the main structure of the convection is well kind of represented, in the 3 experiments, but with the bias correction, we actually see most of the circulation and the clouds, better organized in this experiment. And also, I was glad to see that as we go from day 3 to day 2, there was like an overprediction over this area that as we get closer to 1-day forecast, it gets better represented. So it is not perfect, but I think that these results are very encouraging on our current activities. So in summary, we have demonstrated our capability to successfully do all-sky infrared DA with MPAS JEDI. We were able to calculate the observations error and constant bias for these 2 sensors for channel 13. So we can do cycling experiment. This is very encouraging. This was for only 5 days, but we intend to do it for at least for a month, so we can get more robust statistics. We get more positive impacts when assimilating this channel with bias correction, with some good results for longer term forecast. But still there is a lot to do. So we intend to do more investigation in terms of the variational bias correction using predictors that are more related to this all-sky IR. There is this latest paper of Okamoto that he uses the cloud impact as one of the predictors. So we want to explore, their options and see how, what results we get, and also investigate, more of, the observations operator. I think that's all. Yeah, some of the references. Thank you.
We have time for questions.
Great stuff.
So you've got a head start, obviously. It's good stuff, but I'm very, very curious. You skipped land points where the hottest temperatures are. Was that on purpose because they're the hottest temperatures?
Well, we want to kind of start for something, right? That we will expect that will behave better, I think. So yeah, we skip those for now.
Okay. Obviously, you'll have your largest O minus Bs over land.
Right. So for your the variational bias correction, do you have any spin up time?
Not in these results. So I just run for.
So that means whatever the variational bias correction experiment, what you see is basically the only the spin up period.
Probably, but here I'm only using constant offset. So I'm just, for the part of that will do the variational part is only the constant predictor, is not, and I use the same value for each cycle. So yes, so that will help. But I agree. I mean, it's only 5 days, so there will be kind of an spin up time in there.
We see in the Jedi, so it can be spun up for whatever number of cycles.
Update every cycle.
Every update of every cycle. So that's a possibility in the software anyway.
Okay. Thanks, Greg.
It's new, relatively new stuff.
We have time for one more question. Well, if it's not, okay.
I'll ask one more. So how different is how you specify the observation error? Now you look at this channel 13 as compared to the microwave. Are they just similarly the same?
So I think that the main thing is that the channel 13 is highly non-Gaussian. So when you look at other error distribution, they look more Gaussian. So when you look at this one, it looks like it will have 2 peaks, similar to what Greg showed today in the morning. Like we'll have this instead of Gaussian that will have a mean close to 0. It shows a PDF with 2 moments. So when you look at other sensors, they have calculated this kind of symmetric error that will allow us to kind of overcome some of that non-Gaussianity.
I understand, but that technique is also using a microwave region. So I guess I'm trying to understand what you're essentially using here, basically saying as microwave region.
It is an adapter one.
Hello, everybody. So we will continue our section with our next talk. Our next talk is Jesse Turner from Colorado State University.
Hi, everybody. Okay, my topic is on false alarms in the satellite-based infrared difference. Steve Miller and YJ, who gave her presentation earlier, got me started on this topic, and it is related to when maritime low clouds are overstated at night. There we go. So on the left here, I have an image of the nighttime geocolor product, and we'll see that it shows, without visible imagery, it shows high clouds and it shows low clouds. To get this low cloud feature, it uses the nighttime low cloud test, which is the brightness temperature difference between the 11 micron and the 3.9 micron infrared bands. Here on the right is just that nighttime low cloud test, showing the brightness temperature difference in this region. And you'll notice it matches the product on the right. There we go. The brightness temperature difference works because of this difference between the bands here. So the 11 micron band, or 10.7 in this case, shows a warmer brightness temperature for fog than the 3.9 micron band. So when the brightness temperature difference is taken, we get a positive reading for low cloud, and on the opposite end, a negative reading for high cloud. The low cloud test does not show anything in the clear region, where the infrared bands both give the same brightness temperature. So here, I again show the geocolor image using the nighttime low cloud test. And on the left here, I'm showing a sea surface temperature product, satellite derived. And I'm just showing that, among other things, the sea surface temperature products use the brightness temperature difference to identify the low clouds at night over the water. And those clouds will be masked out in the sea surface temperature so that they don't contaminate the data. So sometimes the low clouds look a little different than we'd expect. So on this image, we can see the high clouds here and the negative brightness temperature difference, and the dark colors correlate to the low clouds. And off the coast of Cape Cod here, we have this feature that doesn't move like the other clouds do, and might warrant a little bit of looking into. So it kind of is locked right here. So is this fog, or is this an error in the low cloud method, the brightness temperature difference? Using another example here in the same region, this is on the east coast of the US. We have a similar feature down here off of Cape Cod, a little extra over here and up here, all labeled with F. And then comparing to the day-night band, it shows that the day-night band uses visible imagery at night, generated from reflected moonlight when the moonlight is sufficient. And we'll see that these F-labeled clouds in the nighttime low cloud test do not show up on the day-night band visible imagery. And just to get another confirmation in here, Calypso happened to pass over at the same time. And using the LiDAR aboard Calypso, we found that there was no cloud from A to B during this region where we would expect cloud based on just the nighttime low cloud test. So this all lends us to believe that maybe at certain times, the infrared difference is causing a false cloud to appear. So for the rest of this, I'll be referring to the false low cloud as FLC. So in case you see that, that's what I mean. And on the right here, we have the weighting functions for the two bands. You'll notice the 11 micron band, the long wave IR here, shows a little bit more of the lower atmosphere. And therefore, if when the difference is taken, a little bit of warm, moist atmosphere can cause a little bit of a positive infrared difference. The radiative transfer simulation here shows a similar story where the sea surface temperature is on the y-axis, and we're looking at moisture here. And for cool sea surface temperatures and a moist marine boundary layer, we find that it returns a similar brightness temperature difference as would a real cloud. There we go. So I wanted to look into where this happens and how frequently this happens across the world to see if the problem is causing like a significant impact or not. So we created a false low cloud index using the sea surface temperature analysis from NOAA and the GFS model to get the atmosphere, and using the stuff that we found on the last slide, that the cool sea surface temperature overridden by a warm, moist atmosphere causes a false cloud signal. We decided to look for all the places on the globe where that false cloud signal has the potential to occur. I did this just by creating the index here, which takes the normalized difference between the marine boundary layer temperature and the sea surface temperature, and multiplied it by the specific humidity in that region. Slight delay there. Okay. So here ran over the whole year of 2022. Here are the places that highlighted the most as potential to cause false cloud in the infrared difference. Here is that East Coast area I was looking at before, or near it. We have a spot coming up here kind of from near the Gulf Stream. Another one popping up over here by the Kuroshio Current. Here down by the Falklands Current, and off the west coast of the US, west coast of Africa, north and south, and also the Great Lakes. All show potential to be regions that can have this false cloud error. Great. So just looking into one of these first, false cloud caused by the Gulf Stream is shown in the false cloud index. This is kind of zoomed in it's over a shorter period of time as well. And this can be caused by the warm water coming up from the south, and the cool water coming down from the north creates this strong sea surface temperature gradient. And when there is a wind from south to north, bringing the warm, moist air over the cold water, we get that warm, moist air over cold water that causes the false infrared difference signal. So to see if it is, in fact, the wind that tends to cause it in this region, and if we can predict it, we took some control cases and found that on average, when there is not a false cloud signal in this region, the wind is straight from west to east here, relatively straight. And then when there is a false cloud case, the wind is more from south to north, giving us that warm water pushed up over the cold part of the Gulf Stream. Another interesting thing about Gulf Stream false cloud cases is that you'll see features from the eddies in the Gulf Stream showing up in the infrared difference itself. So here we have this little eddy circle, and this is echoed in the false cloud index on the right here. This is due to the false cloud being locked to the sea surface temperature gradient and not to solely atmospheric features. In comparison, there we go. In comparison, a case where the wind was not blowing northward, the eddy features from the Gulf Stream, which are pretty constantly here, do not show up as they did on the last slide. So in this case, the false cloud did not occur and the eddy features are invisible and the clouds all look how we'd expect. Another thing that causes this infrared difference overstatement of cloud is outflow from cold water into warm water. This can be seen in the US at the Mississippi Delta, where the Mississippi pours cold water into the relatively warm ocean and creates a signal there. Another one here is in this region in Oaxaca, where the cold snow melt pours out from the lakes into the relatively warm ocean and creates the sea surface temperature gradient needed when combined with warm, moist enough atmosphere to create the signal we're looking for. So there's another one. This area is interesting because the mountains that cause the snow melt also cause gap winds to blow through this area. And when they do blow through, they can push the cold water off the surface of the ocean. Push the warm water off the surface of the ocean, causing cold upwelling and increasing the sea surface temperature gradient. So the top images here are the wind maps here. The one on the left is for the false cloud case. This one's for the control non-case. And you'll see that when the wind is blowing through the wind gap region, it creates a higher gradient in the sea surface temperature on the bottom here. But there is still a little bit of a gradient, I assume, from the outflow that occurs there naturally. Another way this is caused, this one's going a little slow, is by, and then we're going back to the East Coast, Cape Cod region, is by tidal mixing. So in this region, we have these banks here, George's Bank and this other bank off of Cape Cod, creating this sort of V formation. And in this case here, this was just last week, we find that this false cloud signal relatively matches the bank shape. So the theory here is that the tidal mixing from the tides going in and out causes upwelling of the cold water and creating the sea surface temperature gradient that we need to see the false cloud feature. This can be seen again here, and it can be seen more starkly by only taking the features from the image that have stayed constant over a time period. So I ran this over 4 hours and only took the features that remained throughout the 4 hours. And we can see this V shape relatively similar to the bank structure of that region. So just to summarize, the standard nighttime low cloud test, the 11 minus 3.9 microns in the infrared predictably causes false alarms in certain regions. And the regions require a strong sea surface temperature gradient and the warm, moist air above it. So anywhere where you get that, you'll likely get this kind of feature. in this cloud test. And this can occur from currents meeting, cold upwelling, outflow from lakes and rivers, etc. In the Great Lakes, which I didn't go into in this one, it might just be from radiative cooling from the top of the lake that gets it cold enough during the night. The next steps are to see if these false cloud signals from the infrared difference are causing a bias in the sea surface temperature data record. The sea surface temperature algorithms sometimes use the infrared difference for the clouds at night. And if they're too dependent on it and the error is frequent enough in certain regions, it will have a bias away from the cold waters that it's masking out routinely. So I want to look more into that to see if that's a thing that's really happening or if the sea surface temperatures are relatively robust to this, the cloud masking. And the other thing here is, can the false cloud index be repurposed to identify potential regions of real fog and low cloud? So the cold water with warm moist air is relatively similar to the setup that can create real fog over the water at night. And that might be an interesting thing to look into in the future. And that's all I have here. Thank you very much.
So this index that you developed using the GFS data set,
yes.
How much model dependency? In other words, do you test with other models? Do you see how robust your index?
No, but I should. I haven't tested with any other models, but I like that thought a lot. I'm trying to look into that.
With the Great Lakes example, is there a specific time of the year that is? Is it?
Oh, that's a great question. The Great Lakes. So Steve and YJ wrote a paper on this last year, and the Great Lakes was talked about specifically in that paper. I'm trying to remember if they nailed down a time. I know if you have a thought, but I don't remember there being a seasonal dependency. That's another thing I want to look at. I think the one off of Massachusetts does have a seasonal dependency, just anecdotally, but I can't say for sure yet.
The climatology map, that's pretty nice stuff. I like it.
Yeah, well, I would love to. I'd love to share it. Yeah, I'll have to make it a little nicer, but yeah.
We have a question online, Stephen.
Oh yeah. Yeah, I just wanted to chime in here. A nice job, Jesse. Getting a lot of feedback here. I think that what that Great Lakes example that we talked about in the paper was due to an influx of warm, moist air that came from a tropical cyclone that came up through the Gulf of Mexico. I'm forgetting the date right offhand, but it brought the moisture all the way up into the Wisconsin and Minnesota area and across the Great Lakes. So it gave you that nice setup of the warm, moist air over the cooler waters. It was kind of a later season storm, I think. So there was some radiative cooling at night. Anyway, yeah, that map shows it nicely as a little hotspot there, but it's somebody commented, this global map gives us a nice idea of where these biases could occur in somewhat of a systematic way across the world and help us to look at things like maybe sea surface temperature climatology biases, because when you throw out what you think are clouds, but they were actually clear sky valid sea surface temperatures, what you're ended up doing is you're biasing your sea surface temperature climatology too warm. So these are areas where that could potentially happen. So that's part of Jesse's work.
Yeah, thank you, Steve. Thanks for the clarification there. Yes.
Have you done any looking at depth of the water over where these areas are? Because I'm looking at that. Most of those areas are relatively shallow, other than a couple specific areas that are really deep water, like following south of the Aleutians is really deep. But most of those areas are in shoal type water or near continental shelf water.
I wonder if that's just because it tends to need upwelling, or if that's something else. That's a great thought. I'll have to look into the depth of the water a little bit more. Yes.
Sea temperature differences to see if there's like a land breeze effect that's actually making it so that you're not forming that fog.
Not directly, but I have a case where, and it's a good one. I actually maybe should have included it, but a case where the air coming from the land was what they needed. I think of how to say this. So it was showing a signal from the cold water, the warm moist air above it, and then the warm air, the warm dry air from the land came over, and the signal just kind of erased. It was a very neat case, and I think it's related to that. So maybe that would be a good way if I wanted to make a method of predicting these. I think it would need stuff like that.
We have room for one more question. Jason.
You think you might be able to create a mask in the future that if you say, all right, we know there's a high chance for false clouds here, and see that we can just X them out in the product.
Like in addition to a normal mask, maybe like, exit out of.
Say it's fairly predictable, right?
Yeah, apparently, yeah.
So could you just get rid of false clouds if you correctly predicted it, and would you be able to remove them from the product?
Oh, yes, now I know what you're saying. Yes, that's something maybe that's something me and YJ have talked about, is maybe just using it as just like subtract out the clouds that are coming in from the infrared difference. And yeah, for sure, especially selectively subtracting the low clouds. And I think it would be relatively reliable. I think so. Thanks.
Our next speaker is virtual. Her name is Eleanor Casas from Melville University.
I'll start over. So my name is Ellie Casas. I am a recently completed postdoc from the Naval Postgraduate School, a new assistant professor of meteorology here at Millersville. I've been here less than a month. And actually, since our last speaker was from Colorado State, I'm also a recent graduate from Colorado State as well, which plays heavily into the topic of this project because I was Michael Bell's student studying tropical cyclones. And so that's what I'm emphasizing here today. I'm really stretching the limit of what we're just calling clouds. And so for this research, it'll be a machine learning talk. And what we're doing is we're trying to use quantified uncertainty from machine learning to produce synthetic brightness temperatures. And in this case, I'm highlighting some of the cool things that we can actually see utilizing this uncertainty. And so just to give a little bit of background, I'm sure most of you are very familiar with microwave products, but this is an example 89 gigahertz image of Hurricane Teddy from 2020, which is my case study for this research. And specifically, this one's the horizontal polarization. And then I will also note that I'm only showing 89 gigahertz in this presentation, but we have been investigating all 13 GMI channels. More on that in a second. But the motivation for this project is really that passive microwave imagery is super useful for identifying tropical cyclone structures, which is the type of thing I care about as a hurricane person. And so some examples of what I mean by that is you can see things really nicely like eyes, especially if they've got overlying cirrus obscuring them. Maybe the eye wall, we can see that kind of structure as well, or maybe even some rain bands as well. But the problem that I'm hoping this product will eventually solve is that a lot of these features can be really obscured by that overlying cirrus. And so just looking at infrared imagery or visible imagery, it can be kind of hard to tell what the hurricane structure is. But if I'm putting on my forecaster hat, I care about that structure because we use that structure. We know that it has implications on rapid intensification rates, for example, and also just classifying the current intensity. And so there's a whole bunch of uses for this microwave imagery. But the problem is it's very sparse temporally, especially for tropical cyclones. This is an example from September 16th on 2020 for Hurricane Teddy. And this is literally all of the data we had for this entire day, including the SSMIS product. This is from the NRL TC page. The SSMIS one is not even usable. And so this is 24 hours worth of data, but we all probably have had our memories refreshed recently with Hurricane Lee. Hurricanes can rapid intensify really quickly within one day. And so this is an insufficient temporal resolution at a minimum. And so what we are doing with this project, not me anymore, but NPS is still actively working on this, is that we're trying to use Bayesian deep learning to quote unquote fill in the gaps of GMI microwave data. And we're currently using GO16 infrared data, so our brightness temperatures. is what I mean by data. And so we're taking, specifically in this product that I'm showing, we are taking the IR and near IR bands from 3.9 micron to 13.3 micron. So anything that's available 24 hours a day where you can actually see the clouds in some sort. We are taking patches of those infrared bands, so 10 bands of patches with 39 pixel by 39 pixel squares centered around a center pixel. And that center pixel is then co-located with a concomitant GMI observation. And so we have a pixel label and a patch input feature with 10 bands represented in there. And so we feed a bunch of these patches. In this particular model, we have 10% of 6 months of training data. So we picked every 10th GMI swath. We co-located the patches along that swath. We put them all in a training data set. We have our input features and our labels, and we tell the machine, figure it out. What is the relationship between our GMI brightness temperature and our infrared brightness temperatures? And so this is an example picture at the 183 plus or minus gigahertz shown. This paper was actually just recently accepted in the AIES paper. Scott is also, I believe he's in the room. You can ask him for details on this paper as well, but I'm super proud of this paper. This is kind of a first look at our products, and we have another paper that is currently under revision right now. Our revisions are actually due pretty soon. So stay tuned for the next update, which is actually going to be representative of the slides that I'm showing today. And so the really cool thing about this product is, first of all, that we can have like full disk imagery of microwave data. And when I say microwave data, I mean synthetic. And so I'm going to just start right off with my eye candy slide, which is courtesy of the NRL GeoWebs workshop. Thank you all for the color bar on the left. But this is kind of a snapshot of Hurricane Teddy during that time frame. This is only 6 hours because of memory limits. These file sizes I did not make small enough. And so on the left would be our synthetic 89 gigahertz brightness temperatures. And the first time I made this loop, it hurt my brain. It might be hurting you right now. I've never seen the NRL color bar animated like this before, and it's kind of mind-blowing. And so some of the features you can see just on the left, we see Hurricane Teddy, which is the strong hurricane on the bottom. And then towards the center of the panel, we can see the post remnants of Hurricane Renee, or Tropical Storm Renee. I forget what its max intensity was. But the thing that I'm really excited about, first of all, I got to point out that this full day of GMI data for our truth didn't even intersect the center of Hurricane Teddy at all on this day. Whereas we have an animated loop of synthetic microwave brightness temperature from this product. But the thing that's super cool about this product is we're not just predicting brightness temperatures, we are also predicting uncertainties. And that's what I'm showing on the right in the grayscale. And the sun is getting in my eyes, so I apologize. But what's really cool about the plot on the right is that it really, really clearly shows the storm structure. You can actually see where the strongest convection is. You see little poofs of white where the strongest storms are. And you can actually, the thing that I'm most excited about is that you can actually see the low-level circulation underneath even some of the thin cirrus within this product, especially if you can see my cursor, like right around here. And right around here, I thought this was amazing the first time I made this loop, and it's even better close up. And so what is this word that I'm showing? If you can read my screen really closely, it says aleatoric, and this is actually the math equation of what I mean by aleatoric. This is now going to be the vocab section of this talk. So these terms are pretty common in the computer science world, which this is an interdisciplinary project between the meteorology and computer science departments at NPS. So super cool on that front right there. But for the aleatoric uncertainty, what is this? I didn't know until I started my postdoc. It is loosely the mean of the predicted variance. So we've got our sigma squared in there, that's our variance. The outside of the sum shows some sort of mean. And what it represents qualitatively is the inherent stochasticity of the data. So like the randomness. And the key point of aleatoric uncertainty is assuming that your model has sufficiently learned the relationship to begin with. You can't really reduce aleatoric uncertainty with additional training data. And to give a ridiculous example of this, it would be like I'm showing pictures of apple orchards, and then I'm asking the model to predict the way to San Jose. Like, It's just non sequitur. Like, I don't care how many pictures of apples you show me. I'm not going to give you the directions that you need. I don't have any data to go off of that's meaningful. And so that's the aleatoric uncertainty aspect. And furthermore, this variance that we are predicting with our machine learning, that's one half of the variance. We also have another half of variance as well, which we call epistemic uncertainty. And so we've got some sort of mean of the actual mean predictions as well. And so the key point is that this is Bayesian deep learning. We are predicting a Gaussian distribution in both the mean and the variance. And so this epistemic uncertainty, in contrast to the aleatoric, this is the part of the uncertainty that can be reduced by additional training data. And so it really represents the uncertainty of the model fit. And to give some visual representations of this, because my eyes glaze over it the moment I see a math equation a lot of times, I have my little PowerPoint animation to go along with this. So pretend we're having a probabilistic linear regression model. And so we have some sort of input feature on the x-axis, and we're trying to predict some sort of output on the y, but whoops, we only have 3 data points. And even though it's a silly example to have a probabilistic linear regression, maybe we are withholding some data points and we're trying to see an uncertainty in what the slope would be, which is how we would compute our model. So maybe we have a line like this, maybe we have a line like this, but really, who knows? It's 3 data points. Like, does our model even know what's going on? Probably not. And so this would represent high epistemic uncertainty. And so if we add more training data, now we can actually get a better estimate of the slope. Now our linear regression model hits low epistemic uncertainty, and we trust our model a little more. And so that's kind of epistemic uncertainty. And in contrast, if we have our aleatoric uncertainty, that would represent the spread around our predictions. And really, I should be showing all those individual lines and all their individual predicted variances, because this is a mean of all of those predicted variances, but I did not show that. And just as another point to mention, this aleatoric uncertainty is really just a best estimate until you think your model has sufficiently learned the relationships. And so in the very beginning of learning, as it's trying to figure out what the mean should be, maybe your aleatoric uncertainty isn't the best representation to start with, so it can decrease a little bit, especially if you really don't have enough data. But once your model has learned what it can learn from its input data features, you really need to add new information in order to reduce this further. And this is also small aleatoric uncertainty. And so that we have 3 types of products that are being predicted directly from our machine learning from our GOES infrared brightness temperatures. And so on the left, we have our 89 gigahertz predictions. And again, this is 10% of 6 months of training data. And so me as a hurricane person, I say it's a good start, but I'm excited for when we have a larger training data set, which is where we left off when I left. And then we also have our 2 types of uncertainty. We have our aleatoric uncertainty in the middle, and we have our epistemic uncertainty on the right. And so I was really excited to see what these differences look like. I think it's actually really interesting that the epistemic uncertainty is a little grainier looking than the aleatoric. But the fact that these magnitudes are super high in the hurricane, that one tells us that the model is telling us that it really needs more examples of tropical cyclones, which really represent the most extreme brightness temperatures you're probably going to see over the ocean for the most part. We need more examples of extreme brightness temperatures for it to learn from. And so this is a really good sign because I want better skill on the left. And then typically when we think about variance, we think about the variance beyond what our model can predict. And so I qualitatively say that this is the uncertainty that meteorologists are probably interested in. And so for the rest of this presentation, I'm going to be focusing more on the aleatoric uncertainty. But this is also a nice zoom in. Oh,
but you have 3 more minutes.
Okay. Yep, that's good.
Right.
I'm most of the way done. All right. And so I'll focus on this one. And so again, I have nice circles to show kind of the features that I pointed out when this was animated as well. And so I'm really excited about how it's really highlighting the low level convection at this point. And then if we go ahead and just increase the contrast of this, it also looks really promising for enhancing our ability to detect the eye and provide a little more constraints on center fix locations, which is literally everything about hurricane research depends on getting an accurate center fix. And so I'm happy to see this as well. And then One thing that I was also super interested in was we have these two types of uncertainty. What is the relationship between them? And so I just took a basic percentage of epistemic over total for each pixel, and I gave it a color bar so that reds kind of look like convection a little bit. And so what the reds really represent is almost entirely aleatoric uncertainty. And we see some really good agreement between the reds on the right, or at least some of them, with the reds on the left, where there is super red pixels. They tend to be in areas of deep convection, or at least recently expelled outflow from the storm, especially since Teddy was starting to get sheared around this point. And the other thing that I thought was super promising was that the lack of dark red in the eyewall location suggests that the epistemic uncertainty is high in this area, which means that if we give it more examples of hurricanes in the future, that we should be able to represent hurricane structure better as well. And so this is kind of my one slide summary, if you want to take a quick picture. So we are predicting our mean 89 gigahertz, which I would like to see more improvement on in the future. We have our aleatoric uncertainty, which is really useful for seeing low-level circulations. I loved it. And then if we increase the contrast of our aleatoric uncertainty, that shows promise at this point for identifying hurricane centers or really isolating where the deepest convection is. And then the percent epistemic shows potential for even further highlighting where the enhanced convection is. And so this is my last pretty picture slide, where I was experimenting with how to visualize all these different aspects of our model output to really create a product that I would want to use. And so this is where I was able to end up before I left. And so with that, I do have a summary slide and some future work, but I am super excited about this because one, you can see your low clouds better than what you can in just the default infrared GO 16 picture. And I think this product shows especially potential uses at nighttime where you don't have the visible to really see the low clouds either. And so I thought this was a super exciting project. I have a word conclusion that I will skip. And then if I had longer to work on this postdoc, I would be super interested in exploring the 89% product and the 37 color products to see if our machine learning is really learning physical relationships. But I unfortunately got hired as a professor too fast. And so with that, I'm happy to take any questions. I'm now at Millersville, but Scott will be a great resource to ask about up-to-date status updates on this project. And so I'll take any questions.
How do you calculate the aleatoric, I can't pronounce them, the epistemic versus aleatoric? How do you calculate those?
So this is on a per pixel by per pixel basis, and this is our actual formula. And so our model is actually outputting means and variances at each pixel. And so what I have been showing is an uncertainty decomposition. So on the left of the equation would be our total uncertainty, and then we decompose it. Or no, I might be getting my subscripts backward. I would encourage you to read our paper for which one's which, because I am blanking. Which one's model decomposed and which one is total.
Okay, hi. Can you clarify when you say you need more training data, do you need the same model at a longer period or different model at different resolution, different physics?
Yeah, so what I mean by model, we use model to describe machine learning algorithms. So it'd be the same machine learning algorithm, but it has more examples to learn from. And so that's what I mean. So once you train a model, that's it.
I have a question for the epistemic uncertainty. If it's machine learning, you're going to have multiple minima. Isn't there a point where having more data is not going to help with the epistemic uncertainty?
Yeah, and that's actually what we want to have happen. We want to have our predictions to have low epistemic uncertainty. In theory, like information theory, I mean, if you had infinite examples of the training data, you would reduce your epistemic uncertainty to 0. And that is the predicted uncertainty. The remaining uncertainty would be aleatoric at that point.
Even with machine learning?
Yeah, these are machine learning variance terms. So these are the predictions from the machine learning.
Thank you.
Thank you. And our next talk will be the last talk, the pressure on you. Ziwan Liu.
You can forget Chinese name, just use the English name, Jake.
Yeah, Jake, from National Center from Atmospheric Center. Richard, yes. NCAR.
Okay, yeah, I will be on time. I know some of you may need to go to airport. So my name is Jake Liu. I'm from, this myself and my co-authors from prediction, simulation, and risk communication section. It's called PARC within NCAR M-Cube lab. So I'm the deputy head of the section. Chris Snyder is the section head. So earlier, Ivette already talked about the ABI-HI infrared data simulation, but this one is focused on microwave reading state simulation in all weather situation, but evaluating cloud forecast using ABI-HI brighting temperature data. Okay, so give you a little bit about our model. So MPAS-A is the model for prediction across scales, atmosphere. So that's our lab's new generation global regional unified atmospheric model built on unstructured grid. Okay, by new generation is compared to WRF. WRF is just so popular and it's hard to for community to move on, but this model is not that new, it's already 10 years. Our first public release in 2013. So important thing is that this model allow variable resolution mesh and also same source code. You can do global, regional, variable mesh, uniform mesh for all applications. So that's very convenient for someone like this new stuff. So, but MPAS Zeta is the relatively new data simulation system for this model. This based on Zeta framework. I don't want to repeat the acronym there. So this project is named PANAC. So we have been developing MPAS Zeta since 2018. They together between M-Cube and the Joint Center. I'm the PI of the project. Chris Snyder and Tom Molinier in JCSDA is the co-PI. This U.S. Air Force funded project, so that's very relevant. Our project is prediction and simulation for cloud. So after about five years development, the system is fairly mature. I can see that. So we can do quite a few data simulation algorithms for both deterministic analysis and also ensemble analysis using various data simulation techniques. One nice thing with MPAS Zeta is that analysis is directly done on MPAS unstructured grid for no matter uniform or variable resolution mesh, global or regional mesh. Okay, so you don't need to interpolate back and forth between regular grid to unstructured grid. So that's very convenient. So next week we will do the first MPAS Zeta tutorial. That's with the latest public version 2 release in early June, just a couple months ago. So that's we have nearly 40 registered for this tutorial. So the one important aspect for this project is to develop advanced capability for simulating all sky reading state with MPAS Zeta. This earlier Ivette already talked about infrared. So there are a few elements we need to implement in order to simulate all sky readings. First of course, you need a forward operator. Zeta, we have both CRTM and RT12. So far, we mostly are using CRTM, so we could use also RT12 at some point. Another thing, when we simulate all sky readings, we need a include hydrometers as part of analysis variable. Currently, we omega simply analyzing mixing ratios of hydrometers. Another thing is so-called situation-dependent observation error model, or another word, symmetric error model. That's just similar to that in Ivette talk, gave this kind of, following the cloud impact. Another angle is the variational bias correction. So when you're doing reading state simulation, normally you have to do bias correction, okay? All this pretty much available in MPAS data. So for my, device talk about infrared, not fully implement variational bias correction, but for my microwave, I fully utilize variational bias correction. So no one yet told a bit how CRTM calculate cloudy readings. Okay, let me give you a little bit of background. So of course you need first of all temperature, moisture profiles, also surface properties. That's common for clear sky or all sky. But for all sky cloudy situation, you need a layer water content of hydrometers. And also effective readers, a lot of people don't know this. Effective readers of hydrometers, that's also important, and the cloud fraction. Also need to mention that effective readers is calculated with assumed particle size distribution of a microphysics scheme. Okay, that's, the Thompson scheme in WSM6 could be different. How you calculate these effective readers. Cloud fraction in MPAS A model is diagnosed. This diagnosed parameter is not a prognostic variable. By Xu and the random scheme, Greg already mentioned this morning. Another important thing is the CRTM, no matter CRTM or RTOF, we need a pre-calculated lookup tables for the single scattering property for hydrometers. Okay, that's very complicated. Also when calculating this table, we need also assume the particle size distribution. And this distribution is not necessarily consistent with those of microphysics scheme. Okay, remember there's some subtlety between those things. And another thing is also important is particle shape assumption. Okay, there's spherical particle or non-spherical particle. Okay, that could be subtlety between the model and the radiative transfer. So we could simulate a lot of more microwave readings or even infrared, but for this talk, I only focus 3 sensors, MSOA, MHS, and ATMS. So basically, these sensors measuring temperature, some channel is for moisture, some is so-called window channel. Window channel basically seeing the surface in the clear sky, and could see also cloud precipitating particles in cloudy situation. So actually, we can assemble all these sensors in all-scale approach, using all-scale approach. Okay, so we run a 4-month-long global data simulation cycling experiment. So the benchmark run is simulating conventional observation plus clear sky MSOA temperature channels from 6 satellites, and plus clear sky MHS 3-watt vapor channel from 4 satellites. Okay, that's not yet, like operationals, there are a lot of more observation we can assume, but it's very decent benchmark. And then we're adding all sky MSOA window channel over water from 5 satellites. Okay, then we also add about benchmark all sky ATMS. ATMS in this case is temperature, molten vapor channel, and also window channels, but from 2 satellites. Okay, then we add all of them together. Okay, we see the progressively the impact of on the cloud forecast. Oh yeah, here. So there are some common configurations in all these 4 experiments. So we use so-called dual resolution hybrid 3D IMR, that's 30 kilometer, 60 kilometer. So we do the minimization, and at the 60 kilometer, resolution, and we use 80-member ensemble input produced from MPAS Zeta's own EDA cycling at 60 kilometer resolution. This 1 month cycling period same as EVAS. Then we run 5 or 6 day free forecast at E0 TC. Mentioned that the all-sky readings microphysics scheme is very important. So here I used the major scale reference suite within MPAS model. This suite using one moment WSM6 microphysics scheme. Then we compare CRTM simulated brightening temperatures from model forecast with superorbed ABI-AGI brightening temperature. Okay, superorbed into kind of a model grid, not exactly. So by doing the superorbing, we have the we can derive also the cloud fraction by using individual pixels cloud mask. Okay, that's I will talk about why we have this, why we're doing this. This is very important when we diagnose the problems. So just jump to the result. The first look at all-sky MSOA readings DA versus benchmark. So verify against HI data. So Ivette already saw this is the 3. No, that's the channel 10 is about vapor channel. Channel 13 is the cloud sensitive channel. So we categorize into 3 scenarios: is clear superorbs and partly cloudy and overcast over the 30 kilometer superorbed locations. Okay, you can see the that's the root mean square error percentage reduction. Okay, for your benefits here, I marked the percentage. So day 1 is 5%, 3%. It's kind of like, you know, impact up to day 6. Okay, even though it's not looks huge number, but remember that we operational center often saying that, okay, over 10 years we can improve our scale for 1 day scale in terms, you know, normally in terms of AC score. If we look at the horizontal distribution of the root mean square error reduction, so there's ABI and HI against ABI-HI channel 13. So that's the root mean square error itself from benchmark experiments by root mean square error reduction, percentage reduction. It's not the blue again is the improvement, not everywhere improved, but you can see the large improvement up to 10, you know, more than 10% over tropical region. Because tropical region is very cloudy, you know, the cloudy readings can do better job. And this is just a showcase about a single forecast, the day 1 forecast, observe the brightening temperature in grayscale. So observed in the clear sky and all sky. So this one actually I simulated also cloudy MHS data. So just you can see here is clearly the all sky DA matched very well this observed here, but here this one is missing clear sky. So then look at ATMS. This TMS is our recent work by Junmei Ban. So this one is so similar thing, but two ATMS satellite, also all channels, temperature, moisture, window channel, versus benchmark against then this fall from analysis time to day 5. Okay, you can see all is positive impact. For analysis time, you can up to 6%, but you know can quickly diminish the interim impact. Okay, 3 minutes, good. So so that's is good. So ATMS we also get positive impact overall. Okay, not everywhere again. So if you look at again the horizontal distribution is for disk, that's the benchmark, that's the ATMS. You can see a lot of blue points means the improvement, you know, again still up to 10%. In a lot of locations, but there are some locations look some decrease. This for day 2 forecast, okay. And then this one a bit busy slide, but I think it's really interesting to explain. So this one I showed in the left is the bias of day 1 forecast. is kind of O minus F. But this bias is as a function of cloud fraction from model in y-axis and cloud fraction from observation. Okay, that's CFY is the cloud fraction from observation. Okay, in the diagonal side, in the diagonal is kind of, model and observation is still consistent cloudiness. No matter it's clear or cloudy. So you can see that in diagonal is bias is quite small, okay? But if these two sides, okay, this side is model cloudier than observation, you cause the cold bias. This side, model clearer than observation, warm bias from our model. Okay, it's intuitively, we know that, but clearly so this, I didn't know aware there was some other work, but all other thing I don't understand here is that here is the observation is overcast. Y is largest bias here, but not in this side. So that's kind of and the right-hand side is root mean square error reduction in term reduction or increase. Day one forecast also as a function of the cloud fraction. So some location red, some location blue, but overall, we already showed overall is positive, but didn't show some location is more inefficient or some scenario is more so okay. So last figure I saw here is the okay, assembly adding all sky ATMS above all sky MSOA. Okay, this is all collectively together. So we still from 2 ATMS satellite, we still gain 2% for different these 3 water vapor channels, 3 window channels from day 1 to day 5. Okay, that's statistically also significant. So that's I think is quite good. We get here in relative short time. So just give you a few concluding remarks. So first of all, I feel the cloud fraction, these couple of days we talk about a lot of cloud fraction. I do think cloud fraction is quite crucial. So cloud fraction mismatch between model and observation seems the largest error source. When you're verifying the cloud forecast in ABI bright temperature space. Okay, we need to make that right. And all sky microwave readings DA is overall effective to reduce cloud forecast errors, especially over tropical regions, even though not everywhere. And we expect we will have larger improvement from more advanced DA technique like hybrid 4D in VAR. We are readily available to do that, but we need more computing resource and higher model resolution. And also we will simulate more and more satellite data. A few considerations for future improvement. So one is cloud fraction. So currently MPAS model cloud fraction is diagnosed variable. It's not prognostic variable. I know some center using cloud fraction as prognostic model. We can even do, analyze consider it an analyze variable. And secondly is that if we do 2-moment microphysics scheme, I think we should also analyze number concentration of hydrometers. The thirdly, I think the DA and other techniques, together could be more powerful. For example, data simulation, machine learning. That's all I have. Thank you very much. Any questions?
For a few questions.
Yeah.
Your data thinning with respect to MPAS grid?
Yes, the thinning is quite conservative. We use 145. It's conservative, yeah. I think that's common practice in current operational centers. Some use more aggressive, some conservative, yeah.
The other comments, excuse me, about your previous diagnosis about the seeing on my type as a function of the cloud fraction.
Mm-hmm.
What do you think the possible, what caused that kind of phenomenon? Is that because the observation error model you're using? Or maybe go ahead and explain.
Can you go back to this? Oh yeah, there it is.
Okay.
If you notice,
the O-F is decreasing significantly up the axis. It's not as obvious until you really look at the scale and you see it getting lighter blue, but not certainly going to reach orange red. So these are clear model pixels, model clear the knobs. These are clear model pixels where there's likely convection in the atmosphere. So O-F is huge, which makes sense, right? But the cloudier the model gets, at least the differential starts to decrease. So the model has some clouds, just not tall enough clouds, because these are going to be very cold clouds to give you the largest O-Fs in the clear sky shape. So I was very careful to look at that very point because I thought the same thing. It needs to get cloudier. But my guess is, Jake, I was going to bring this point to you. You have a convective scheme active. You're not passing the convective cloud amount to the radiation and to this H of X, are you? Because we're not in JEDI.
I'm not sure. I'm possibly can have convective cloud amount. This distinction, I'm not aware of that.
Because basically you're using explicit microphysics cloud in isolation without the convective cloud amount. So where the model's physically getting some convection right, it's not being accounted for in H of X at all. And I have the same problem. I don't have the variable available to me yet. I've got to get it added.
Okay, we can talk that offline. Yeah. Okay. Great.
One more comment on your cloud fraction scheme. Shu Randall's going to give you a binary 0 or a 1. The only way you get cloud fraction is from your superobbing. So as you leave superobbing, both the model cloud fraction turns binary and the observation becomes more binary as you get higher and higher resolution. Because right now your cloud fraction is coming from that footprint of 25 kilometers. So you get cloudy pixels next to clear pixels, you get a cloud fraction. And I'm doing point by point DA and not using superobbing, which means it is more likely either to all cloudy or all clear. I don't have to worry about the cloud fraction part.
Yeah, I agree. But that's the convective scale DA versus this 30 kilometer. Okay. When I'm also doing regional I'm part zeta not showing here, but in that case could be different. The approach. Yes.
Just be careful.
Yeah.
Yeah. More questions? Jack? So let's. And basically we'll close our, workshop. Yes, our talk today.
That concludes the talks. I want to thank everyone for coming and presenting these great talks. We do have some breakout session topics. I know it's really late in the day, so I don't know how much time we're going to be here until about 5:30. So maybe just a brief wrap up of some of the things that we've been talking during this conference or this workshop. Unfortunately, the breakout rooms don't have internet access, or at least access to Zoom. So unless the online participants want to stay in this room, the other breakout rooms don't have Zoom in them, unfortunately. So I'm sorry about that for the online people. So this may be the time you want to jump off, unless you want to hear what's going on in this room. Maybe we could work that out, that the most popular topic would be in this room, and the other two rooms, we would just go and discuss the other topics. But let's see, I will show, let's see, the breakout topics. Yes, if you look carefully, this is where my novice shows. So the breakout topics there. So these are just very general topics we were thinking about. One could be just verification metrics or verifying clouds. That would be one of them. Observational uncertainty would be another. It's come up quite a bit in this workshop. And then mitigating cloud forecast errors. That's another one. Like, that might be DA or fixing the model physics, that sort of thing. So
I'll do it here. We just
that might be a better idea. Since I think because that's a shuffling around the rooms, and then we wouldn't have to lose the online people. I think that's a good idea. We can just talk a little bit amongst ourselves here about what we've learned over the last couple of days. And maybe I'll give people five minutes to, go to the bathroom or get a drink or escape if you want to. So we'll just reconvene here in 5 minutes. I will do that. So there've been so many great discussions out there in the hallway. And now we just have to discuss this as a group. What are the big picture things that I've gotten out of this? I just want to kick it off with some of the things. Is observational uncertainty, that some of the things that Greg talked about this morning. That's a really big deal. That if we're not even measuring the relative humidity properly in the soundings, a lot of times you just shrug it off. Oh, there's not much water up there anyway. But if we're not assimilating that properly, how are we supposed to be simulating clouds properly? So that was one big thing. Others like, how do we verify clouds? What is a cloud? I'm just throwing out questions here. Does anyone have any comments? What did you get out of this? How is it that we're going to improve cloud forecasting and verification? That's really the answers, the questions that we're asking here. And what are people's impressions? What is it that we can do? What are the top things on the list that you think that we should do focus on going forward to improve those? So let's open it up to the group.
You can go first.
Great. I want to say how impressed I am in totality with the verification metrics that were discussed at this meeting, because we have, Sarah and Jason I've worked with the most on this with the brightness temperature verification. And I would say on our side, the RAL side, when I was doing that work, Maria Fridiani did a lot of the work on the other metrics, hail size, reflectivity, etc. So that, clouds are just part of the picture. Clouds make the reflectivity and so on. So that's a big deal. But I also loved seeing what Eric is doing in mode space and everybody else's use of mode, Hui's use of mode, and newer metrics methods, because that's what it's going to take. It's a big concept picture thing. We can't do it. There's no RMSE is passe. It's done. It's not doing the job, right? So without more of these techniques. But while I say that, I also say that as long as I've always used the word holistic when it comes to verification. If one size fits all is never working. But I'm not a verification heavy person. So I don't have more to say than that about verification. And you already know my viewpoint on fixing cloud forecast errors. Use the Thompson microphone.
Are we at the point of diminishing returns in terms of microphysics?
Oh, that hurts. No, it doesn't. I left the job on microphysics almost behind. I'm not entirely out of the picture, but I'm most of it because of how I personally feel that isn't the biggest fish to fry anymore. I've switched jobs and moved on to data assimilation. That's how strongly I feel about the fact that I can't sit there and spend another 10 years tuning knobs. I'm old enough, I got 10 years left. And I'm not going to spend my last 10 years going like this, fiddling in microphysics knobs, which is why I presented the stochastic parameter perturbation stuff as the heaviest chunk of my talk. It's because all the tuning more that I can think to try isn't getting us there. And I talked to Jake about what we can do with how to improve water vapor initialization. And I know Jason's got work in this background in DA as well. And it's like, that's where I want to be. I want to go after the next bigger fish.
What about aerosols?
Oh, and Jason knows my background on this one. So I have aerosols is another pet peeve project because you can't do it with one moment microphysics. You can't have a constant droplet concentration. You get your sizes wrong, you get your radiation wrong, but aerosols is a whole nother topic. I don't want to open that can of worms in a cloud verification workshop.
Several talks we're talking about this. If we really knew the aerosol distribution, which is big ifs, you'd be able to observe it. Would that then open it back up for microphysics?
To a degree, obviously. I mean, fire aerosols affect clouds. That should be quite obvious. Marine aerosols are different than continental aerosols. We know that. But in a bulk, really bulk view, I think we have a starting point. That's why Trude Eidhammer and I made the aerosol aware schemes to give it aerosol awareness, because you can't afford wharf chem type physics in an operational large scale model, period. You can run your case studies, but you can't do it real time. So you got to dumb it down. I'm a dumb it down person. You know, when I told Truda, we have to take aerosols and make them 2 numbers. We have to have a water aerosol, we have to have an ice aerosol, and that's all we're going to do. And no mixing ratios, just number concentration. You know, I think everybody in the world thought we were insane, but the real pollution experts, the people that write the CMAC model for aerosols, probably can laugh us out of the room, and that's fine. But I wanted to show that water drops nucleate in continental clouds differently than in rural or continental locations. But even if I had the best aerosols around, we still have the uncertainties of the model and the vertical velocities that create the CCN. So I still don't think that's as big of a fish to fry as getting DA better and getting inputs better, because that impacts the forecast 1, 2, 4 days later. Jake showed it.
So what do we do with DA? What do you think? Is it cloudy DA?
I want some other people to answer.
Yeah.
Just first of all, in terms of verification, I do think if there's a community, cloud verification or whatever, if we establish a common ground for verification metric, the cloud verification, that'd be very helpful. Otherwise, okay, collectively or just one single parameter or collectively somehow, because I think otherwise people can always claim, okay, I do better than you, okay, with different metrics, right? I think we learn a lot, from NWP world, like ACC score, 500 meter ACC score. Okay, we can claim, okay, we do ECMWF, we can do 0.6 for 8 days. Other centers just can do 7 days. And for ground precipitation, people also using FS scores. I think pretty standard. But for cloud, is really, I did from my knowledge, I don't see there's some golden standard or golden rule. What we should really, I think that the displacement and the intensity of the amount, the cloud fraction, all those kind of things. So I think if as a community we can come up with something, that would be very beneficial, I think, to the community and to our own research. I know there are some other, we attended like some, it's called ATOPS conference already happened for more than 20 years, maybe 30, 40 years. So this community, they do, continuously those NWP, satellite DA. I'm not sure this workshop going forward we will do regularly or so. But if we do that, I think that would be very nice to me, again, for the cloud community, really. Like Ivan first day said, okay, even cloud definition sometimes even confusing, So I think it would be, we establish some common ground, people really okay. Everyone we against same thing. Okay, so that's my just a little short.
Yeah. This very meeting is a seed toward getting a little closer to that, since we did talk about so many metrics and different groups doing different things. I thought that was pretty good.
Yeah, diversity is good, but
Yeah.
we need some, I think, more common thing. I think.
Yeah, I agree.
That's important with mode. Well, who's the high PY Flex store? I forget his name, but you said that there is an intercomparison going on. I don't know if anyone's.
That's for the tracking software.
Tracking, or just tracking. Okay. I know I work with Mode Way, and we scratched our heads for a long time to figure out how to choose the parameters. I don't think we still quite know what was right. And there's some knowledge here in this room. Does anyone have any comments on should there be a list, or at least some forum where people know what the parameters are and how they react, and maybe certain clouds that we verify, we should take certain mode parameters, match those clouds.
I have one thing on the comment. I'm looking at you guys put different weight on different, the table you listed out, was like, well, I did not do that. I just use whatever's default value. So I guess from you guys, more experienced users, I know you can configure those weights.
Yeah, you can config the weights, you can config, so not only is it the weights, there's also like, some of it's stepwise, some of it's, no, just a straight slope on how much it is. So like, you can set up the configuration that from like 0 to 20 grid points for a centroid distance is just 1. You can change that to 10, you can change that to 5. There are so many, maybe it's a bit like microfit. There's so many knobs you can change in mode, and I don't think there is a right answer. It depends upon what you want to put emphasis on. You don't care if the objects are the same size, you just want them next to each other. You set the weights to 0 for all the area stuff and just go with the distance ones.
Starting to use mode, that needs to be out there. There needs to be either a publication or maybe a arson project where you start really investigating mode, because a lot of people are really interested in mode. And it speaks to something very primal. You want to see where this object is and how good the model is predicting it.
Let alone mode TD, when you gotta have the 4th dimension in there.
Yes.
Right? So a timing error of an hour is, the stats are trash, but an hour forecast offset of some, MCS initiation point, that ain't half bad. You know what it's like as a convective forecaster. You're not gonna get it bullseye on the hour in every case. You'll get some of them well and some of them not so well.
I tried mode TD once, and that was the only time I tried it. That was the paper that we were on.
Yeah.
Where we started with an object and then like took it forward in time and saw how everything else did it. But that was the only time I've ever tried mode TD, because that is a whole nother can of worms.
Jason, Sarah brought a really good point that instead of you use one single pixel as a centroid, you can try to make it bigger. So there's more pixel at the centroid. So it's work more as a cluster, also a cluster problem.
Yeah.
And it could increase your chance.
So I wonder if that's something to communicate to Tara meant.
So I
Maybe there
think,
should be, as part of the
Yes.
next map workshop, something where we'll get together and start talking about mode and what the parameters should be, and just communicating it. We don't know what the parameters should be.
And I didn't get a chance to get into it in my talk because that's really getting in the weeds, but I showed you how like we take the interest score and we break it out. That's not technically correct, because in the interest score and mode, the centroid distance gets the confidence, instead of it being 1, it's whatever the area ratio is between the paired objects. So like what I even showed you up there technically is not correct, but it's the best that I could do without really getting into the weeds of it. And like that's going through like lines of C code, trying to go through that. Like I did visiting scientist back in 2015, and that's the only reason I know how a lot of that stuff works, is I actually got to sit down and talk about how did the interest score get calculated and all of that stuff.
So
So
the error ratio that from the Met 9 and 10, that definition of that is actually different.
yeah, they changed it, I know. That surprised me at one point, because I'm like, why is my area ratio over 1? Oh, they now have said it, so it's like, I think it's just forecast divided by observation, not whatever is the largest but less than 1.
And when you're looking at it too, from a model comparison standpoint, those different knobs and just testing the sensitivity and the different values of those knobs can also give you a good idea of the robustness of your results. If model A is better than model B, despite the tuning of different parameters, you can get a lot of information there. So I don't know if I would endorse so much of a standard set of tuning things so much as a standard set of sensitivity tests to what you're doing, which I know you guys have done lots of different sensitivities and just trying all those different things and looking at how it affects the results.
But it depends on what metric you're looking at. Some of the skill metrics are pretty robust, remind of whatever the metric, what knob you're tuning.
Yeah.
But other metrics are more sensitive.
Yeah.
I'm thinking about just a light bulb come up in my head is that it could be a very good problem for machine learning, because machine learning could do turn the knob for you as we will combine a machine learning and math together and get, so that like it would not choose the knob, the weight, the centroid, the distance by us, but it's based on the data set that you put in.
Machine learning does that internally. They do the
Yes.
super parameters, right? They
Yeah, so-
investigate all those little things in the algorithm itself. to see How
Yes.
sensitive it is.
So we can upgrade it. Upgrade is not a word. We can do a two-step machine learnings. So
Then
that, it's a feedback of mod and come back. Instead of it's instead of machine learning train on the error, it would train it on where the error with the different selection we have and turn around and choose different error, different option, so that it would turn a knob for us until it's get the best
Well,
option.
except the problem is that what is the best, just the most stable isn't necessarily the most relevant.
Exactly, I was wondering, how do you quantify your machine learning model?
That's
What's the
how.
truth you quantify your machine learning model?
But the thing is that the machine learning model will based on how the error is, so it depend on who is the architecture of it. So you have to architect the machine learning that to prioritize what kind of error or what is the type of error we want to look at.
Yeah, but the issue with machine learning, then, my machine learning is, limited. I use convolutional neural networks, but you want to talk about knob turning? And what do I want? What's my learning rate? When do I stop? And now you're just like, let's turn these knobs instead of these knobs.
Actually, in the CNNs nowadays, they call it hyper parameter tuning.
Right.
So they will tune each of them for you. Actually, I can have a slide, I can show you it, do it for you.
Okay.
Based on,
But that's going towards a known target, and that's the.
yeah, so it's can based on all of that.
Known target.
For example, I want to try to train a model that based on every value, on ETS score, accuracy, POD, FAR, everything that I put on in that, the metric. So it will be go through and turn all the node, trying all the combination and give us what is the best. They think, from other different option of the hyper tuning. And that is the only problem I thinking of is that it will be considered highly computational.
I was gonna say, we're taking a simple verification problem and making.
Yeah.
Come back 2 months.
We change our own tail, but that will be a standard way that if you don't want a human sit there and just tuning it. And machine learning, they don't have the knowledge that we have. So so that it will take longer.
The reason RMS is such a popular method is because it's understandable, right? Even mode, it's hard to understand what it's doing because of all the knobs to turn. And although it is giving you something that's very, it's something you can grasp. How graspable is it actually? Because there's so much variability in what it's actually measuring. That's getting at the squishiness of the problem, right? That we don't know what good is.
I think
Good is in the eye of the beholder.
I think it's actually moderately decent, and especially sensitivity analysis, right? So finding out if change A makes a better final answer is probably what it's best at.
Yeah,
The purely goodness of a forecast is much better, at least comparing A versus B's.
Yeah,
Would you agree?
Yeah, if you take you have your centroid distance and you give it a value of 2, everything else gets a value of 1. Well, if you give it a value of 4 and it's much better, or you give it a value of 4 and it's worse, then you know that it's not as good at getting the center of the objects next to it, that your model just isn't as good as that. So there is a way you could do it by changing values. I wouldn't start with what we did, I'd start with 1s across the board and then change stuff that way. But if you put more emphasis on something and your model gets worse, you know that it is worse at that one attribute.
So one comment about how Jason described something that's graspable. So since this is a DoD workshop, Jacqueline brought up yesterday during the panel discussion how important communication is and being able to communicate errors and, so my question here is changing subjects a little bit for Ray and the Air Force guys. What sort of verification metrics specifically for clouds are you guys find most useful? Is there anything that would be useful that you're not seeing or something,
That's pretty easy for us, anything. The only cloud verification thing we have is, I think it's comparing cloud fraction in eighths for the new OPSI ensemble members against the UK meta-analysis. We had, well, we have, I still have Jason's cloud code, which still is missing one module in PyPy. So I can't do anything with it legally.
So that uses Wimka as its box.
Yeah, which we still get Wimka in and we released that, and I've had people, hey, Wimka failed. I don't know, go talk to 16. But I mean, from the Navy's perspective, kind of going at this, expanding a little bit, Eric, on what you had there, and kind of going with like the simplicity sort of thing, like the verification webpage that I have gets lots of hits. Almost every single one of those people that hits that page is NRL, is FENMOC, is like the senior chief that has 30 years of experience and no longer considers themselves to be a forecaster, but now wants to make sure that their forecasters are forecasting correctly. It's none of the people that would have the most benefit from knowing that NavGem is too strong in this situation or anything like that. And that's kind of where, like, the last slide I had in my presentation yesterday was, how do we describe something simply so that the people that could get the most benefit from knowing that to apply to their forecast will use it, while also having the exceptionally complex, heavily weighted mode output so that researchers and the developers can actually make the most valid improvements. That's something I've never really had an answer to.
Because there's no universal answer.
That's what I'm thinking.
Just pick something and then we'll talk about it. Fog. What matters for fog? What I can see again. And when I can launch planes off a carrier. I mean, so there you go. So then you just, that's your metric. So can you do that or not? And everything else, modes, and they're all good tools, but I mean, you know, those are the complexities that you have to hide to make it do the question as simply as possible. But the question is easy.
Yeah, so the question, with the question being easy, the answer being difficult, the question then becomes, how do you actually make the output be able to answer that easy question?
Well, in that case, using mode, you could run, like, you can run mode in real time and you could calculate the OTS. The OTS is from 0 to 1. So if it's less like 0.1, you give it a green, give it a yellow, and then above 5, it's red, the model's off. Not saying that it's good to go. It's just saying, don't even look at this model because it's so messed up.
Ray likes stoplight charts.
Exactly. That's why it's a stoplight chart. Like,
I don't like it. It's the people I have to report to that like them.
yeah. Yes, there is a way, like using an OTS and mode, you could, everything 0 to 1. So you could distill it down in theory to a stoplight chart. But that doesn't tell you when the fog's going away. It's just telling you this model is crap right now in the fog. Don't look at it.
Yeah, honestly, those are two different things. Like,
Yeah.
this audience does not need to be concerned about how do you fit it in a stoplight. Right now, it's how do we construct the science of the problem so that it makes sense. Then once that makes sense, then we could say, all right, actually, you know, when the fog is up to 1,000 feet in the model, that's good enough to say that there's visibility at the surface or whatever. But like, we don't even have to talk about that right now.
Yeah.
So we gotta figure out the science first.
Yeah, but doing the science with that in the back of your mind probably
No
makes it a
question.
better outcome.
But I mean, it's the use case that matters, not
Yeah.
necessarily seeing it fully through.
Right, you need to pair the overall statistical methods that we're talking about now with like a casebook of case studies. So like several of the talks had these eye-popping or eye candy images that were examples. And so that's how I think you tell the story, is you distill it to, here is the weather scenario that this is valid in, and here's what we usually see. And that usually is backed up by the statistics that we all make.
I agree. I mean, clouds, what do you want clouds for? Then it'll define it. Aviation versus visibility or line of sight versus, you know, DE, whatever it is, that those are all different use cases.
Yes.
I was thinking about this as the discussions have gone on in the last 2 days, that I think
the science question verification is 2 orders of magnitude more difficult than the user verification question. Because the user, we have use cases where the whole thing is completely automated, and it doesn't matter if your displacement, was just a little bit off. Like, it's wrong. It just doesn't matter. Like, it did not forecast that correctly. It doesn't matter how awesome your model was and how close it was. It doesn't matter, right? So I think like your general error characteristics are very useful for the users. Is this typically forecast too much or too little? And how often does it get it right? But then, trying to improve the science, it's much more complex.
Well, except that I think with a lot of the user stuff, getting the right observations to be able to, other than, the pilot who experiences it, but that doesn't get often shared back to as an observation, right? So as you said, if this cloud needs to be in the right spot, or if I thought it was over there and I fly here and that's where the cloud is and it's super cold water, now I'm in trouble.
Right.
But what is a standard observation of a cloud?
Well, yeah, that remains to be a very tricky question, right?
Or the observational uncertainty part feeds back into the verification there.
I was gonna say, that's what I thought was the biggest need for verification. That question you posed for everyone was like more observations / a standardized understanding of the observations. Be very good.
And there are ships for the Navy that are taking all of those observations and they just write them all down. We don't get a copy of them at FenMock because it's, not the METAR. Basically, we usually get the METARs. And since the ship positions are usually not unclassified, trying to use that data, it usually takes us 2 years to be able to actually use the data in anything to go through the declassification processes. So just even if we had all that extra data, we'd have somewhere to start potentially, but it'd be at higher classifications.
That's why I've had so much trouble over the years doing cloud verification. Is the observational uncertainty. For a long time, it sounded like pretty much top down. You can see what cloud top was, but you really wouldn't see much below it. If there were thin clouds, they might be in the wrong place in the atmosphere because they're semi-transparent. I like these ideas of verifying brightness temperature, which I think is really good for model physics, but then like the users, you need to know, is there a cirrus cloud here or is this a cumulus? And it's only recently now that they're starting to get these 3D cloud analyses coming out of CIRA, places like that, where I felt confident enough to start using these.
Yeah, the L2 products are amazingly better than they were 20 years ago because 16 channels on the modern series is a huge help compared to 5 channels. And so we can diagnose partly thinner clouds than we ever did before. So you're right. It's the L2 products have gotten, and machine learning has advanced that, and science has advanced that. It's just tremendous where we are now from the old days. Goes 8. Goes 8. Yeah.
But then those observational data that we kind of treat it as truth, how much uncertainty do we know?
That's a good question. How much uncertainty is remaining?
Well, I mean, I showed an example today of the goes level 2 product for a cloud.phase, and they're keying more heavily on the birth cloud encounter for the top, even though it's arguable whether that's the right thing to do. Because in that circumstance, you're now classifying cloud ice very frequently when you know it's. And so one has to ask the question of how much more should the product be enhanced to say this is two types of clouds. And that's where the NASA group has done a little bit more on that. The SAT core group, Bill Smith, Pat Minnis and company, they've made that a higher priority because partly because their connection with I know I met Lewis Nugent 20 years ago in a meeting called ASAP, and it was about how we diagnose more icing clouds, and that was why. So, and application driven science basically, but to make a dumbed down product to hand to people, sometimes you're just saying, okay, there's an ice cloud up there, we're going to call that an ice cloud, even though, it's a double cloud.
I saw I forget who the author was, but someone had done an analysis, different cloud analysis. They did compare the cloud analyses to one another. Whatever it's true, and then There's significant differences between them.
Well, again, it comes back to the definition of cloud. So exactly the same. Get a LiDAR, that cloud top is gonna be really, really, really right at that first few ice crystals. And that's not an infrared sensor, for example.
So how far can cloudy DA go to help bridge the gap?
I'm betting on it that it can, because the number of channels and the signals you get can all be part of the DA, so I'm sort of betting my career on. Yeah, well, laugh, and it's funny, but I totally think that's.
You say you already have
As
10
a
years
next
left.
question,
Don't
I
worry.
know, I gotta hope there's something fun for that whole 10 years. and it seems like fun.
But if you're relying on the DA to solve that, now and then you're gonna use that to verify the models. Right,
So,
Well, that's the airplane cloud analysis, right? That's their DA, is that correct?
I can't comment on ARA5.
How does that-
Our cloud
How
analysis,
does that-
it's obviously not correct in 100% sense. But I mean, if we think about the DA world, if you've got a channel that's sensitive to those very thin ice clouds, like I think channel 6 is on GOES, I'm sometimes confusing my numbers, then your channel 6 information is gonna tell you that. Well, whereas channel 13 is gonna tell you something slightly different, and there's nothing wrong with that.
No, it just
That's
matters.
where we wanna be.
I know, but then the model is feeding into the truth set that you're using to verify the model.
As Steve Arino saw yesterday. They had a very simplistic. You're just saying, okay, I've got a cloud, and you can see it. Where does the model say the cloud base is? That's really simplistic. Some clouds that work, some clouds that won't. Of course, is that better than using the retrieved cloud index in terms of cloud base? I don't know.
Well, the other aspect from the operational perspective, if you're gonna assimilate all those extra channels of the satellite, you've got to be able to make the DA still perform at speed that the operational center is gonna want to even use that DA.
You bet.
Because if
And hyperspectral geostationary is gonna be nearly impossible, but
I mean, with those 16 channels, I mean, that's gigantic amounts of data.
yeah.
Like I know FedMock struggled just to be able to get all of the pictures through our pipe at
You
one
know about the
time.
Chinese satellite, right?
I haven't heard enough about that one yet.
4 gears is a hyperspectral infrared sound imager. So we're talking about thousands of channels over a geostationary platform, not a strip of land, not a strip of earth with a LEO. Talk about a biggest data set you ever see.
Yeah, I sort of don't see the DoD successfully getting that set up.
Yeah. Europe's launching that satellite next year, and US is called GeoXO, and that's even more years out, but at least it's already in the plan. So it's the wave of the future, but we just keep hoping that computers get faster. Quantum computing, will you come?
I think for the 3D cloud, I'm very hopeful or maybe near future, we will have more small satellite with active sensors.
Yeah.
I think that's the way to go. I think once now it's just too few sensor, right? Cloud side, Calypso. I know Japanese they launched not launched yet next year or Scare. So but I see the small satellite can easily do tens of globally. So that's I think.
I don't know how many people know that every USA METAR site basically has a salometer. VISILA salometers are near visible spectrum radars, if you will, and at least with relatively clean cases of clear boundary layers, not overly polluted and cloud-based, non-raining, the cloud base incredibly well. Again, it's a pencil. Pointed in. It's a pencil, but the number of METARs in this country is, it's 4,000-ish. At what could be 1 minute intervals. Think about that from a DA perspective. And yeah, there's cases like everything else. There's cases when it's going to be washed out from snow and rain. There's going to be pollution sources causing problems with that. But that salometer has more data than you've ever known. That METAR says broken deck at 10,000 feet. It's baloney. This is a vertically pointing sensor with near visible wavelengths that you can see traces in it. You can see Virga coming out of that data set. And the weather service doesn't distribute it.
Well, it should be available by the spring.
Is that right?
Yeah. Well,
Great.
the problem to that is that's US.
Yeah, I know.
Do we, like,
Well, it's worldwide to an extent.
well, that's the bigger question is
I don't know
like,
that-
how well is the worldwide
US
coverage? Are we gonna be able to get that data? Because otherwise, that data really kind of only focuses and helps NOAA, not necessarily DoD.
You have the DoD installations as well.
You do, but I mean, like,
I know they're not as dense as the US, but.
I'm just giving some hope for bottoms, because I agree, bottoms of clouds are tough, and I still don't trust satellite-based techniques to know the deep cloud bottoms, because they can't see deep enough. They saturate and they stop.
So a lot of those train off of CloudSat and Calypso.
Which also have their limits at the melting level.
So why not use accelerometers to train? Is it just because the data aren't available?
it hasn't been available.
Hasn't been. I didn't even know that they were such radar looking things. They look like, they sort of look like a LiDAR, but they're not as impressive. But you can see the scattering signal off the bottom of nice clean looking clouds till they start precipitating moderate or heavily, then you just don't get anything.
And it's only good up to about 12,000 feet.
Too bad when you think about it. Yeah.
But it's,
Agreed.
it's more than we have, but
Do
it's
they
less
not go
than
to
we want.
20?
What's that?
Do they not go to 20 these days?
The newer spice ones are like 25,000.
Yeah, that's how METARs have increased the low.
Previously.
That's how they've increased the height of what they say. If they say CLR versus if they say SKC in the METAR, that's two different things. One of them is clear to, used to be with the number you said, but now it's what she said.
I used to do them, so.
Yeah.
From thinking broader than just numerical weather modeling in my program office, I mean, we have the sensor program office for all of the fixed base Air Force and Army sensors, so it's like 300 some odd sites. I'm pretty sure a while back we changed from producing METARs on site at locations to producing them in our joint environmental toolkit system. So we might be resending some of that raw sensor data back. I'd have to check with those teams.
So when the accelerometer data become available, will it be historical also, or just the new?
I mean,
I don't know that any of that original, any of that original data are stored.
yeah, I wouldn't think so.
Yeah, I'd be surprised if it's historical. I'm guessing it'll be starting from now.
But
I don't know that for sure.
And I have a dumb question, but do we have an archive that we can save all our, like forecast, our data, so that one day we can get it out? Do we have a place that we archive our data?
Well, it depends on what you mean by our data.
Like
There's
satellite data?
well,
like-
there's NCEI
Yeah.
that stores most of the NOAA stuff, but it's not storing all that satellite information. I don't think anybody's holding on. to
No,
all of that.
all goes our series are so far up on the cloud. AWS S3 buckets.
Yeah, that's
It's
my
amazing how many years of data that is
Oh, well, okay.
already.
Yeah, it is. Yeah.
It's in an S3 bucket. I can send you to it. You can just download a Goes PDF file like that. I've been doing it.
Goes, get something from Goes 8 or something.
Oh, no. Goes R series.
Okay.
You can't go back to Goes 8 to 8 to 15. Wouldn't that be nice? No.
So what about the model data? You're saying that if I want GFS data from 5 years ago, is there?
You haven't searched very far, have you? Yeah, it's been available for years.
Is there the place? What if I want
NCEI.
they have
Oh,
everything?
yeah,
They have
that's
all
my question is like,
Cloud
where is the
data.
archive of the data?
I don't know
Yes.
if do they have every variable, every output field?
Yeah, they have a grid A file and a grid B file, but they have real-time files even from the FE3 native grid, which you get the 6 faces, the cube if you want it. God forbid I would want to learn that. Nightmare. But they store the originals and then some net CDFs at like roughly 13 kilometer globally, and then they start to degrade. So they go to 1/4 degree and then 1/2 degree. So the oldest data you get will end up being 1/2 degree GFS.
I'll have to go to you to find out that site, because
There's a Nomad server for real time and NCEI for old, and I have a little wget script I run all the time.
Right.
And it's on Amazon.
That too.
AWS, and it's the 1/4 degree, which I just found out is on Amazon. Going back
AWS
years. Yeah.
The whole 1/4 degree?
It's all free. So you don't even need an Amazon account. You just need the Amazon, either the CLI or the Python Photo 3, and you can get them.
India has a one, I'll download it.
Okay.
Yeah, you can send Jason the link.
Sure.
Yeah. They said maybe we needed it in case we want to test more with the data.
Yeah.
What you want to work with.
Yeah.
when.
2022 data.
More data.
I was surprised for, I don't know, if 20, so I was doing 2023 April, and it was quarter degree.
That's my point, is it ages, the longer it ages off, the
ages
more
off.
they take away.
They
But the
keep
group
a
files are-
big,
Right?
they keep a lot there. And if you just search AWS Open Registry, and there's everything.
The only data set where I found where NCEI errors better than Amazon are JEFs. Because for some reason errors keeps quarter degree JEFs around, not quarter degree JFS. I don't understand.
No,
Oh,
it starts quarter degree, I think, and then after 240 hours, I think it goes.
then it degrades to.
Yeah.
Yeah, no, I was just surprised quarter degree was there like at all.
It's 5:30. Are there any other real pressing issues that anyone wants to talk about? We can keep talking or we can go up to dinner. We're just the last ones in the building, so the last one out, close the door.
And please don't forget something, it will be very hard to get back in if you forgot something.
Oh, okay.
Yeah, it's really against everybody's policy to let strangers show up at the door and say, come on in.
Okay, I think, what about?
Great.
Thanks.